All right, welcome back, and we're on the final lecture, or series of lectures actually. And so now we're going to actually design the circuit board. So in the last couple lectures, we went through and we looked at circuit boards, we touched them, we looked at their construction. We got a working vocabulary of what things meant when we're talking about top copper, bottom copper, when we're talking about what's a via, blind via, hidden via, what FR4 material is, what routing is, what Gerber files are, all that stuff. If that does not sound familiar, definitely go back and watch those videos again so that you have an idea of what we're going to do. So, so what the plan is this. I've built three different projects. One is a magic wand, like a Harry Potter magic wand, a very low cost version of it. So and then we've got an organ, a 12-tone organ, and then the final project is a kind of a Simon game, a matching game, if you're familiar with that, and lights up with colors and all that, and you kind of it plays a pattern of lights and colors, lights and sounds, and then you have to press the buttons to repeat the pattern. But I've based that on an Arduino chip, so it's also a microcontroller based project. The idea of these projects is to take you from something very, very simple to and kind of slowly increment the complexity. Because what we want to learn here is, where do you even start? So you want to design a circuit. You don't want to do it on paper. You want to do it in the computer. Then you want to select parts for the circuit, real parts that you can buy. You want to lay the circuit out in the schematic editor, and then you want to design the printed circuit board, and then you want to build the circuit board. So there's all these real things that we want to do. So this is a very complex process, and there's a lot of steps and a lot of decisions that have to be made. Now, as I was thinking about this and trying to say to myself how I'm going to do this, this is a course in itself. It really is. So each one of these designs took many, many hours to do. So the first one probably took, I don't know, maybe it took 10 hours or 20 hours. The second one probably took maybe 15, 20 hours, and then the last one probably took 20 or 30 hours, the maybe more, the Simon game. So obviously I can't record myself doing that exact same process. There would be 100 videos just on that. So what we're going to try and do here is we're going to go through each design, and I'm going to kind of go through my thought process, and we're going to design it in real time as much as possible. We're definitely going to do the first two. The last one I think is too complex to do. It would just take too long, so we're just going to kind of look at it. But anyway, the whole idea is that we want to learn how to do schematic entry and PCB layout with the Circuit Maker tool. All right. Now, by no means am I an expert in Circuit Maker. I've been designing circuits for a long time and doing layout for a long time with other tools. But with this tool, I'm no expert. It takes many months and sometimes years to become an expert in any of these CAD tools. But the whole idea is, if you know one tool, you can usually pivot to another tool and get the hang of it in a couple weeks so that you can at least use it. And then, you're looking up in the reference and the help and looking at YouTube videos how to do things, all right? So it's a painful process initially, but I'm going to try, and as I go through, we're going to just do this trial by fire. I'm basically going to design things in real time, and you're going to kind of learn as we go. All right, now, a couple things. One, do not try to follow me with your tool as you're watching the video. It's going to be too hard. You're just going to be looking up, and I'm going to press some key sequence, and you're going to miss it, and you're going to get frustrated. Just watch the video. Just watch the entire design series for one of the projects, then go back and try to do it yourself and watch the videos again. This is the best way to do this. And I'll make an analogy. When you're in school and the teacher is lecturing on something really complicated, math or whatever, you spend all your time writing down and trying to keep up what he's saying. That's a bad idea. So what I used to do is not write a thing. I just listen to the teacher very carefully, listen to him very carefully. And then I would go study myself. I wouldn't even write notes. And I found that was much better, because what you're doing is you're trying to just copy all this stuff down and you're missing the lecture itself. So what's good is nowadays you can video things, and we've got video of this. So you can just watch this video after. So just take your time, relax, watch the entire thing end to end, all the different parts of it. We're going to have to break it up into many parts, and then go back and try and follow it. That's how I would do it if I were you, rather than trying to stop the video and play with the tool and all that. Just first do the whole thing once. All right. Second thing, uh, you know, the whole idea of this is for you to see the real process. So this is the real process. And so when we start off with the first project, it's a magic wand. We're going to go through in painstaking detail how you would do something like this. And that means we've got to do part selection, we've got to do price comparison, we've got to look at the sizes, we've got to see if they have footprints and symbols. There's so many details to doing this. And what this is like is we don't want to show you the easy cheating way. We want to show you the hard way, because when you get to it, you're going to be like, wait a minute, this chip doesn't exist, or this is too expensive, or this or that. So I'm going to talk about those things, you know, as we go. All right. And then the other thing is, as I'm doing this, sometimes I'll speed the video up. If I do something redundantly, like if I copy something 20 times and each takes 5 minutes, I'm not going to sit there and just, you know, let you watch just slow video. I'll speed it up. So anyway, let's jump right in. And the first thing that I want you to do is you should have already installed Circuit Maker. So if you haven't done that, go back to the previous couple videos and install it. Or, you know, it's real simple. Just go to circuitmaker.com. You're going to create an account. So see this sign in thing here. So you got sign in, sign up. Go ahead and sign up. You need an email, you need a name, you need a password, and that's about it. It'll send you an email to your email account to verify you're a real person. Click it and then sign up. That's it. All right. So then you're going to go to Circuit Maker, and you can do this from the web. So what you might want to do is what I like to do this. Because the help and everything is kind of online. Remember, this is a cloud-based tool. I'm on the website and I have the tool running simultaneously. So let's go ahead and let's just click sign in here. So I'm at Circuit Maker. I'm going to go ahead and sign in. Okay, and here's my login. So I've got my username and my password is typed in there. So I'll just sign in here, and then it puts up that page is not working. I don't know if that's just a browser caching issue. All right, and then here's kind of the landing page, and we've looked at this before, and we've got all these different things here. So one thing that I want you to do is, and this is a homework, go to documentation up here in the main menu. All right, and you can see there's all these different things here. All right. I really do want you to go through all of these. I've went through them all. I don't remember but 1% of it, but at least you go through it. The whole idea is to know what you don't know. And you may not remember what you don't know, but you'll know that it's there. You'll say, I remember something about that. So if you go through all of this, read all of this, and go through all these links, it really is going to help you. But what I definitely want you to go through is the Circuit Maker Video Vault. So if we click this, all right, and if I recall, yeah, so projects, collaboration, components. So if you click on this, I think it's going to jump. Yeah, and there's only a couple videos of each thing here. And these are embedded. So you probably just want to go to the YouTube version of it. All right. So if we scroll up here, you can, you know, it talks about there's a YouTube site, Circuit Maker, and it's right here actually, if I can find it. Right here. Yeah, so it's actually just Circuit Maker. So if I click Circuit Maker, and then you'll see there's these different videos here, and we'll click on their videos. Here we go. And you can read through and try and click the actual design videos, okay? All right, so anyway, so that's that. So let's go back here. All right, and go back to this little video gallery area. All right, so now we'll click back to Circuit Maker and just get back on this home page so we're get straight here. Okay. All right. So where do we even begin? So we're just gonna jump into this and start doing stuff. All right. So the first thing is I've already launched the tool. So I've got the desktop tool here. So take a look. And another thing, I've got this QI press running right now. So you know, if I hit the over here in the left, you can see what key presses I'm pressing here. And that's going to be important so you can see what's going on with Circuit Maker and try and figure it out, what I'm pressing. And sometimes I have to try things myself. I don't have this all super memorized. All right, so I'm running this QI press little tool here that puts that up there, and hopefully it doesn't crash. If it does, I'll just restart it. But anyway, over here on the left, you should be able to see what's going on with the keys. Now, I've already ran the desktop version of Circuit Maker. This is what we actually are going to work in, right? And it's sitting here. It's waiting for me to log in as well. All right, so what I'm going to do here is I'm going to go ahead and log in, and I'll go get my password, which I purposely make them so complex I don't remember them. And we'll put that in there. We'll sign in. And you can see this page right here mimics this page, very similar. So the web view is very similar. You just can't do anything. You can't work in the web view, but you can look at everything with a web view. All right, so let's go, and we can do this with either the tool or the web view here. But let's start here and just kind of do it with the web view. All right, so you can see I've got a few projects in here. This Cardwino boy is not part of the class, it's just another project, so let's just disregard that. So we've got our 3 projects here that we care about. One is called Crash Course Electronics Magic Wand, one is 555 Timer Organ, and this one is Simonduino Color Match. All right. So all of these things are the projects that we're going to go through, and we're going to actually design these things. All right. So the question is, how do you get access to this? All right. So once you have your account, you're going to go to your projects. You're not going to have anything. So the first thing that you need to do is you need to find these things. All right. So you could type in their full name here, but another thing that we can do is we can do a search, and if we can find the search projects, I believe. Yeah, if you just go to projects in general, now we're going to search. Just use my last name, Lamoth. I think there's only one of me on Circuit Maker. Yep. And all my projects will come up. So again, we don't care about this Cardwino boy one. We only care about, and I don't know, maybe you may not even be able to see this because this is a sandbox project. So maybe I can see it, but I don't think you can. We'll see. Anyway, so here's the 3 projects. So now what I want you to do is click on this first one, this Magic Wand project, and give it a time. Give it some time. Everything is very slow. Okay, so now I don't want to edit this. I don't want to delete it. I don't want to follow it. What we're going to do, both of us, is we're going to fork this. All right, and it's basically just we're going to copy it. So we don't want to mess with the original copy. You can't mess with the original copy. I can, but you can only mess with a forked copy. Now this forking process is a little bit weird. It's just should do a copy, but it seems like it takes a little time before it populates and updates your project view. So you kind of have to bear with it. In any event, so what we're going to do here is we've got follow, edit, delete, and I don't want to do that. So over here, design files, fork, and open. Okay. So what I want to do is I want to fork this, and we're going to see if this works correctly. So when you do this, it says create new fork. So Crash Course Electronics Magic Wand. And another thing, Crash Course should be 2 words, but it doesn't really matter. Crash Course Electronics Magic Wand, and then what I'm going to do is I'm going to call it work copy. And you can see I've already done this. All right, so work copy, and you can call it whatever you want, but I would call it something similar since it's Crash Course Electronics Magic Wand. All right, hit enter. Okay, that progress bar is good news. If we don't see that, something has gone wrong. Okay, so now it's copied it. So now if I go back to so now it's putting it up here, and it's, you know, there are no design files to display. That right there doesn't make sense because we just forked it, so there should be design files. And this is what I mean. It takes a while for this stuff to propagate through. So let's go back home. Go back home. We'll go back to my projects. All right, so now here is the original because it's got this nice picture, this 3D picture, and then each one of these has a picture. So here is the forked copy of this. So if I just click on this and give it a second, all right, so now you can see it says work copy. So now we know we're looking at the work copy, all right? Okay, so that's good. And now look, in design files, they're actually there. There's the schematic and there is the circuit board. Just a moment ago, they weren't. So it took a minute to propagate through the system and the cloud and the database and get back to us. All right, so this is good. Now, what we can do is we can say open here, and what that will do is it'll launch Circuit Maker and then push this into Circuit Maker and open it. But let's not do that. I just wanted to use this as a tool so we can kind of see what's going on. What I really want to do is let's just go to Circuit Maker. Now I'm using the application. This is Circuit Maker application. I've clicked on it down here just to make sure you get that. All right, and there it is. Okay, and again, we logged into this, and it kind of put us to this landing page. And again, we can go to My Projects. All right, and sure enough, there we go. There's the 3 originals, and then here's this working copy. All right, now One thing that I want to do is this. So we can load as many projects as we want over here in this project list. And this IDE is, very similar to many IDEs you may have used for programming or different things like that. There's a number of windows, and you can drag them and kind of attach them to different places and so forth. But the projects window, which will kind of start off in this position here, is the one that we care about. And forget this free documents. This is just documents you may be working on of different things. So what I want to do is this. So check this out. So what I'm going to do is I'm going to click on, this is the original. This is the original that we just forked. All right, but I have a fork of it. You don't have a fork of it. So now I'm going to say Open Design. So this is the original. And you can see it says 1 forks. So now when you do this, there might be hundreds or thousands of forks, right, of all the different students that have forked this. Okay, now, Crash Course Electronics Magic Wand. So this is the original. Now, let's go back here to, let's click up here. And there's lots of ways to do things. We can go back, we can go home, we can do whatever. We'll go back to My Projects again. All right, and then this, we know this is the copy of it. Now, what, if you hover over this, it says Crash Course, let's do it again, Crash Course Electronics work copy. So we know that that's the copy, and then plus it's got the design and not the nice picture here. So we're going to click on this also. All right, and now we're going to say Open Design. And the reason I want to do this is I just want to show you. So here we go. We got Crash Course Electronics Magic Wand. There's the original. And then we have Crash Course Electronics Magic Wand work copy. Okay, and there it is right there. All right, and then currently in both of these projects, so this is kind of the project name, and then it's a container. So it may have a number of different subdirectories, source documents and other things. In the source documents, I've created 2 files. One is the schematic, and it always has the extension SCH-doc, schematic doc, and then the circuit board, the layout, has this .cmp PCB doc. All right. And then I'm using this naming convention CCE for Crash Course Electronics, Magic Wand 01, because it's the first kind of version of it. Now, here's the interesting thing. Now, look over here in the copy. So the copy uses the exact same names, but this file is not the same as this file. It is a copy of it. It's a complete separate copy. It's been forked, and I have a whole another fresh copy of it, just like you will. So the point is, what I want to do is I want to show you something. So let's say that we go over here, and here is the copy, or the forked copy. And let's go into the schematic. So I double click and the schematic opens up. And again, I'm just going to show you a couple things. I want you to make sure you understand where things are and what are copies and not copies. All right. So I'm going to zoom into here, and I believe it's if we hold Shift, no, if we hold Control and then the scrub wheel. All right. And then if you right click with nothing, then you can drag things around. So that's a very common kind of interface. All right, and then there's all these capacitors in design, and we're going to talk about all this. Right now, I'm just showing you a couple things. I just want to make sure you can fork things properly and things make sense. So see this capacitor C2? Let's make it a different value. So I double click on it, and again, you don't know how to do any of this yet, but I want to show you that the forked copy is different. So it's 0.1 microfarad. Let's make it 0.01 microfarad. All right, and then I'm going to save this with Control S. That always works. Control S, save. All right, now what I'm going to do is where it says Crash Course Electronics Magic Wand copy, that's the actual project, okay? I'm going to right click on it to get a typical context menu. And I'm going to say Save Project. Let's save it, make sure it's saved. And then we're going to commit it. This pushes it to the cloud and synchronizes everything. So you always say this commit. And then it says, hey, you've modified these files. Are you good with this before you commit it? Yes, I am. Go ahead and do it. All right, so now you notice all these green check marks. That means everything's committed, everything's up to date. All right, so this has got this 0.01 microfarad here. Now let's go to the original. Here's the original project right here. Let's open up its schematic. All right, so we're going to now be careful. Here is the forked copy. It's got the same name, and I'm going to open this one up. I'm going to double click on it, and then it selects. One thing you're going to notice is because it's cloud-based, things don't happen instantaneously. It's a little bit disconcerting at first. When you click on something, you're used to it being highlighted. It's not, so give it a second. It'll highlight. Don't click it 8 billion times. All right, so here is the original copy. Now, look at this. Control and scrub to make this bigger. There's that C2, it's 0.1. Now here's this version, it's 0.01. The file names are exactly the same, but they're a different copy of it inside of this new container, this new project, which I own both copies of this now. So I have both copies of this, all right? So that's what you're going to do. And so what I want you to do is, I want you to make a forked copy of this project, and you're going to load it up in here so you have something to work with, all right? And then what you're going to do is, that's going to be kind of the reference design. And then we're going to create another new design that we're going to actually build this in, because this is already built, right? And we want to kind of do this again, but we need something to have a reference so we can kind of click over here, right? So what I'm going to do now is I'm going to close the original. So I'm going to close the original here, which close project right there, and I just right clicked. All right, I have the working copy right here. Let's go back here, and I'm going to fix this capacitor value, make it 0.1 back to what it should have been. I'm going to save that. All right, notice it's got that little exclamation, means you know, you've changed something. All right, I'm going to go ahead here, and I'm going to commit this project. Again, it's going to show me what I've modified and allow me to commit or not commit certain elements of it. Okay, good. Now I'm all good. So now here is my forked version of this project. So now what you're going to do, I want you to do the same thing. So I want you to go and you can do it in the application or you can do it here. I want you to go and fork. So let's go back to projects and go to my projects. And you're going to search using Lamoth as the search term. Let's go ahead and do that again. All right, and you're going to, this is the forked copy, so don't mess with that one. I guess you could, I think you can fork a fork, but I've read that you can't, so I'm not sure. Just start with the original. Here's the original. I want you to open up the original, and you won't be able to do anything to this, but you'll be able to fork it. So go fork it and give it a slightly different name, and that'll be your name and your project, and that's what you're going to load. So now once you've got your forked project, now you're going to go into Circuit Maker. Now let's go ahead and close this project. We're going to close this thing, if I can find it. Close project. There we go. And again, like any tool, you can go up here. We got there's a lot of things here. We've got, you know, file, new, open, close all, recent projects, all that. And depending on, once you have a project open, then you have many more tabs and more things to do. But right now we're just trying to figure out our way around here. So we'll go back home in this little web view thing. All right. Now we'll go to my projects. Now I've already forked the project. You've already forked the project. So I'm going to go grab my fork, not the original, just the fork. I'm going to click on the fork. Okay. And then I'm going to go open design. Not edit. I don't want to edit it. Editing means the project information, the pictures and all that. I want to open the design. All right, now it's open the design. Notice it doesn't dump anything into this main window. It's a behavior. Maybe you could get it to do that. But anyway, this is kind of the start tab. So now what I want to do is, here's the thing that we want to copy. All right, so we're going to build this in real time. So let's crack open the schematic. So I'm going to double click on the schematic. It opens up. Now, notice when I do that, all these different things come up. All right, so we got home, we got view, we got project, we got tools, we got outputs. It just got real complicated, right? So for now, don't worry about it. We're going to learn these as we go. All right, and now what I want you to do is I want you to double click on the circuit layout. This is the actual printed circuit board. Okay, and give it some time. It's slow. And yours will be probably much slower. Mine is sitting here spinning. And I've done this, loaded this many times, so even still, it's slow on mine. Now this is a new forked project, so that's probably why this is slow. But once you do it a couple times, then it's very quick. All right, and give it a chance. And it's not crashing, it's just working very hard. Okay, there we go. Okay, so now it's down here in this window. Now again, both of these, all the windows, all the design windows kind of have the same navigation. So once you select one of these things, if you right click, you kind of grab the window. All right, so you right click with your mouse and you can grab the window and move it around with a little hand. All right, now when you want to zoom in here, there's lots of ways to zoom. You could probably go up here and do it with view and some other things like that. Here's zoom up here. So every one of these you kind of go through, zoom in, zoom out, zoom document, etc. But let's go back to home here, our design elements, and I like using shortcuts. So if you hold with the right button here, okay, and if we now do the scrub wheel, that doesn't do anything. But if we hold down, I believe it's Shift and then the right button. No, it's just Shift. It's Control. There we go. It's Control and the scrub wheel. That zooms, and then let off and then grab with the right. So it's just Control and the scrub wheel. That's one way to zoom, and that's what I like to do. I kind of grab it with the right button, move it around, and then I'll hit Control and zoom it like that. All right. And again, these things you just kind of it's like muscle memory. So you know, you just got to kind of figure them out. Okay. So now let's go to the PCB design. Now this one's a little bit different. So the way that this thing works is it's kind of got some axes and whatnot. So instead of putting it in the center of the screen, it puts it down here. That's fine. All right. So let's zoom into this. So again, I'm going to hold down Control, and I'm going to use my scrub wheel. All right. And then I'm going to keep dragging it up. And you can see what's happening here. As I zoom, it's zooming, you know, off center. So there we go, zoom kind of, I'll move the mouse. Now I've got this and I can kind of scroll around with the right button and I'm not holding anything. So I'm scrolling around, let me zoom out a little bit like that. Okay, and so just right clicking and dragging this thing, you know, so you're gonna have to, you know, figure out how to manipulate this. And I can't bring it up any higher, all right? I can't go down here because it's where this thing is positioned originally. Now, right now we're in 2D view. So now let's go to view here, over here, and we're in this 2D view. All right, so now there's this little icon control here. All right, and we can go to 2D layout mode or 3D mode. So we're already in 2D mode here. All right, so now also notice there's a shortcut 2 and 3, right? So that's 2 for 2D and 3 for 3D. So watch this. This is pretty cool. So I press 2 and I stay in this mode. All right, but I press 3 and now I'm in this 3D mode. All right, and so again, I use the right button to drag this thing around, and now let's zoom, Control, and I'm scrolling with the scrub wheel, and this is a 3D model of it. All right, now watch this. This is going to be pretty cool. So I'm going to zoom out a little bit, and now what I'm going to do is there's this little thing you see tracking on the cursor. Wherever I place this and hit Shift, it drops down this little control. So see this control? It's a 3D control. So wherever I drop it and I hit Shift, it puts it. Then what I can do is, again, with the right mouse button, I can drag any of these little directions, or I can just drag wherever I want. All right, and so this is tricky. All right, if you haven't used 3D tools before, this is going to be a little bit confusing at first. All right, now if I want to zoom out, I got to let off Shift. Now with my right button, I can grab it and drag it. It's dragging in 3D, but if I want to zoom, again, Control and then scrub wheel in and scrub wheel out. So this is awesome because you can actually see what this thing looks like. All right, you can see everything about this, which is totally cool. And you can be like, okay, that fits there, and all right, that looks good, and all that. You can just play with this thing and do whatever you want with it. Now, sometimes you can see these parts right here, they don't have any 3D models. And the parts are in the design, but there weren't models for them, 3D models, so they don't show up in this 3D view. No big deal. All right. But you know, a lot of these other things do, which is nice. So when you're picking parts, ideally, you want to go pick a part that you like. And we're going to go through this process in painstaking detail. And if you have let's say you have 3 parts, you like them all, they're all equivalent. Then you go to Circuit Maker and you say, well, part 1 doesn't have a model. Part 2 doesn't have a model, but part 3 has a model and a symbol, so I can place that, and I might as well use that one because I can see it. Now the other 2 parts would have worked just as well, but since they don't have models or symbols, why use them? Now, let's say you have 3 parts. One of them is very expensive, one of them sort of expensive, one of them is very cheap. I want to use the cheap one. The cheap one doesn't have a model. I'm not going to go use the very expensive one just because it has a model, a 3D model. I'm going to have to make a 3D model because I need to use the part. So we are not going to let Circuit Maker dictate to us what parts we use. We're going to hope that it has a part, someone's built a part in the library and has a symbol and a 3D footprint, 3D model and a two-dimensional symbol for it that's correct, ideally, but if it doesn't, we have to make one, and that's a pain, all right? So that's an advanced topic where I don't think we're going to do that at all. You can watch videos on how to do it, but we're going to talk about that as we go and as we make our decisions for our parts. All right, so this is a good place to stop. So you should have your forked copy, and I'm going to press 2 here, go back into 2D view, and then let's go back to the schematic view here. So we're going to stop here, and then what we're going to do is, in the next video, we are going to actually create a blank project, and then we're going to just use this as a reference, as a cheat sheet, and we're going to build this as I did when I originally did this when I created it from nothingness. All right, but we're going to have this as a reference because we kind of want to build something like this, all right? Okay, so I'll see you in the next video. Bye. All right, welcome back, and we're continuing here with the magic wand design. So in the last lecture part, whatever, this is all getting split up in however many ways, but we talked about the magic wand, and we forked the project, and now you should have a copy of it just like I do over here in your projects view. You should be able to see your forked copy, whatever its name is. So in mine, I just called it work copy. And then there's 2 documents. One is the schematic with a .sch doc, which should look like this, and the other one is a CMP PCB doc, which should look like this. And this doesn't make a lot of visual sense right now because it's a top view. All right, but if we press 3 to go into 3D view, remember that 3 goes into 3D view. Of course, this only works with the printed circuit board, and then 2 goes back to a 2D view. Or we can do it up here in the view menu, and it's got all these different things. Go down here to switch to 3D. All right, so let's go back and click home here. And so like any tool, you've got these main menu items: file, home, view, project, tools, outputs, and depending on what you're doing, they'll contextually come up with different kinds of information. So you just have to work through them and figure out. We're going to use some of them, but obviously not all of them. And then make sure you watch those videos on the Circuit Maker website. And there's probably maybe a half-hour video, if that, an hour maybe. I'd watch them all. All right, so so the goal is we are going to replicate this whole thing here and make this complete circuit board and circuit ready for manufacturing. And one more comment. We talked about Gerber files. If you remember that, those are the output files that are used by the printed circuit board manufacturers to actually manufacture the circuits, the printed circuit board at least. And this tool, Circuit Maker, is obviously capable of generating these files, these Gerber files. But because it's a whole process unto itself, we are going to just stick with, we're going to design the first project, we're going to do the second project, we're going to do the third project, then we're going to come back and we're going to start generating the outputs for each one of the projects. I think that's how I want to do it, rather than do the first project, then generate outputs. We'll see when I get there, but I'm kind of thinking I just want to stay with design before we go to manufacturing. See what I mean? Rather than do design, manufacturing, design, manufacturing, design, manufacturing. So we'll see. We'll see how I feel. All right. So now what we want to do is, obviously this is already done. All right. And we want to do this ourselves in real time. So the first thing I want to do is, let's talk about the circuit here and how this thing works from kind of an abstract, all right? And then we're going to kind of generate it. So I'm going to zoom in, and remember, over here, keep looking to your left so you can see what I'm doing. Control and scrub wheel to make that bigger. So what I wanted to do for our first project was a couple things. I wanted to do something that was through hole. That means that all the parts go through the holes in the printed circuit board. They're not surface mount. That means it's easy for you to design. Or construct and design also. The second thing is I wanted to have a couple ICs on here and a couple components. I wanted to have some kind of battery, some mechanicals, so you could kind of see what those things look like. All right, and then but I want to bring your attention to a problem. And the problem is that I completely designed this in this tool. All right, so now I've designed this in this tool. And the problem with it is I don't know if it works. I didn't simulate it. I didn't build it, right? maybe it doesn't work. Maybe there's a mistake or mistakes. So this is the problem with doing schematic design for your designs without doing any kind of simulation or any kind of prototyping. So, and we've talked about this. So typically when you design something, what you need to do is you can use the schematic editor, design pieces of it, piece by piece, and then you can simulate those components, simulate those blocks, or build them on your bench. Verify that they work if you can. Now, some things you just can't build because they're too complex. You need to put them on a circuit board. But as much as possible, try and simulate, build, verify, and then make no assumptions. So just because you got the part in Circuit Maker, a human being made the part, right? So like say this part right here. This is a Texas Instruments 74 HC 393. It's a 4-bit counter. It's got two 4-bit counters in it. And so I looked this part up and I found it in Circuit Maker. I decided I want to use it, and we're going to go through all this. And then Circuit Maker gave me a symbol for it. And it says pin 2 is clear, pin 1 is clock, pin 14 is this, etc., etc. I don't believe that. I don't trust that just because it's in Circuit Maker. So I go to the manufacturer and I make sure I download the data sheet and I look at it and I make sure it's the same as this. I still don't believe it. Maybe the manufacturer made a mistake, and they do. They make them all the time. All right, so manufacturers can have a pin wrong on a data sheet. You hope that if the data sheet is old, so see if you see a date on the data sheet of like 2015 or 2014 or 2013 or 1990 or 1995, whatever, typically if that's the latest data sheet on the website, it's probably correct. But if it's brand new, 2017, 2018, 2019, whenever you're watching this class, there might be a mistake on it. So you may want to go and see if you can find another copy of the data sheet from another vendor if the chip is a generic chip, right? But if it's only made by one manufacturer, then what you need to do is go through the data sheet. There's like multiple places that pinout might be, right? The pin descriptions, the functional description, this and that, and verify it, because believe me, you don't want to build a circuit and have a pin wrong and then have to fix it and relay it out because it'll drive you crazy. So be very careful, make no assumptions, and just double, triple check things as much as possible. Okay, there's no one looking over your shoulder but you. So you got to make sure of things. Okay, so anyway, we want to build this. Let's talk about how this thing works. So originally, I wanted to make something that had a couple ICs on it, use some things that we've talked about, had some mechanicals, like I said, and I like things that are visual and audio, all right? So it's no mystery that I'm a game developer, and I've written lots of games, and a lot of my books are about game development, software and hardware. And so I like things to be interactive, no matter what. All right, like for example, I don't know if you can see, yeah. So sitting here next to me is one of my favorite games of all time. This right here, this football game. And so I played this as a child. This is from 1977. This is 40 years old. 40 years old, still works like a charm. Can turn it on and play it. And it's it's a little football game. You can see there. And this is in Guardians of the Galaxy. Peter Quill. This is something he brought back from the 80s, and he plays it, but he modified it to make it so it's a weapons control system. But anyway, I like things that are interactive. And anything that has some LEDs, some sound is good, because then we can get visual feedback, all right? So what I wanted was, like any computer person, I like Harry Potter movies, and so I've seen them all. And I thought, well, it'd be cool to make kind of a magic wand that has some LEDs on it, and how can we make the LEDs sequence or do something that's not too complicated? Now, ideally, you'd want something that had an accelerometer on it, maybe could, monitor gestures as you move the wand around, right? That's complicated. But you can do that maybe later. You'll be able to figure out with a microcontroller how to do that. But I want to do something very simple. So what I thought was, how about this? Let's take some chips we've used. So one, we need a clock source. Let's get a clock source of some kind. So we use a 555 timer. And here's our 555 timer chip. All right, and that's going to create the heartbeat for the system. All right, and then what I thought was, because there's an equation that describes the frequency that it operates at, right? It's based on the two resistors, RA and RB, and then a capacitor, and I don't have it memorized. But in any event, instead of putting fixed resistors, because that would be hard to adjust, you'd have to solder and desolder, let's put a couple potentiometers in there so we can adjust the frequency. All right, so we've got a clock rate here, and maybe this is going to be 1, 10, 50 hertz, something fairly slow, so it's human speed. All right, let's take that and let's just run it into a 4-bit counter. So we're going to clock it into a 4-bit counter, and as the counter counts, and when you hover over things, a lot of times it goes to octopart and shows you everything, so that's kind of interesting. So as it counts, it's going to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then cycle back to 0. So if we have a 4-bit counter, and there's many 4-bit counters, countless 4-bit counters, these outputs, QA, these are the outputs right here, they're going to cycle 0 through 15 in binary. All right, so I can do something with those 4 bits because they're going to sequence in some way, right? So we could have just taken these 4 bits and we could have just hooked up 4 LEDs, been done with it, right? And they would count in binary and that would look like a magic wand sort of. But I thought I'd rather have something that kind of chases. So I want the LEDs to go in a sequence. Boom, 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 right? So it's like a runway or something like that. All right. So then how do we do that? So we want to turn one LED on for every single code. So we need to decode the count. So the count has got 4 bits. So we need a 4 to 16-bit decoder, which we could find, but that's a lot of LEDs. And to get the point across, we don't really need 16 LEDs. So 8 LEDs will do. So we don't need to use all 4 bits here. We can just use 3 of the bits, right? So we've got QA, QB, QC, and QD. Now, notice here I picked these 3 bits, QB, QC, QD, instead of QA, QB, QC. Why did I do that? Well, because these 3 bits are going to be toggling a little slower than the first 3 bits, right? And all that really helps me with is the 555 timer. I can make the timer go a little bit faster and the sequencing will go a little bit slower. But you don't necessarily need to pick these 3 lines off, right, in sequence. You could pick them, you could do QA, QD, QB, do them out of order, and what that would do is instead of doing a perfect sequence, it would go out of sequence. That might be something you want to do, right? But anyway, this one, my version, is going to count in sequence, and what's going to happen is as this 4-bit counter counts, as it counts, we're going to get codes on here. We're going to get binary codes 0 through 7. As I get those binary codes, now I've got to decode them. So that's what a decoder is for. Now, remember the 138? All right, that's our decoder. That's a 3 to 8 decoder. So here's our 138. So we've got 3 bits in, and remember it has all these different enable bits here. So you've got E1, E2, those are enable low, and then we've got this enable 3, which is high. And remember the whole reason is because these decoders are used in memory logic a lot of times. So instead of adding external logic, so you can have a high or a low or 2 lows and a high, whatever, it has it on the IC, so the IC can help with some of that decoding and selection of the IC itself. Remember that conversation? All right. Anyway, then we've got these outputs. Only one output will be active at a time. Now, active here is active low. You see the little bubbles on these. Let's zoom in. Remember decoders, or this particular decoder is active low. So when you put a code on here, say you put 000, that would select Y0. So Y0 will go low and the rest will all go high. So these are active low. Got to be careful. So they're active low. Since they're active low, I'm going to take each one of these outputs and connect it through a resistor, a little current limiting resistor, to the cathode of an LED, and then the anode of the LED, they're all going to be tied together, and they're going to go to V sub CC, which is in this case going to be +5. All right. Now, some things. If you go look at this IC, the 74138, whether it's LS or HC or whatever, it can't put a lot of current out of each one of these IOs. So this 100 ohm resistor here is for safety reasons, and you can make it larger, you can make it smaller. But the bottom line is each one of these can only drive a few milliamps anyway. So, and we're going to look at this. So the point is that these resistors are for safety and current limiting, but the IC itself can only drive so much current or sink so much current in the first place. So you could probably get away without them. But we don't want to design without things and probably get away. We want to do good design from the get-go and do that. Okay, so this is what we're going to build, and then where are we going to get the power from on this thing, right? We need power for this thing. So we've got these ICs here. These are all HC chips, so these are CMOS ICs, okay? That means they can work from like 3 to 6 volts, you know, whatever it is. We can go look at it, look at the voltages of each. But, so we need some kind of power source, all right? So we're going to use batteries for this. And I thought it would be cool to use like a AAA batteries. So if we go to the actual design here, you can see, and I'll zoom in, these are actual AAA battery holders, all right? Now these mechanicals are not the easiest thing to find. There's not a whole lot of vendors that make these and make nice ones. They make some real cheap ones, and there's some good ones also. Let me do a little bit of 3D here so you can see these. Yeah, see that? And that looks very familiar to you, I'm sure. And then they pierce right through the circuit board, and one side will be plus and one side will be negative. So we got to kind of wire these together in series. So we'll go back here. And so you can see we've got 3 of these battery holders. And again, I've selected these battery holders, right? So I had to go through and see what was available on DigiKey or Mouser that I liked, and I liked their prices, and I liked the product. Then I went to Circuit Maker to see if they even had the thing, right? And if they didn't have it, I would be kind of out of luck because I want to use those. Now, we could let Circuit Maker decide for us and see what it's got in its libraries, which are usually, they're connected to Octopart, but that doesn't mean all the parts have models and symbols. So there's a disconnect. One of the biggest problems that newbies do with Circuit Maker is they type in something they want into Circuit Maker search and they let it pick for it for them. That's a really bad idea because you have no idea about the availability of the part, the cost of the part, the this of the part. You really need to go look at it and compare and read the data sheets and things like that. So we're going to search like a professional engineer would, not like a newbie would, and we're going to not let this tool make our decisions for us. Okay, so let's see here. So here's what I do. We've got an extra little dot here. This is a little connector here. So we're going to get to all this, but when we're in this mode right here and we're in schematic layout, if you just grab something and drag on it, all right, it'll drag, and this little dot, and I'm not sure why this is showing up here. Let me move this. Let me see if I can drag this away. Yeah, there we go. I think what's happened is, yeah, okay. So I'm going to save that. Now, since I've modified this work copy, I've got to go commit it. So I'll just go commit that real quick. And that wouldn't have hurt anything. The design was fine. That was more just superficial. Okay, so now here's a problem. We're going to go look at what voltages these things will operate on, but we need some kind of power. So what we're going to do is this is going to be a real poor man's power supply. There's no voltage regulation. So we're going to take 3 of these AAA batteries, which we know are approximately 1.5 volts, and we're just going to put them in series. That means we're going to get about 4.5 volts unloaded. When they load, the voltage will drop down a little bit. As the circuit draws more current, this voltage is going to change. It's going to vary a little bit, up and down, right? And as the batteries die, it's definitely going to drop down. So this is a battery-powered toy with no voltage regulation. So if this was digital in nature and had, well, it is digital, but if it had a microcontroller on it, something like that, we might want to think twice about just connecting a battery here and not putting any voltage regulation. But here we can get away with it. Many, many toys will not use voltage regulation. They just let the battery run down, run down, run down, and when the battery finally dies, the toy just stops working. We're going to take that approach right here. All right, just as a simple way to do this. Okay, so we've got that 4.5 volts. And that's going to power the system. There's going to be a little switch, and then when you flip the switch, it is going to connect this node here, V sub CC, and then the whole thing will be powered. Anything that says V sub CC will be powered. All right. So that's what we're going to build. All right. And then we want to, and then the other thing is when I got to the actual circuit board, right? So after I did the design, then I got to take all the parts and I got to lay them out to build the circuit board, right? So how did I do that? Well, once I got these battery holders and these footprints, these mechanical footprints, you see this rectangle right here? When we get to this part of the tool, these mechanical footprints will drop down here and you can drag them, and then I actually made the circuit board this size. Let me zoom out. This size, whatever it is, and I can actually go measure that. If we go to tools, there's a distance tool here, and then we can also tell based on the snap grid, and we're going to talk about that too. We've got so many things to talk about. But I can grab it here, see that? And then it's computing. I'm taking my finger and pointing down here at the bottom of the screen, but it's computing the distance wherever this is. So just put it over here, and we can see that the board, it says it's DX is, oops, there we go. DX is 14,085 mils, right? So that's 14 inches or 357 millimeters, okay? So anyway, so I basically designed this press escape to get out of a tool. I basically designed this so it would fit these nicely, and so the LEDs would fit nicely. And I did the whole thing on probably well, I did on a tenth of an inch or a quarter inch as kind of the snap to kind of make the board a certain size and just make it pleasing and make these things positionable and give enough space for everything and all that. All right, but this is a very if you haven't got the board size or the board constraints from, say, a mechanical engineer or industrial designer, a lot of times most guys will just, most engineers will just make it a rectangle, make it a square, make it a rectangle, right? And that's it. And they just kind of fit things in there. But in this case, this is functional. We want to hold this thing like a wand and maybe even do some 3D printing and print something around it, right? It's a little wand. So that's why we went with this size here. That's what drove that design decision. And then I just want to make it as small as possible. So I want to put a little space on the left and right of it. So, you can mount these things. And then, again, we, the height of this thing is basically the length of these ICs. Now you could have said, well, why didn't you rotate the ICs the other way, right? I could have done that, but I probably would have ended up with a longer board, right? So longer or taller or shorter, these are all the things that you play with. Okay, so again, the shape is up to you, as far as aesthetics, and then it's got to be functional, and then it's got to fit everything, but you don't want to mash everything on here. So one thing is, when I did this, I could tighten all this up and make it much, much smaller, and many times you have to. I mean, if you're making a smartwatch and you've only got so much surface area to put the circuitry on, you've got to smash it. But we're learning here. We want to be able to work with this, and we'll be able to get our hands in here and solder these things and all that. So, make the circuits big, make the layout big, so you can work with the parts and get them in here and all that. And then in the end, this looks just fine. This looks nice, okay? Again, there's a little bit of space. It could be a little bit tightened up, but not so much. I mean, I want the LEDs this far, so they have some distance between each. And then these batteries are on top of each other. So maybe we could tighten this area up, but that's about it. That's really about it. We can't do much more. And we can't make the board any wider, if we want to call this the width or the height. We can't make it any smaller because we got these batteries on here, right? So we could make it a little bit smaller, but that's about it. And you got this on and off switch. You just don't want to crowd this too much. And then also, if you have plastics around here, they might want to bite onto the edge. So you want a little bit of room there, all right? Anyway, so that's that. So there's no right way to do these things. It's just the way you need to do it, and you'll come up with your own techniques and tactics as you go. Okay, so all right, so this is what we want to copy, and I just wanted to go through this kind of a little bit so you understand what it is we're doing. So now here's what we're going to do. So basically we're done. Here's the circuit, right? So what are we going to do? Well, we're going to start off completely fresh and do this as if we're doing it for the first time, and we're just going to sneak peek at this every now and then and look at it as a reference. Okay, so here's what we're going to do. So we're going to go here and over in our projects here, and we're going to go to, and again, your guess is as good as mine sometimes, because the way this tool is like a web page almost, and I hate that kind of stuff, and it's very slow, so it doesn't act, and all these tabs and all that. So you got to be careful, and sometimes you click something and it puts it up, and to me this looks like home is selected, but in fact it's file is selected here, and here's home, and now here's view, but file is always up here. It's always highlighted. It's a little bit confusing at first, but what I want to do is I want to do a new project. All right, so we're going to do a new project. All right. Okay, so now here is what's going on. So we want to create a whole new project, and we're going to put it in here, and this is where we're going to create this magic wand thing. We're just going to use this other one that's in the projects over here as a reference. Okay, so what are we going to call this? So why don't we call it, we'll call it Magic Wand Final. All right, we'll call it Magic Wand Final Design. All right, so we'll call it Magic, and you can call it whatever you want to call it. So I'll call it Magic Wand Final Design. Okay, we'll make it public, and we'll say this is the Magic Wand Final Design based on the reference design. Okay, in this case, we are developing this in real time for the course together. And I can always change this, and you can change this. I'm just typing something in here. All right, Magic Wand final design. All right, I guess good enough, huh? Okay. One thing I figured out is once you name a project, you cannot change the name of it. You can delete it and then redo it, but you can't change the name. All right, now we've got all these different things here: main project file, short description, public concept, tags, all these things. I'm not going to mess with all this. You can copy all this detailed description, and then we've got all the different licenses. So I think the license that I've been putting on here is this one right here, which is kind of this copyleft license, Wikipedia-ish. All right, same one that's on a lot of the Arduinos, I guess. All right, so we're going to hit save here. And so this is what you would normally do when you want to start up and make a project. This is what you would do. Okay, so Magic Wand final design. All right, great. Now, there's nothing in this design. So now I'm going to say open design. Okay, and there's no documents here, but you can see it here. We're Magic Wand final design. Okay, so now we're getting someplace. Now, here's still these documents of the forked design, so the schematic and the layout. So that's good. Now we're going to go to Magic Wand Final Design, and now what I'm going to do is this. So there's a lot of different ways you can do this. So you can right-click on it, and like you normally would with any ID, and you can say Add New to Project, Schematic and PCB. All right, so that's one way you can do it. Up here, you can probably go on File and do something, New Document, yeah, Schematic and PCB. So I like to do things like this. So I'm going to right-click right here, and I'm going to say Add New to Project, and let's start with a schematic. No PCB yet. We don't need a PCB. Now, this right here is just called Sheet 1. Okay, that's not very explanatory to me. So we're just going to call this, we'll call it Magic Wand, all right, and we'll call it Final Schematic Document. That's fine. We don't need to put the naming and all that. So there it is right there, Magic Wand Final Schematic Document. And now notice we don't have a PCB yet. We don't need it. Right now we're just worrying about doing the schematic. Okay, so that's what we're doing right now. All right, so I'm going to press Control S and save this. And we've got a lot of little red things going on here and this and that. So I'm going to right click on this and I'm going to commit the project. All right, you must save all documents to form this. Yes, let's do that. All right, so now we see this dialog. We want these things. We're going to click OK. All right, now we're ready to go. So now, basically, we want to, now we don't really want to copy. So here's the original, right? But this is what we want to end up with in this blank right here. So what we're going to do is we're going to stop right here, and we're going to start back up in the next lecture, video, whatever you want to call it, and we're going to start working on this. All right, so I'll see you in the next video. Bye. All right, welcome back, and we're continuing here our lecture on the Magic Wand design. So we have the schematic document up here, and it's called Magic Wand Final Schematic Doc. So if we look over here in the project area, we've got the original project right here, which is the fork. So we made a fork of the source material, so we can mess with this or maybe change it if we want to. And then down here, we've got Magic Wand Final, which is the new project. All right, so we're starting off fresh. And right now, we've only got a schematic, which is this document here. And later, we'll add a PCB. But right now, we're just going to mess with the schematic because we've got to do the design. All right, so first thing that you will want to do here is let's just kind of click through these tabs here and see what's what here. We're not going to go through all of these things and everything that they do, but let's just take a look at them. So in the home, you've got the way that this is set up is there's different blocks. You know, here's clipboard access, circuit elements is this panel, graphical elements is this panel, collaboration, fonts, appearance, just kind of, you know, fairly random. I mean, fonts, who cares? Let's forget the clipboard, that's just editing things. The most important thing is the circuit elements panel. And we've got components, wire, net, bus entry, ports, power ports, a number of different things here, right? So that's what we're going to design the actual schematic with, and those are going to be functional components of the schematic, all right? The graphical elements are more just for looks. These are annotations, and they add no functionality to the schematic whatsoever. So these are things that you might want to put into the schematic just to help separate the schematic, make it look pretty, text, pictures, images, and so forth. So that's what these things are for, right? But the actual functional elements are over here. Now, I typically don't use this. I will just right click. So when you're on the schematic page, if you right click, then a context menu comes up, and then as you go down here, more or less everything up in those menus is available here. So I like to do that or use a hotkey. And you can see here's all the hotkeys here, like component is C to place a component. All right, now again, to zoom in, to move things around, you always grab with the right mouse. All right, and to zoom in, we hold Control and then scrub, and that zooms in. All right, now one thing that you want to kind of decide on when you're doing your schematics is if you're going to use an English system or if you're going to use a metric system and your grid snap. All right, so you can see here there's a grid snap. You may not, I guess you can see them on the video, but there's a grid here. And typically when you're doing schematic layout, you'll set the grid for a certain resolution. And then when you're doing PCB layout, you'll set it for a completely entirely different resolution because they have nothing to do with each other. The PCB layout is very important, what you work in, either metric or English. But when you're in the schematic entry, you know, it's not as important because it's just a picture of the circuit, right? It's not going to be the actual circuit. That said, if we go over to view here, if we go to project, if we go to tools, in one of these, and I'm trying to find it if it's even here where the grid is. All right, so let's see, document options. I believe it might actually be in there. And a lot of times, like, you got to hunt for things here. Got to look for them a little bit. So I believe if we go to project and let's see, document options, yeah. So, all right, so it's in project document options. And here's where this thing is hidden. So this is the document options, and we can see this snap here, how many grids, and then grid size, and these various things right here, and then units over here. So use metric. So right now it's using imperial system, right? So we're going to leave it in that. And what all this really matters is when you're doing schematic design is when you do the actual printing, right? Because this doesn't really relate to anything physical in the physical world. It's just a picture. It's just a schematic. So now one thing is I would prefer to use millimeters in the metric system for absolutely everything, but it seems like CAD and PCB design is still kind of locked into this English or imperial system, and it's been for a while. So even though a lot of ICs will primarily use a metric system to measure the pitch between pins and whatnot, just as many will use the English system. And a lot of times when you're doing routing and whatnot and doing PCB design, you'll always work in a English system using mills. And the reason why is because most mechanical engineers work in mills, and they work in a thousandth of an inch, which is an English measurement. So since the PCB is a mechanical kind of construct, we kind of get stuck with the English system. So it doesn't mean you can't use a metric system, but it just may be harder and more difficult, and there may be conversion. Anyway, we're going to leave this in imperial units. All right, now another thing, so I'm just going to click cancel here. Now another thing, if you go to templates here in project, so take a look here. So see this sheet here? This is a certain style sheet. It's got a certain size. Now one thing that you'll notice is see the title, size, number, revision. This bar here, which has all this information, is kind of going out here in virtual space. And this is so small, we can't see it. So if we go to templates, and we go to general templates, we can change what this is, all right? So if we say A4, and we'll say choose document scope, what do you want to apply it to? We'll just say just this document, all right? And you'll notice it made it a little bit bigger. All right, so there's this A4 size, and now we can see there's more stuff here. We can see the circuit maker logo and whatnot. That just gives us a little bit more room to work in. That's all. And we can see the size down here, and we can change this as we like. Okay, so we could go here and let's do it again. and we can say A0. All right, and if you take a look now, A0 is huge. So this is huge. You can see there's the document information. So this is if you're going to design something really big all on one page. All right, so we're going to go back to what we had there. We'll go to A4, and then I'm going to grab it and I'll zoom back in. All right, so we'll just kind of work with A4, okay? And I'll save that. All right, now, when you're doing a schematic entry, a lot of times what engineers will do, just like in source code, you'll have one page for kind of various elements. So you might have one page might be for the power supply or power supplies, another page for the microprocessor, another page for the memory, another page for the input output, and so on and so forth. It just keeps it separate. But when you're learning, it's easier since your designs aren't going to be that complicated. Just put it all on one page. Just make the page big enough, and then that way you can easily see everything, zoom in, zoom out, and just deal with it. All right, so I would just suggest keeping it simple and not trying to get all hierarchical to begin with. Okay, all right, so here we go. So let's go to our source, which is what we're trying to copy here. All right, so we know we need a 555 timer, and we know we need this 4-bit counter and this 3 to 8 decoder, right? So let's just get right to it. So we've got this 555 timer. Now, this is kind of, so if you look at this part number, LMC555CN-NOPB, all right, great. Now, the one thing that I said was when you select components, and you're doing your schematic design, there's two kinds of components that you're going to be selecting. One are specific components, a very specific IC that only one manufacturer makes. So say one manufacturer makes a certain processor. No other manufacturer makes that processor, which means I have to use that processor. I can't use a generic version of it. There is no generic version of it. So for example, an AVR, an Atmel AVR 328P, it's the Arduino processor, right? Microcontroller. That's the only company on earth that makes that processor. Now, there may be multiple footprints. There may be a DIP footprint, a QFN, a QFP, but I have to use that manufacturer. Now, with other components, there are hundreds of manufacturers that may make the same component. All right. For example, passive components like capacitors, resistors, and so forth. Say like this 0.1 microfarad capacitor here. This is a monolithic capacitor. It has no polarity, so it's not electrolytic. It's just a ceramic capacitor. Now, surely I can pick a very specific one, but what I really care about is the footprint of it, because I know that I can replace it with 100 or 1,000 different capacitors. So as you're doing your schematic design, we don't have to pick the exact part for many of our elements. We just have to pick a part that has the same footprint that we need, and then we can exchange it for something else. All right? So in other words, say like this 555 timer. This comes in maybe a surface mount component and a through-hole component. The through-hole components are always 8-pin, and the pitch is always 0.1 inch. So as long as I have an 8-pin version, which they all are, that's 0.1 inch pitch, I don't really care exactly what the exact part number is. It might be from Philips, it might be from TI, it might be from this or that inside of Circuit Maker, but I know I can replace it with something because that's replaceable. But other things are not replaceable, and I need a very specific component. So for example, you see here the AAA battery holder, right? The AAA battery holder, that's very specific because it's mechanical and I want it to look a certain way and have a certain size. So I can't just change that to something else. So I actually had to find that in DigiKey. Then I had to see if it was in Circuit Maker, and then vice versa. You know, maybe I checked in Circuit Maker, AAA battery holder, and then I saw what parts came up. I looked at them in DigiKey and I looked at their pricing. So what drives a design is the functional requirements and the cost. The cost. And when you're selecting parts that are specific parts, now remember, the generic parts we don't care so much about. If we have a 1K resistor, I can find a million 1K resistors from a million manufacturers. But if I'm putting a part in my design that's very specific and there's only one company that makes it, I need to make sure I can buy the thing. I need to make sure it's available. I need to make sure it's not going end of life. I need to make sure of a lot of things, and I need to make sure of its cost. So that's why you got to look on DigiKey, look on Mouser, look on Octopart, and make sure the part is available, make sure it's cheap, and if it's not, you have to pivot to another part. Okay, all right. So let's begin here. And why don't we just start, let's build this up from the power supply and move our way up. Okay, so this particular part right here, if I get this stupid thing off, so if I double click this, all right, what comes up is a bunch of information about the part. All right, the unique ID is not what I'm interested in. It's got an Octopart ID here, and then it's got this Keystone URL here in Octopart. So what I'm going to do is I'm going to copy that, all right, and there's the picture of it right there. I'm just going to cancel that. Now watch what I'm going to do here. I'm going to go here, and I'm going to open up Octopart. I can copy the URL in there. So there's the URL, I'm copying the URL. All right, and here's the part right here. So now over here in DigiKey, here's the SKU number in DigiKey. Now also let's take a look at these prices. So the prices from all these different manufacturers, we look at it for 10, use 100 or 1,000 as kind of your budgetary pricing. They're about 60 cents. About 60 cents for 1,000. Now I've already went through this and I like this part, but let's go through the process. So now I go into DigiKey, I put that number in here, and here it is here. So there's the actual part, and I look at it and I like it. That looks good. Now it's under battery holders. It's a AAA battery holder. It's got plastic around. It's got springs. It's a good part. It's Keystone Electronics. I'm familiar with this company. I like it. Now how we originally would go through and do this is we would say, okay, we want to search for a AAA battery holder. So you can see here, product index, battery products, this, that. There's all these different search trees that we could go under, but I'm just going to put in AAA battery holder. All right, so let's just start off from the beginning. All right, so I start off, and here we go. Battery holders and clips and contacts. Good. Okay, so great. I'm going through here, and now we want a AAA battery. Number of cells, just one cell. Now, how do we want to mount it? All right, chassis mount, custom, free hanging, PCB, surface, through hole. Yep, we went through hole. That's enough for now. Remember, with DigiKey, Mouser, and all these different search engines, if you select too many different search requirements at once, sometimes it won't return anything. So we'll apply the filters. All right, and now let's also make sure it's in stock. Okay. Okay, and now a number of these have come up. So let's hover over it. So I don't like that. That's out of the question. This is pretty good. That's not bad. This is a little bit better. Oh, that happens to be the Keystone one. That's why I like it. This one, don't like that. It's kind of ugly. That one's kind of cheap looking to me, even though it's a Keystone product, and it's probably, now what's interesting about this, it's actually a little bit more expensive. So maybe have some thicker metal. And here's another one by Keystone. But I like this one. All right, so this is the one I like. So I click on that. And this is the process we do. We actually search for it in here, and because we want to compare to other things. So now that I found this part, the question is now, can I find this part in Circuit Maker? So 2466 is the part number, right? So 2466 Keystone, all right? And then here's this DigiPart, DigiKey part number. Now the interesting thing about Circuit Maker is, so let's go back here. Now what we're going to do is we're going to go to our schematic, which has nothing in it. All right, so the first thing that we want to do is we want to place a part. Okay, so we're going to right click, and remember we can go here home, and we could just click component, and it would bring this up right here. Or we can right click and say place, and then there's all these things we can place. We're going to place a component, or we can press C. All those different things are the same. Now, we can look at our history, we can put this information in, but we're going to go to choose. Now, one thing here. When you're using this dialog, this is cloud connected, internet connected, and it doesn't update sometimes. And so you got to give it a minute to kind of find things. So first, I don't want to look in my favorites because I know it's there. I don't want to look in the project because it's not in there. I want to look in Octopart. Now, check this out. If we put this number 2466, we might be able to find the part. All right, and sure enough, it just came up right there, and this is it right here. Battery holder, AAA, and look at it, it's the exact same. But let's just try AAA battery holder. And if that's in the search term, all right, and then you can see there's all these different things here. So there's a 4 AA, and there's a 2 AAA, a 3 AAA battery holder, something or other, and go down here. So now, if we wanted to use Circuit Maker to find our battery holder, we might not find it if we don't put the right search term in. Like we put in just AAA, that's going to come up with a lot of different things. You're going to have AAA in the search term, like here an LDO, an LED, lots of different things. So you got to kind of go through here, all right? And we can see there's battery holders right here. So if we go here, there's one, there's another one, there's another one. There's another one. But again, I can't tell what their prices are. I can't see their availability unless I put it down on the board and start messing with it. That's why we want to work the other way. We want to kind of work from DigiKey sometimes or Mouser to find the part we like and then put it in here. And usually it'll cross-reference. Octopart will have it. But the question is there a symbol and is there a footprint? And see this footprint right here, if I click on it, I can actually move it around, and I can actually, if I press Shift and then holding down the right mouse button, I can rotate it in 3D to see it. Okay, so that's our part right there. See that 2466? That's what we want. All right, so I want that. I like that. That's good. Here it is, Keystone, and here's the footprint of it. Now that footprint is very specific. Someone made this footprint, and if this was a more generic part, it might work with other battery holders. All right, but we're just going to put it here. All right, so we're going to put one there. We're going to put one here. And we're going to put one here. All right, I'm going to press Escape, and that's going to get me off of that mode, and I'm going to zoom in a little bit. All right, so here are 3 battery holders. Okay, all right, so that's looking good right there. Now remember, the long side is positive and the short side is negative, right? So we'll go back to our source design here. So this is kind of what we're trying to make right here, right? We're trying to make this thing right here. Okay, so let's go back to this schematic. Okay, so we've got our battery holder. And so now, what about manipulating the symbols on here? So this is the symbol, and associated with this is a footprint, and that's for the printed circuit board. And that's what it's going to plug into or solder onto. That's the footprint. But also associated with it is a 3D model. The model is just for looks only, right? And that's when we go to this view, looking at the source material, and I press 3 and I get this 3D view here. That's what these things are. These are the models. But this thing down here on the PCB, that's the footprint, right? That's very important. So like on this resistor, the footprint is just these 2 pins. On this IC, the footprint are these pin holes here, and these are where the chip goes in, and then the 3D model is this thing here, and it doesn't have to be perfect. You can see, like, this is a really bad 3D model. This one right here, this one's a better one. This is more actually what a chip looks like. Okay, they look like these trapezoids. Okay, so but it's just for reference. It's just for looks, so you can see this kind of 3D rendition of things. Okay, all right. So let's go back here. Let's go back to our schematic here. Okay, so now if you want to move something, just click on it with the left button, hold it for a second, and it'll grab, and then you can drag it around. Okay. And we can do that. All right, if you ever get all mucked up, just start hitting Escape, and that'll kind of put you back in the neutral mode, and you'll be okay. All right, so now let's connect these wires here. So how do we connect wires? Well, we can press the right button, and we can say Place, and we can look through here, Wire, or we can press W. That's what I like to do. So I'm going to press the W on the keyboard, and now you can see, and I'm going to zoom in, I've got this little X, and so when I put it on top of the nodes of a component, you can see right now it's just kind of a black X, and when I put it on here, see it's a red X. Now click, and now see this wire starts going, and then I'll click here, and now I've got a wire. All right, let's move this over. Click here, good, click here, and I'm just going to click here, I'm going to click here, and then I'm going to right click to stop, and then I'm going to press Escape. That takes me out of that mode. All right, so look at that. So we're getting our battery pack here. So I'm going to put the 3 batteries in series to give us our 4.5 volts. Each is 1.5 volts. If it's an alkaline type battery, if it's lithium ion, it might be 1.6. If it's a nickel metal hydride, it might be 1.4. Roughly, the whole thing is going to add together to 4.5. Now, let's go ahead and change what the reference designator is. So if I click right on the reference designator, I can edit it, right? Now, if I click on the part symbol itself, it'll kind of give me the big dialog, and I can also mess with the designator, okay? Another thing is, if I just click on this, I'll get this. This is the string that describes whatever it is. That's just a text string, and I could edit that. All right. Another thing is, if I want to move these things, so say I want to drag this, just click it, hold it, and you can drag it. All right, so you might want to move these things around, all right? But let's change the reference designators. All right, so let's go ahead and make this BT1, like battery 1, make this BT2, make this BT3, okay, back out. All right, Control S, my fingers, every time I do something, Control S, Control S, Control S. All right, now, Keystone Electronics 2466, That's great, but let's shorten this up a little. Keystone 2466, and maybe we just say AAA, right? We know it's a AAA battery holder. That just helps us remind ourselves. And I'm going to click on that one, and I'm just going to copy and paste that same string in there. All right, and I'm doing it a little different than what I did on this one. Let's see here. See, I just called it AAA battery holder. I didn't say who made it in this version, but in this version, I'm changing my mind. That's all. No big deal. Okay, now we need a ground here, so we need to put a ground symbol. All right, so let's go up to home here and let's look at, we've got all these different things. Now, we don't want to draw a ground symbol. We need an actual electrical ground symbol so it's connected to the net ground, GND, ground. So let's look over here, component, wire, net label, bus, port, power port. That looks promising. Here they all are here. So these are all different symbols for power. So let's get this ground, and there it is. We got a ground. Now, many CAD tools, you can't really do this. So when I have this ground, if I just put it right on top of here, this tool is smart enough to realize here's one wire, here's another wire, and I'm going to connect it. What will happen in other CAD tools is you'll lay it on there, but it actually just lays it on there. It doesn't make the connection. So what you do is you put it here. Then you would take a wire. I just pressed W. I'm in wire mode. Then you would connect it, and now you would have a connection. So now when I drag this around, it's connected. Okay, but we're going to take advantage of this tool and this little feature that it has. So we're going to grab a ground right here, and I'm just going to connect it right there. All right, and I right-click to get out of whatever mode. Now if I grab it and select it and move it, see, it's connected. That's what we want. Okay, good. Okay, so Control S, let's save this. Okay, so we got our batteries here, we're doing good. Now we need a switch. Now this is a big topic. We talked about switches in the lectures. There's a gazillion switches, countless switches. What I really care about here is cost. Mechanical performance of the switch. Is the switch hardy? Can it take current, a lot of current? Can it take a high voltage, and so on and so forth? One manufacturer that I use a lot is called E-Switch. All right, so the first thing that I did was, again, remember the circuit maker is connected to Octopart. So it can find any part in Octopart, any part, but that doesn't mean there's a symbol, it doesn't mean there's a footprint, it doesn't mean there's a 3D model. So again, the first thing that I did was this. I went over here and I said place, and I said like component, right? And then I went here to choose, and I said, just give me a switch. I said E-switch, I think. I said E-switch because I know I like E-switches. All right. And then some of these switches started popping up here. So E-switch, E-switch, and I said to myself, okay, it looks like we've got a lot of models here, and see it's downloading. See, this one's got the symbol, it's got the footprint, but no 3D model. All right. Push-pull, single throw, we know what that is. Again, it's got the symbol, but here it's got no 3D model. No 3D model. You can't see a switch on this. All right. So anyway, so I'm like, okay, great. This has got E-switches. It's got a few of them. People have created symbols and models. Let's see if we can find something I like. All right. So then what I do is I go back and we go over here, and then we just say E-switch. Now we could look up switches, we could look up E-switches. Okay, now what do we want? Push button? No. Rocker switches? Maybe. Tactile toggle, dip switches, slide switches. Okay, so slide switches. All right, and then I start looking through these things right here, and I know what I want, and I know what I like for switches. So the first thing is, how many poles and all that, right? So we want something that is it double pole? Is it single throw? That kind of thing, right? And if you remember, like the poles are how many different contacts, and the throw is like how many different directions and all that, right? So we only need this thing to be on and off, okay? So if you look at, let's see here. So if you look at our design here, and we go back to our schematic, we selected this 1218 switch here, all right, this 1218 switch. And it was actually this first one right here. If I do a sort by price, all right, we do a sort by price, and we go bulk and cut tape, apply filters, and we go in stock, apply filters, and we say we want active, apply filters. Now, what do we need here? on, off, all these things right here. You can sort of use this, but this is more what we need here. So single pole, double throw. So single pole, double throw. So I want to be able to throw it in one direction, throw it in the other direction. That's the one that we want, that kind of switch. All right, and we can see this EG1218. Now we've got these other switches here. Now my other concern is how big is the switch, right? How big is it, right? So actuator length is 2 millimeter, 3 millimeter, 5 millimeter. There's some variance of it. And then I would go in here and look at the mechanicals. Now, if you look at these switches, these things kind of go through the printed circuit board. This one is for a panel mount. This one goes through the circuit board. This is kind of a micro switch. We could use that one if we wanted to. But this one's kind of a nice hardy switch. I've used this one before, this EG1218. This can handle 200 milliamps at 30 volts, so that'll do we're not going to use much more current than this. But if we were going to use much more current, then we got to kind of go down here to these 500 or 5 amp and these kind of bigger switches. But this switch will do. So this EG, this one right here, so that's what we're going to do, and it's actually a nice looking switch. So we'll click on it. We look at its prices. Down at 1,000, it's only 37 cents. I like that. Switches are very expensive. Mechanicals, especially switches, are very expensive. It's like they're made out of gold. All right. So we like that switch. So now the question is, can we find this in Circuit Maker? So Octopart definitely will always have it, right? So Octopart always has it. If we go to Octopart, which Circuit Maker is connected to, we type in the part, sure, of course, Octopart's got it. It shows you all these different things. But the question is, does Circuit Maker have a footprint, model, and symbol for it? That is what we need to know. So we right click, we're going to say place, we're going to say component, or we could have pressed C, or we could have clicked it up here with component. Now we're going to go to choose. Now I'm going to type in this EG1218. All right, and we see what comes through here. So only one thing popped up, and then these are all the revisions. So as someone has worked on this, they've made multiple revisions. All right, so here's the switch right here. So there's actually a 3D model of it also. So if I click this, and there it is. So you can see it right there. So that's nice, right? It's shaded a little bit funny. So we want this. So this is perfect. So we'll hit OK. Okay, we'll hit OK there. Now we'll put the switch like this. Now, I'm just going to click it down there for a second. So when the switch is in the upper position, this path is connected. When it's in the lower position, this path is connected. We can put the switch either way that we want, all right? Doesn't really matter. But let's see what we did over here. Yeah, so we did it like that. We did it in the kind of that direction. So we'll just kind of do roughly the same thing. Remember, we don't need to copy this, but it's not going to hurt. So now I could connect it like that, but let's just leave it out there. Let's hit W for wire mode. Let's add a wire, okay? Now, let's add another wire here, and we're going to put this up here. This is going to be our V sub CC. This is our power to our system. So now we need another power port. So we're going to go up here in Home. Remember, you can click through these View, Tools, Outputs, all these different things here. But in Home, contextually, this is kind of what we want. And we're going to go to Power Port here. Now, there's different versions of this, +5, bar style, wave style, all this kind of stuff. In our case, we're just going to call the signal V sub CC. All right, we're just going to call it V sub CC. And then again, it depends on what style you want this. Now, I prefer the arrow style here for power, all right? But this bar style is also cool. You know, whichever one you want to use, just be consistent, all right? So we'll use this arrow style. Oops, I don't want to do that. And if you look back here, I use the bar style here. So let's use the bar style. So I thought I used the arrow style. And we're going to go V sub CC here. So there's our V sub CC, and I'm just going to connect it right there. Okay, now Control S, I'm saving again. If I move this around, it's definitely connected. Now what I'm going to do is we built this up in this corner, which is fine, but I want to move it a little bit. So just like anything, just rubber band it. All right, and to rubber band it, use the left mouse button, and it creates a rubber band. Now I've selected the whole thing, and just grab anywhere and just move it a little bit. Be careful. If you grab and let go and grab again, you might grab a subcomponent and drag it. If you do, just Control Z like you normally would undo, and everything will be okay. Okay? All right. What's next? All right, so we got our switch. Now let's go label our switch. So we're going to double click this, and we're going to make that switch 1. All right, and Control S. All right, so everything's looking good. Now, one thing I'm going to add here is a capacitor. Now, the reason why I'm going to add a capacitor to this is once we turn this power on and this thing is powered up, V sub CC is going to be powered by these batteries. As we access these batteries, the voltage on the batteries is going to change as the current gets dragged from them. All right, because each one has an internal impedance. So how we can smooth that out a little bit is we can put a capacitor on this side, and when we want charge, it'll pull it from the capacitor first, then get it from the batteries, because the capacitor will be lower impedance. So we'll put a capacitor here, a big capacitor, like a electrolytic, and that will smooth this out a little bit and put a little less load on the battery, all right? And it'll keep the voltage a little bit more stable so it's not fluctuating. All right, so we need a electrolytic capacitor. There are about 1 billion of them, and there's all kinds of different classes of them for different uses, for filtering, for general capacitors, automotive, this, that. There's many, 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 many. What we really care about is the footprint. So we're going to put a through-hole capacitor. We want the holes to be separated by a certain amount of distance, whether it's 0.1 inch or 0.2 inches or 0.3 inches, and then we can just put any electrolytic later that we might decide to put in there. But first we care about the footprint. All right, knowing that, let's go back to our original here. And you can see here's the capacitor right here, and I'm just saying it's 47 microfarad. It might be 47, it might be 100, it might be something different, but I just put 47. That's a good number to filter this. Now, if we look at this capacitor right here, one thing you'll notice is it's polarized. There's a plus, so this is a polarized electrolytic capacitor. And then if we double click it here, it's this capacitor right here. Here's a DigiKey URL, here's the Octopart URL, all right? And then here's the part number right here. Okay, and then here is the 3D view of it, and let me see if I can zoom out, give me a second here, get this to cooperate with me, and I'm not sure what I did, but anyway, that's what it looks like. Okay, so this is good. And then size and diameter, this particular one is 4 millimeter, but what I really care about is the pitch. And see this 4 by 7 by 2.5. So this is a 4 millimeter diameter, 7 millimeter height, and 2.5 millimeter pitch. 2.5 millimeter is 2.54 is 0.1 inch. So this is a 0.1 inch pitch capacitor. Many capacitors will fit into that size. So that's what I wanted. So what I really did was I went and found a capacitor that kind of, is something that I might use, but more that I cared about, did I have a model, a symbol, and a footprint for it. So here's the part number right here. So I'm just going to take that at this part here on this one. Now what I'm going to do is I'm going to go to DigiKey. Where did DigiKey go? I'm going to put this part number right in DigiKey. And here it is right here. Here's our capacitor. And again, we can use any electrolytic capacitor that's roughly the same size and all that. All I needed to do was find any capacitor that has a footprint that I like, then later I can change it, because this is a generic passive component. It can be replaced. But I like the price also. This particular one is not a bad capacitor. So at 1,000, it's only 5 cents a piece. So we look at it. It's this particular one is 10 microfarad. Doesn't matter what it is, right? Plus minus 20%, 16 volt rating, so that would all work. General purpose. It talks about some other things here, and then here's what we care about here. Is the lead spacing is 2.5 millimeter. It's almost 0.01 inch, right? 0.098. Okay. So now we could find an actual 47, but at this point I don't really care. 10 is fine, and I could look at this part number here and I could probably engineer a 47 microfarad, right? So there's the 10.0 microfarad encoded there, I would imagine. So if I take this and I go like this and I put 47 there, I bet, if I'm lucky, there it is. There's the 47. So this is an actual 47 microfarad. The size and the shape is all the same. So you can see it's 7 tall. This one is got a 6.3 millimeter, so this one's a little bit bigger, and then the pitch here is 2.5. So why don't we just use this one? Let's see if this one's inside of and we can try using the actual part number. All right, so let's see if Circuit Maker has this one. So let's go back to our design here, and let's do place component. And we want to choose, and we're going to go here. We're going to put the actual part number, and it may not be able to find it. Uh-oh, didn't find it, because no one made a model of this one. All right, so let's go back here. Let's put the DigiKey part number All right, let's see if we can find it with that. I'm not going to give up until I look for that. Nope, can't find that either. Okay, I'm going to go like that. Can't find that either. So see, can't find it. So that means that it may not even be an octopart. We'll go to octopart and look. All right, here it is in octopart, and sure enough, it can find it in an octopart. So that doesn't mean that Circuit Maker can find it. So again, this is why there's this little bit of a disconnect. So let's go back and let's just go back to the 10 microfarad version. So go back to DigiKey here, and we'll go here, and we will make this 10. All right, and the 10 does exist. Here it is here. Now I'm going to go ahead and get this part number. All right, go back here, and now let's try and see if we can find this part number. Ah, there it is. And someone's made a nice model for us. All right, there's a 3D model, and the footprint is right there, and then there's a symbol. So we're just going to use this. All right, and then later we're going to put maybe a larger capacitor. Okay, now what's going on here? So the capacitors in this orientation, I don't like this. So what you can do, and then this is a little bit tricky, but if you have the object selected and you're holding on to it, if you hit the space bar, it'll rotate around that pivot point. So, oops, it just teleported. All right, so there it is. And sometimes you got to be careful. All right, and then now I'm going to connect it right here. See the little red on the screen there where it's making that nodal connection? And then I'll press escape, And now I'm going to drag, I'm going to be careful. I'm going to drag, still careful, drag the component. All right, so in this case, it's kind of made this node here that I really don't like. So I'm going to delete that. And what I'm going to do is I'm going to go place that component again. And this is the same one. All right, we're going to rotate it. I'm going to put it right here. Now I'm going to go into wire mode, escape, press W, wire mode. All right, press escape. Now I can grab this and drag it a little bit. Now, as far as reference designators, you can just leave them all blank and then kind of do them as you go, or you can kind of do them in sections too. So in this case right here, I'm just going to call this C1. It's probably going to be different than the other design. And this says cap polarized 2. I'm going to change that to what it actually is. So in our case, I want to make this like 47 microfarad. All right, or we could say, hey, make it 22 to 47. Your discretion. All right, we could say that too. All right, and that's that. And then this also needs a ground, so let's go to ground, and we're just going to copy and paste. So we're going to press Control C. All right, now, yeah, and this is a little bit tricky too. So you got to. I'm still not quite sure the behavior of this, but once I do Control C, if I do Control V, you got to stay close to the object because the more you move away from it, it creates a local origin, and then it copies it away from the object. So anyway, now I'm just pushing against the screen here, and then I'm going to connect it there. Okay. There we go, so looks good. Let's save that. Now another thing you might want to do, something I do is I'll pull this up a little bit. Now you see this ground and this ground? I kind of like things on the same level, right? So we could drag this down a little bit and then we can level it out and see, yeah, they're about on the same level. So that's nice. Control S, make it neat. Doesn't hurt to make things neat. Now I want some text describing this. So what did I call this over here? What did I call this over here in the source? I called it battery power 4.5 volts. All right, battery power 4.5 volts. So I could just take that and copy it, all right, that text, and I can come here and I could place it, right? I could do that, but let's say we don't have it. Well, how do you do that? Well, it's not a circuit element, it's a graphical element. So we'll go to text string and I'll put it right here, all right? And then I'll zoom in and I'll double click this, all right? And then we're gonna say this is battery power approximately 4.5 volts DC. Let's add DC to this one. And let's make this a little bit bigger. This is new times Roman 10. And remember, clicking on anything with this cloud-connected software causes it to do things. So we'll give it a minute here to do whatever it needs to do. It's probably downloading a font list and some things like that, and who knows. All right. I don't know what size to make it yet, but I'll start with 22. I'm not too happy about this navy color. So let's start with 22. All right, let's go to this one right here, and let's see about this. So if I double click this, this is a Times Roman 14 bold, and it's still in navy color. All right, so we'll go over here, and this one, we got this at 22. So we'll use the same font size, 14. Where to go? 14, and then we'll make it bold. All right, we'll hit OK. Okay, and then I'm just grabbing it and dragging it, and there we go. And that's it, Control S. We have our power supply. All right, so that is our power supply right there, our battery power supply. When the switch is in this position, it'll be on. When it's in this position, it'll be off. When you turn the batteries on, what's going to happen is it's going to first charge into this capacitor, and then this capacitor will then become the charge source. And then when current is needed, the charge will come from this capacitor first, and then it'll come from the battery. So what's nice about this is it'll smooth out the ripple a little bit as current is drawn from these batteries, and the internal impedance of these batteries affects the voltage. So this is a little bit smoother design than just having the batteries directly connected to V sub CC. Okay, now let's see. How much time do we have here? I want to go a little bit farther. I want to kind of do this in chunks. So let's go back to our original schematic here. Now I think I have, do I have a power LED here someplace? And I'm wondering, do I have a power? No, I don't. So when you turn the thing on, these LEDs all just work. So there's no power LED here to show you that power's on. All right, but there is this magic wand. So I'm gonna copy this. So I'm gonna copy this, and I'm gonna copy it in here. I'm gonna cheat a little bit, and I'm just gonna put this right here. Okay, just to put that in there. All right, so we've got our power supply, and now that the power supply is here, I can see I can move it a little bit. So I'll just move it up here. That's good. We'll just leave this magic wand there. I'm just going to drag that. Okay, so we got our power supply. We're good to go. Let's go ahead and commit our design here to make sure it's up there, wherever up there is. All right, so that's all good. Now notice we haven't messed around with the printed circuit board at all. We're still in schematic design mode here. We've got a lot of work to do. So we're not worrying about that right now. We're just worrying about this. All right, so we'll go to our source material here. We'll see. So this is, we're getting there. Now you can already notice one thing is switch 1, BT1, BT2, BT3, but this is C4. And the reason why it's C4 is I probably, what I did was, in this case, I might have designed the whole thing, and then I went back and designed the power supply, and by the time I got to this capacitor, it was like the fourth capacitor. See, there's one there, there's one there, there's a 5 and 6, and then there's probably a C3 here. See that? And this ended up being C4. So it doesn't really matter. They're just reference designators, all right? So let's go back here. Oops, let's go back to our schematic of our Magic Wand final design. So that's it. So we're ready to move on to the next piece. Okay, so we're going to cut the video here and we'll start back up in a second. So let's go to the schematic. So the next thing we're going to do is let's go ahead and deal with a 555 timer. All right, that's kind of a biggie, and that's the heart literally of the entire system, and everything, the signal flows from the 555 timer. So I'm not going to start with the LED driver down here. I could if I wanted to. Hardware doesn't care which order you go in. But first let's get the clock, then let's get the counter, then let's get the LED driver, and that's how we're going to do this. Okay? All right, so let's go ahead and stop here, and I will meet you in the next video. Get it back up on the screen here. So last time we left off, we were inside of Circuit Maker, and we just had finished putting together the battery section of our original design here. All right, so we'll go here to our Magic Wand Final, and this is what we have so far. So we've just done the battery, so we've got 3 of these 1.5 volt AAA batteries together with a switch, with a capacitor that's used as a bulk capacitor for charge storage. All right, and then that goes and connects to V sub CC, which is just an abstract net right now. It's a net name, V sub CC. The tool knows its power, but there's no voltage assigned to it or anything like that because there's no simulation really, so it doesn't really matter. So it's just text as far as the tool is concerned. We could put any text we want there. But anyway, it's V sub CC. All right, so to refresh your memory here, we had the Crash Course Electronics Magic Wand working copy, which we made a forked copy of my original, and you should also. And we're not touching that, we're just using it as a reference. So it's got the 2 files there, the schematic and the PCB. So here's the original schematic that we're trying to copy. All right, so let's just dive right back in and just keep this going. So the next thing that I want to deal with is the 555 timer. All right, so we're going to use this as the heartbeat of the system to create a clock signal. All right, now there's a million ways we could create a clock signal. We could use an IC that's programmable. We could use a microcontroller. We could use a transistor oscillator, a FET oscillator, you know, it goes on and on. But a 555 is a real simple way to do it in kind of a classic hello world way of doing it. All right, so we've gone over the 555 before. What we are doing in this design is using through-hole components only, no surface mount. So we know we need a 555 timer, and the question is, what package does it come in? If you recall, it comes in a DIP package, a dual inline package. It also comes in an SOIC. You can probably find it in a TSOP as well, but we're going to use the DIP package, which is a standard package. So we know that, and we can look at this part right here if I double click on it, and we can look here at the Octopart link for this particular one. Now remember, all we really care about when we're doing the schematic design, when we're dealing with generic components, we don't really care about what the component's part number is specifically or the manufacturer. We just need some part that has the proper footprint, because we may change the part. For example, if we have a 555 timer, there's many companies that make 555 timers, right? And we don't have to use one, you know, from Texas Instruments or Philips or NXP or whomever. We can use whichever one we want because they're all the same. It's kind of a generic TTL part or generic part. What we do care about is that the footprint is correct so that we can put our own part in there. So again, I've discussed this. As we're designing, some of these parts are fairly generic, like the capacitors. I don't want the exact part number here. You see all these part numbers here? So when I put this capacitor down, this tool wants to put a specific part number and use that. That's fine. But the part number may be for a 1 microfarad capacitor. And every time I could put a capacitor down, I don't want to keep getting a different part to change what the value of the capacitor is. I just want it to have the same footprint, because I know that ceramic monolithic capacitors come in pin pitch when they're through hole of 0.1 inch or 0.2 inches. So if I just make everything 0.1 inch pitch and use that same footprint, I know I can find 1,000 different values of that same geometry, so that I can put it in the circuit and change the component. So in other words, we care about the footprints. We don't so much care about the exact part number unless we do care about the exact part number. If we're using a very unique IC or part that there's only one of, then we want to have the right part number and we want to have the right footprint. Okay, so that said, let's go and let's search for a 555 timer chip. All right, so there's a couple ways we can do this. Now remember, I told you when you're looking for parts, I don't necessarily want you using the tool Circuit Maker to find parts for you. I want you to go search for parts in DigiKey or Mouser and see what's available, see if they are available, look at their price and so forth, so that you can kind of get an idea of what you might actually use in your final bill of materials. All right. Then once you have that part number, see if Circuit Maker has it. If it does, great, just use it and you're done. If it doesn't, then what you want to do is say, well, what does Circuit Maker have that has the same footprint as the part that I want to use, and I'll just use that part for now, knowing that I'm going to change what the actual part number is. All right, if that makes sense. Hopefully you're not getting too confused. So let's go over here back to DigiKey, and we're going to just type in our LM555 timer. That's the timer identifier, their part number, and clock and timing programmable timers and oscillators. All right, so first let's look for active. All right, let's look for in stock. Okay, and we might as well put RoHS compliant. We'll hit apply here, and let's just get things in cut tape or a tube. Doesn't really matter. Now look here, here's all our different packages that we have. All right, mounting types, so we want through hole. And when we do that, we're only left with dip or PDIP, which are both probably the same thing. PDIP means plastic dip, but this other manufacturer just may call it a dip. All right, and then there's two companies that are showing up, Texas Instruments and Fairchild. All right, and if we go on Texas Instruments here, it shows 0, probably because it's not in stock. So we'll just click on the Fairchild here, apply filter again, and we only have one IC. So again, you can see it. It's a through hole. It's a dip package, standard dip package. So this is what we want. And then we look at its voltage. It's 4.5 volts to 16 volts. All right, 4.5 volts to 16 volts. Now, that'll work fine. Now, what we might even like is a version of this that can operate at even a lower voltage as our batteries start dying out, right? We want this thing to continue operating, all right? So that's one thing to pay attention to. So now, if we go to the design here, you can see this says LMC 555. Let me show you that. LMC. That C stands for CMOS, kind of a CMOS version of it. So if we pick this version, and again, it doesn't really matter because all I care about is the DIP package, all right? But if I can use the part, and if Circuit Maker has the exact part, I might as well use it. But if it doesn't, I don't really care. All I'm doing right here is searching. Now, when I did this, I realized this needs a minimum of 4.5. That's a little bit high because that's kind of what our voltage is going to be, right, with our batteries. So let's see, can we find something else? If we look at LMC 555s, that is the CMOS version. All right, now we go here, integrated circuits, and again, we'll do our same thing. Let's make sure it's active. We'll pick cut tape and tube. We'll put in stock. Let's lay off the RoHS restriction against hazardous materials and substances for now, and we want it to be through hole. All right, and again, only one comes up, but look here, it's got a C in there. Now when we go look at the voltage, look at that. Voltage supply, it'll work from 1.5 to 15. So what do we know? As designers, we know we probably want to use the LMC version of the 555, but the package is the same, so we don't really care either way, right? What part number we use in the circuit maker, right? We just want to make sure that it has the right package. If the part number is correct, then wonderful. So now let's see, can we actually find this part number? So let's forget about this NOPB thing. Well, we can take that. It's probably not going to hurt it. Now let's go to Circuit Maker. Let's go to our design, which is this one right here. And now let's go turn on so you can see what's going on here with the keyboard and mouse. So bear with me here. Okay, so I've got the QI press working so we can see when I press something here like control, you'll see it over here so you can keep an eye on my keystrokes. All right, so remember we want to place a component. So up here in the main menu, we can go to all these different tabs here. And the one that we want is we can sit at home and we could click component if we want. We can do that. And that'll work, and that brings up the place component. Or we can press C, that'll work. Or we can right click and then hit place and then go to component. Lots of ways to do it. Okay, so now let's go to choose. All right, so now let's get out of favorites. Let's go to Octopart, and we're going to put in that part number. And we are going to see if it finds it. And sure enough, a couple of these have popped up. So now what I'm going to do is, there's the exact one we're looking for, that NOPB. All right, and then if I go here, it shows that also. So let's just, since that's the one that's in DigiKey and that's the one that we want, let's go ahead and pick this. And then here is the footprint right here. Let's take a look at that. Is that what we want? Yep, and that's a 3D model of a DIP package. So this is what we want, so let's go ahead and hit OK. Alrighty, and we're just going to pop this right down right about here. All right, and then I right click or hit escape to get out of that mode of placing. Okay, so we're good to go. All right, so now let's go ahead and let's design this up. So let's take a look at the schematic here. All right, and in this design we've got V sub CC. We're gonna have to, we can copy this from here or we can copy it from the data sheet. Just hold on a minute, we'll take a look at that. But we've got C5, C6. I'm not going to worry about making these reference designators the same. We're just going to make them how we make them. But in the design, we also have a bypass capacitor here, and we're using 2 potentiometers. All right, so keep that in mind. All right, let's go back here. Now let's go to the data sheet for this. So I clicked on data sheet. Let me make that a little bit bigger. All right, so now LMC, CMOS version of the 555, and this will also go up to 3 megahertz, I believe. Yeah, 3 megahertz, which is nice. Industry's fastest, so you can actually, do some pretty high frequencies with this and do some RF stuff if you wanted to. You could generate AM radio frequencies at least. All right, and what we're looking for is the A-stable or astable version of the circuit. So let's go find the pinout of that. All right, and we can just type in A-stable, and there's a typo, and monostable, A-stable, and I think, yeah, that's about it. Variable duty cycle, And let's see, pulse width, I don't want that. Yeah, so the one we want, let's go back here, astable operation. So this little schematic right here is showing the astable operation. Let's make that a little bit bigger. So all we need is this. So we need one resistor here, RA, one here, RB, between V plus discharge and threshold. And then threshold is fed back to the trigger, and that self-triggers it. The output is here, all right, on output. And I don't like that it doesn't show the pin numbers. Then reset is sitting here, and this is a reset low, all right, so we don't want to reset this. We don't need to worry about that. And then we have a capacitor C, which we can make anything we want. All right, so we have RA, RB, and RC. And we've talked all about this. I don't want to go into this too deeply. The equations, the modeling equations are right here. For T1, T2, and then that would be the total time, and then you could, that creates the period for the high and the low, and then the frequency is 1 over T, and then the duty cycle is this. All right, simple as that. So those are the modeling equations. So the bottom line is we're going to pick some values for the resistor and the capacitor so that we can change it. And how we're going to do that, we go back here, we're going to use potentiometers, and we're just going to say, if you do the math and you set the potentiometers at about 100K, and you set the capacitor at about 1 to 10 microfarads, that's going to give you hertz. So when you change these resistors, if you plug these values of 100K, 100K, and 1 to 10 microfarad, you're going to get hertz. All right. And so that's what we want. We don't want this thing at kilohertz or megahertz. We want it at hertz so we can see it, because it's going to go clock, 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 clock. And as it does, it's going to cause that LED to move and the counter to count and all that. So we want it to be really slow. So we need a really big delay. So we need bigger values. All right. So we can, and then again, this is how you got to do this. So here is the data sheet. This is what we have to go off. So we got to sit here and connect this thing up based on this data sheet, right? We got to read the data sheet and do that, all right, which I've done, and I've kind of copied it here. So why don't we just copy things here a little bit, some of the schematic, since it's just derived from the data sheet. Okay, so first, let's do ground and power. So V sub plus here is to V sub CC and a bypass capacitor, and then ground goes to ground. That's easy enough, so let's do it. All right, so let's go select that. We'll press Control C and then Control V, copy. So I've copied it. All right, I'm going to press W for wire mode. There we go. And now I'm just drawing a wire. And let's zoom in a little. Control and the mouse wheel makes it a little bit bigger. Okay, looking good. Let's go get that ground. I select it, Control copy, Control V. All right, and where is ground? There's ground right there. So we're going to put it down here. W again. All right. Good enough. Okay. And then 2 should go to pin 6, if I recall. So I'm going to just wrap it around like this. 2 should go to pin 6 from my childhood memory of this IC. And if we look, that's trigger to threshold, trigger to threshold. That's correct. All right. Here's our output right here. So I'm just W again. I'm just gonna set it right there for now. Just kind of set it out there. Reset is active low, so we kind of want to pull that high, right? So let's go to the final design here, and where is that reset? So if you look at reset, I've got it pulled high, because we're never going to reset the thing. We just want it to run, all right? So we're just going to go, and we're going to take reset here, and why don't we bring it out right there, a little bit higher. Good. Okay, right click to get out of the wire mode. Control S, let's save this. Okay. Now I'm using the right mouse button and right mouse button and grabbing the document to drag it around and pan it around. Okay, looks good. Okay, what else do we need here? Let's see here. Now we need some capacitors. We need to deal with that situation, and with these potentiometers. Okay, so the capacitors. Here's the deal. When you're doing through-hole design, you're going to either use kind of large electrolytic capacitors, and typically their lead spacing, the spacing between the leads, will be 0.1 inch, 0.2 inch, 0.3, 0.4, 0.5, so usually multiples of 0.1 inch. All right, so now from my experience, I know that I can get like 100 microfarad, 220 microfarad, even a 470 microfarad with lead spacing that's very small, like 0.2 inches. In other words, the capacitor won't be that large. So I know that if I make my electrolytic capacitor lead spacing maybe 0.1 or 0.2 or 0.3 inches, I can probably facilitate values up to 100 or a couple hundred microfarads in an electrolytic capacitor package. Good. Now, for my monolithic or my non-polarized ceramic capacitors, which I'm going to use small values, 0.1, 0.01, 0.001, or picofarads and so forth, I know that a common leaded package size is going to have a 0.1 inch spacing, like this. Let me get one. So here, and I don't know if that's going to focus, so those are 0.1 inch, and so are these. All right, and these happen to be actually 0.1 microfarad capacitors. So these are, I put these everywhere. So this style and this kind of size you can find from picofarads up to maybe 10 farads, 10 microfarads. All right. So that's what we're going to use for all our monolithic capacitors. So we just want something that has a footprint that's got a 0.1 inch spacing. That's all we care about. So again, now if you go to DigiKey, and you go to DigiKey here, and let's go back to DigiKey. And if we say 0.1 microfarad mono, okay, we'll start with that. And we want ceramic capacitor. Okay, and then what tolerance do you want? Again, there's a lot of parameters here. There's all kinds of stuff, all right? So the first thing, let's kind of think through this. So first, I want it to be active. Next, let's make it in stock. Next, let's make it RoHS compliant. Okay, let's hit the filters here. Next, what do we want the voltage rating to be? What's the highest voltage we're going to have to deal with? Well, the smaller the capacitor, right? The smaller the capacitor, the higher the voltage you can get kind of for free. It's very easy to get higher voltages. The larger the capacitor, getting higher voltages is more expensive. So typically with these monolithic capacitors, I'm going to pick 25 to 50 volts in that range right there. That's pretty cheap, and you should be able to get that. So let's apply filters. No problem. Okay, next. Let's see. We want them in bulk and cut tape because I want their single prices. I don't want all this these other things here because I'm just trying to price. Next, I look down here and I can see I'm getting a lot of surface mount. Let's get rid of that and let's just put that through hole over here. So I did that. Let me apply that filter. And what's happening now is there's probably more than 22 results, but again, with DigiKey Mouser, the order that you do this search engine actually changes what you search. It's a bug. It's just the way that it works. So if you do things in a different order, you get more results even though you have the exact same search criteria. All right, giving up trying to understand it. Now, here's the height. I don't care so much about the height right now, but I care about the lead spacing. This is 2.5 millimeter and 5 millimeter. 2.54 millimeter is 0.1 inch and 5 millimeter is about 0.2 inches. So we want the 2.5. We're going to hit that again with apply filter. Now we're left with not much here, except we're left with these two things, these temperature coefficients. We've talked about this, remember? And this is how the capacitance changes as a function of temperature and all that kind of thing. And different values are more expensive and better, right? So like out of these two values, the X7R is slightly better than the Y5V, all right? And you got to look these up on Wikipedia or something. All right, so now we can see that we've got a few different things left here. We're just going to leave them be, and then we're going to look down here at what we have, and I'm going to sort by price because I'm always trying to do things cheap. All right, and then you can see there's a little yellow version. I literally just showed you something like that. And then here's like a little blue version, which I literally just showed you something like that. Now, at this point, we don't really care. We just need a part number that we can potentially use in Circuit Maker that we might ultimately want to buy. Now look at some of the price deviance here. There's a 41 cent down here. So now here's the problem. If you just went into Circuit Maker and said, give me a 0.1 microfarad capacitor, blah, 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 it might only be able to find this 41 cent one. And you would just blindly go use that. Okay, I'll just use that. That's why we do this in DigiKey or Mouser. I don't want to use the 41 cent one. I want to use down here at this 19 cent one, right? And I look at some of their parameters and I say, well, I know that X7R is a little bit better. Look at this, it's 10% tolerance. It's 50 volts. It's from minus 55 to 125. This is pretty awesome, right? Who makes this? Vishay. And here's the part number. So it's 20 cents. It's like the cheapest one that they have, right? So I want to use this one. So we're going to try and use this one. So let's click on it. So here's the component right here. So this is the actual component I want to use. Now, remember, All I'm trying to do at this point is do some searching for my bill of materials. At the same time, I'm trying to find parts that I have actual footprints for in the schematic tool, because I have to have a footprint for everything in a symbol. But even though that this is 0.1 microfarad, I'm sure that this company makes a 0.01 and a 0.001 and a 1 microfarad and so forth that'll fit in the same footprint. So I don't need to keep finding new parts at this point. I just want to find one part, and then I will change what the value is in the schematic, knowing that later I'm going to have to actually find the exact real part number when I create a bill of material. Now, of course, you could do this as you design your schematic. You could be that detailed, and you could find every little part and this and that. There's nothing wrong with doing that. But I find that that's a very slow process, and you make so many mistakes, you have to redo everything. I like doing it all at the end. Anyway, so let's go here and let's grab this part number. So I've got it. And now let's go back to Circuit Maker, which is not responding. Oh, there it is for some reason. Okay, so now we know that we need a capacitor off of pin 5, and this is just an extra capacitor. You don't really need it, but we're going to put it there anyway, and a bypass, and they're both going to be 0.1 microfarad. So let's go here, back to our design. Okay, here's our design. Now let's place the component. What do? Press C. Let's go to choose. Now we're looking on Octopart. Octopart will be able to find the part, but remember, that doesn't mean that there's a footprint, a symbol, and all that, right? So here we go. It actually is here, and there is a footprint for it, and there's no 3D model though. So there's no 3D model of it. So it's just going to look like 2 pins. So whatever, but we can use it. So let's go ahead. Okay. And now we're going to, okay, now look at the capacitor. It's not in the orientation that we want, but if I press space, see how that flips it around, start rotating it around, so we can kind of get what we want here. All right, so let's see, I don't know, we could put that there, and we're going to need another capacitor. Okay, so now we've got these capacitors. Let's take this one and rotate this one too. Okay, so this one is our bypass capacitor. Let's press W to go into wire mode. All right, so that's that. Let's stay in wire mode here. Good. All right, let's hold on. Remember, you just grab it and you can drag it. Okay, now what do we have? We have, this is C1, so let's go ahead and let's just name this C2. We're going to name this C3, and this one we'll name C4. Okay, now they just say cap. Well, it's not cap. The value is 0.1 microfarad. Now, the problem is, if I go into the component, got to be careful of this, and if I go and look at the link for it, which, why is it not showing the link in this case? So in this case, it's not showing the link. Oh, here it is, Octopart ID. So this ID is for that specific part from that specific manufacturer, which we don't care. And see right here, it's saying 100 nanofarad. That is 0.1 microfarad, right? And so we're just going to leave this description, but we're going to change what the value is. Here's 0.1, right? Maybe I'm going to make this one 10. And I'm not going to go in to the part every time and change this description. This was the original part, and you got to keep this in mind. It's the original part, all right? So anyway, this one right here, I'm going to make this one 0.1 also. In the comment, that's the comment, it says cap, 0.1 microfarad, all right? And okay, now this is an interesting thing. Sometimes this doesn't update, so let's go on cap, and we'll put 0.1 microfarad. Okay, now this this guy right here, the C3, is going to end up being this capacitor right here. So this is going to go from 6 to ground at some point, but we want to have these two potentiometers here. So from 8 to 7, and then from 7 to 6, we have two potentiometers, and then from that point, we go down here to ground. So we got to be careful. So 6 basically goes through a capacitor that's 1 to 10 microfarad to ground. So let's actually put that one in right now. Okay, so that's going to be here, and I'm just going to put it right here, W, to get into wire mode. So off of 6, I'm going to put that there. Okay, and then now let's go back to the cap here and we'll say 1 to 10 microfarad. So there's no such thing as a capacitor that's 1 to 10 microfarad. That's a note to me. Make that 1 to 10. So when I get to the final bill of materials and I'm drilling down, then I can change that and make that perfect. Let's get some grounds in here. So I go select ground, copy, Control C, Control V. All right, there's one there, another copy, there's one there, there's one there, and let's go to W mode and continue the wires. Now remember, we can also just drag it. And if we once we see the little X, all right, and you know, sometimes again, remember I told you I'm not sure sometimes if it's made a connection, so I like making a wire there, okay, and then I can always drag it up a little bit if I want it to be prettier. Okay, Control S. Okay, so now we're getting there. So we got threshold, so we got our control capacitor, which is a C3 here. All right, and that is coming off of pin 6, which is also feeding back. Let's look at this schematic and just make sure we're not being crazy here. Where is the schematic? There it is right there. And you can see there's that threshold. It goes through the capacitor. So now all we need now is from V plus, we need one potentiometer, RA, and then that goes to discharge. And then from that point, we need another one, RB to C. Now, so now we're in this whole potentiometer situation. A lot of different potentiometers, a lot of different styles. Again, we want it to be through hole. We don't want it to be jankety, so it's cheap, but we don't want it to be like gold plated and super expensive because it's a very complex little mechanical device and they can get real expensive. So we want to find a happy medium. There's a couple companies that make potentiometers that I like. One is Sullins, I believe. Another one is Bourns. Another one is maybe TE Connectivity. So I kind of know some things that I like. So first, we know that we want it to be 100K. That's just a general value. 100K, so that'll give us 0 to 100K. That'll allow us to manipulate the frequency enough in RA and RB because we can't change C. That's fixed. This is the C down here in the formula. Okay, so let's go to DigiKey and let's look around. Well, you know, what do we see here? What do we see? So we're going to say 100K pot, and I might have to type potentiometer, which is not that easy to spell. All right, here we go. So we got rotary potentiometers, rheostats, joysticks, slide a lot of potentiometers here. Data acquisition, digital potentiometers. We don't want that. Thumb wheel potentiometers. So again, we're not quite sure which one we want here. I actually want to see all of these things. All right, so let's go rotary, trimmer. Let's do trimmer because it's got the most hits, 856 hits. All right, so now we look down here. Now let me tell you what we're dealing with here. So these are kind of what we want. These are kind of looking good. There's a lot of them. So first, let's go here and let's select active, in stock. I'm going to put RoHS, which is really going to bind it. I'm going to say I want 100K. The search engine came back with 10 and 20K. Don't know what I was thinking there. All right, next I want bulk cut tape, and tube is fine. All right, next, how do I want it mounted? I don't want it chassis, I don't want it panel, I want it through hole. Simple through hole. Panel mount through hole might also work, but we'll just stick to through hole. Okay, number of turns. Now this is very important. This controls your accuracy, right? One turn is not very accurate for 100K. That means from 0 to 360 degrees, each degree is 100K divided by 360, which is, let's figure it out. So 100 x3 divided by 360 equals 277 ohms. So that means every little degree is like 300 ohms, not very accurate. So we would like something that maybe has 4 turns or 12 turns. The more turns, the more expensive. So for now, we're not going to get greedy. Let's just say 1 and 4 and 12, all right, which I doubt we're going to find that cheap. All right, we'll apply filters. Okay, now let's take a look and see what we have. Now I can kind of scroll through here and I can see what I like, right? I hate these things. I hate these things. This is cool. This is nice. You do it with a little screwdriver, so it's very accurate, right? But again, we care about its size. Same thing here. Do that with a little screwdriver. It's very accurate. These, you can see it's got the pins. I'm kind of pointing, but let me see if I can get that to stay up. Sort of. See, they're offset. They're not in a straight line. So that's one little concern with that. Here's this flat one, which takes up a lot of space. These I hate. Oh, those are horrible. These are horrible. These are horrible. All right. These I don't really like. These circular ones are kind of cheap. Okay, so you can kind of see, what I'm looking at here, and you can see the company. See, it's Bourns. You can see TT Electronics that I was mentioning. Bourns, TT. So why don't we let's just bring this down a little bit more here. So the next thing let's do. Let's say, do we want side or do we want top? We probably don't want side because that's going to make it too hard to adjust. We have to put the screwdriver in sideways. We probably want to go in top. So let's do top. Okay, so that helps a little bit. And then temperature coefficient is 1,000 parts per million, 100 parts per million, 150. Let's also be greedy. Let's say 100 to 150 parts per million. I want these things to be fairly accurate. All right. And next, tolerance, 10 or 20%. Let's say 10%. Okay, let's say 10%. All right. And now let's scroll through, and this is a process. This is not easy. This is why it takes hours and hours and hours to do this. All right, you got these circular ones here. Okay, so now at this point right now, I'm kind of like, all right, I'm happy. Let's sort by price. All right, so I make an agreement to myself. I say, I don't want to spend more than $1 for one of them. All right, $1 for one of them. All right, so I scroll down here, and this is about, all I can pick then, if it's $1 for one of them. So I look here and I say, this is Cope Electronics, half a watt, that's pretty good, 10%, 100 parts per million, looks good. And then I'm comparing it to, this TT Electronics one. This one's kind of, that's what that looks like, that's what that looks like. All right, I see no reason not to use this one. Now, we don't really know what its dimensions are, right? So we could click on this. Let's click on this. So they got 15,000 of them. It means they're in stock. I don't see any, end of life, any crazy thing like that. We look down here at 1,000 units. They're like 43 cents. Now, let's back up and let's go to this other manufacturer, TT Electronics. It's roughly a little bit more for one unit. But what is it at 1,000 units? At 1,000 units, it's 46 cents. And this one at 1,000 units was 43 cents. So this is the better deal. All right. They're both roughly the same. I like that this is blue with yellow because I can see the little dial, right? Okay, so this is what I kind of want to go with, all right? And now I'm going to get all my dreams and hopes destroyed because Circuit Maker may or may not have this particular part. But I know the manufacturer and I know what this part number starts off with. So you can see here, see this 10.4? This is 10 to the fourth here, right? This is where that 100K is coming from. Right, so 10 to the third is 1,000, 10 to the fourth is 10,000, and the way that this works is it's like 1 0, and then this is how many zeros are the multiplier. Anyway, we know that the value is encoded here. So what I could do is, if I can't find this exact one, because I may change it anyway to a 50K, a 500K, a 1 meg, I'm just going to search for these few first digits. And I might be able to find a 100 or a 50K or 500K. It's the exact same footprint. Then I know I can just put the part in there because I want the footprint and I want the 3D model and I want the symbol in Circuit Maker for this part. Let's give it a try. So here we go. So I've selected it. I'm going to go to Circuit Maker and we're going to press right click, place, component, or we could have went up top there. We could have also pressed C. All right, let's go to choose. Okay, Octopart. Octopart will find it usually, but it may not have the model or anything like that. So Octopart just didn't find this at all this time. All right, so this may mean that, now let me show you this. If we go to Octopart, watch this. So there it is. It's definitely in Octopart's database, right? But it's just not in Circuit Maker version .octopart database. So let's back off some of these constraints. So instead of the 104, let's just go like this. Can we find, aha! Now look what we found here, 500, 103, whatever. So like, see this 103 part, this 103? So that is, that's going to be a 10K. So the 103, if we go back to this, and we take this part number, and this is exactly what I'm talking about. This is the process. I type this in. There it is. Exact same thing, but it's 10K. I don't really care, right? I just want something with a 3D footprint, with the 2D footprint and the symbol, and I can always change it. So now we're happy in Circuit Maker. We found something that is close to what we want, which is this 10K. All right. Oh, and another thing we didn't look at was it's one turn. Yeah, it's 1 turn, so it's not going to be that accurate. Let's go back to DigiKey here. And here is the minimum quantity. Where is the number of turns? Someone tell me that. Here it is, number of turns, right? So you see as I scroll, the first time I see a 12 is $1.85, and that's over my limit of $1, right? So I'm sorry, I'm not using it. It's $1 at 1,000. Not going to happen, right? Not going to put dollar potentiometers on this little tiny board, but you could if you wanted to, right? All right, let's go back here. So we got the part. Now look, there's no 3D model of this. There's only a kind of a 2D footprint down here. All right, and you can see that's it, but that's just going to have to do. All right, that's just going to have to do. All right, and interestingly, it's showing it's a Vishay part, which I'm not quite sure why, because this is the part number is whatchamacallit. Let's see, CT6EP01. CT, where did that go? Got to go back here. And yeah. Yeah, CT6EP103-104. Okay, so anyway, so what I would do at this point is maybe Vishay owns Copal or Copal owns Vishay, or maybe it's a generic part number. I don't really care. I can see that it's correct, and all I care about is the footprint at this point, and I'm going to go back and fix this later. All right, and put the exact part number. All right, so put this Copal part in here. So there it is. The orientation, do I like it? Not really. I'm going to turn it like this. And then I'm going to put another one kind of like right here. All right, and then I'm going to right click out of that. Okay, now at this point I need to move some stuff around. Okay, we're running out of room here a little bit. So let's go ahead and grab this a little bit. I grabbed the whole thing, I rubber banded it. I'm just going to move it over here a little bit, then zoom in. Now I'm going to put these guys a little bit over here. Okay. All right, and now let's go back and look at our schematic here and see what we got to do. So here's the rule. Between pin 8 and 7 is one resistor. That's like pot A. So we got, remember, to use the potentiometer. So if you use the two ends of the potentiometer, that's the value of the potentiometer. That's 100K. We need to put it at the wiper so we can change it. All right. Same thing with B. So we want to go between pin 1 and 2 or 2 and 3, but not between pin 1 and 3, because that'll just be 100K or whatever the value of the pot is. The pot won't work. So we want to put one pot between 8 and 7, then the other one between 7 and 6. Very, very simple. Okay, so let's go back over here. Let's get into our wire mode. Okay, so between 8 and 7. So clearly I've got some collision stuff going on here. So maybe what I can do is I can bring this V sub CC up a little bit. And let's see, can I drag this up here a little bit? And see if this tool will cooperate with me. Yeah, put this up here a little bit, move this ground up just a teeny tiny. Okay, so that's not too bad. And then maybe I can drag this whole thing down a little bit. Let me see if it'll, no. You got to be careful. Be careful when you're dragging. If you don't grab the whole thing, you can really mess things up and not know you mess things up. So let's see if I can push this up a little bit more. Okay, good enough. All right, so here are our two pots. So this is going to be a little bit ugly. Now let's drag all this in here. We don't need this to be this close. So let's do this and do this. And remember, this has nothing to do with the functional, what it looks like is not changing aesthetically, is not going to change its functionality. It's just going to make it harder for you to figure things out. So still make things neat so you can kind of see where things go, but you don't have to go crazy. Okay, so here we go. So pin 8 goes through one of these. So let's go into wire mode. So here we go. So pin 8 straight across, and I'm going to put that up here to pin 1. Boom. And then pin 2, the wiper, is going to go right here to pin 7. All right. Then from that same pin, so from pin 7, right here at this wiper, that's going to go to the other potentiometer. And that's going to go to pin 1. All right, and then from this wiper is going to go to pin 6. Okay, and that's it. Could have been a little bit neater. I don't know what I do here. Yeah, so not, just you got to kind of do it. Now, we could have done something different. What we could have done is we could have not ran wires. We could have just put net names on here. I could have put net names on here, discharge, threshold, control, etc., and then just put these parts off here and then put net names. How do you do that? Let me show you that real quick. So net label. So what we could do is right here on say trigger, I can click it and then I can put a label to it. See this? All right. And I'm just trying to push it out here so I can edit it. Let me double click it. All right, and it's called net label 4 here, but it's on trigger. So what we could do is we could just put trigger, and we can put an N there if we want for trigger negative. Now that's a label, and we don't have to have this wire. We could clip this wire and just leave that sitting there. Then wherever it's connected, we could put the net labels there, and we could have these symbols which refer to nets, and then the tool knows to connect those nets together. Sometimes we're going to do that, but not right now. So we're just going to delete that. All right. Okay. All right. And that just got a little funky. Okay, we've got to be very careful. See what that did? It just made a connection there. Got to be very careful. Okay, the tool is not a mind reader. Okay, now, we don't know what this R is, so first I'm going to call this pot A. So I just double clicked on it and this little R value. I'm going to call this pot B to stay consistent with the naming convention of the 555 timer. And if you go into the schematic, again, this is called RA, RB, and C. Okay? All right, let's go back. Yeah, this takes a long time. You're probably saying to yourself, wow. You know, and of course you're sitting here with me doing this. Okay, so all right, so we've named these 2 potentiometers. Now we have this part number here. We don't really need this part number here, and it's technically wrong because this is a 10K it's showing. So what I'm going to do right here is instead I'm just going to put the value 100K. That's it. It's 100K. All right. I don't really care about this part number. I care about the footprint of the part number and then being able to get part or parts that are in that same footprint. Okay. So now we're getting someplace. Now notice these pin 3s are just left open. That's okay. Now the question is, do we have the whole circuit? So we've got our bypass capacitor here on V sub CC. We've got our C4 here, which is just a little added capacitor. If you read the data sheet, you can put this here on this control pin. We've got our 2 capacitors here. And we've got this C3, which is C in the formula, and we're just saying a note to ourselves, it's 1 to 10 microfarad. Notice if I hover too long, or if I hover, it puts up all these supply chain things, which is real cool, but it's kind of annoying. Then we have the output, which is going nowhere right now because we got to connect it someplace. Okay, let's zoom out. So we're looking good. Let's go here. Let's grab this text, copy that, and I'm going to put it over here. All right, and I'm going to type in 555 timer clock. I don't know, circuit. What did we use in the other thing? 555 timer clock source. Okay. Again, I'm not trying to copy this exactly. I'm just trying to show you this in real time. Okay. So that looks good. And again, we need to verify this circuit and go over this thing and make sure it's correct. Okay. So a couple ways to do this. Let's see if we can kind of do it this way. And here's the circuit right here, and I'm going to just squish this down and hope that Windows doesn't crash because I've squished everything down and things get all weird when you do things like that. All right, so let's see. We got ground to ground, we got that. Trigger is pin 2. It's going to go around to pin 6 to threshold, trigger to threshold, got that. Off of threshold is the capacitor, threshold is the capacitor. Yep, that's our C. Reset is active low, so we got it up here to we're pulling it high. We've got our output on pin 3, not doing anything with that special. We've got our bypass capacitor there, yep, and then very, very simple. From V plus to discharge is RA, from V plus to discharge is RA, there it is right there. And then right at that same node discharge, there's that same node discharge, goes through RB, which it does, goes through RB, which it does, then it goes straight down through the capacitor, and then at that node where RB meets the C, where RB meets the C, that of course goes back to threshold, which it does. So this looks to me as if we have the circuit correct and we're good to go. So as far as I'm concerned, we've got the next element of our circuit. So I'm going to save that, Control S. You can always go up to File, and you can say Save and do all that too. Now what I'm going to do is notice that we have this little red exclamation point right here, Modified. So we need to commit this project to make sure it's synchronized with the cloud. So do this also. Saving is not enough. from what I understand, you need to be able to do this. So go up to the project and make sure it's selected, then right click on it and select commit. And then of course it's going to come up here. You may or may not want to commit certain elements. I want to commit everything, hit OK. And then that's it. So it's been committed. Notice everything is green over here on my project view. So we're good. So we're getting there. So now we've got the battery power system. We've got the clock system. And so if we zoom out of this design, what's next in our data flow is the 4-bit counter. So we need a 4-bit counter. So we can search through and do all that in DigiKey, or I can just know a 4-bit counter that I like, right? So I happen to know a 4-bit counter that I like, which is this part, which I think we talked about this, or a part near this. But anyway, let's stop right here, and we'll come back and we will work on the 4-bit counter, and then we'll take the output. See that? Output of the 555 goes right into that. How simple is that? Very simple. And 4 wires come out of here, 3 wires actually, because we're only using 3 bits of the 4-bit count. But let's stop here and we'll come back and do the 4-bit counter. So I'll see you in the next lecture. Bye. All right, welcome back, and we're continuing with our lecture series here on the design of the Magic Wand. So in the last video, we finished up our 555 timer circuit, which is shown here on the screen. And the last little part we had a little trouble with, or we had some discussion over, was the potentiometer. So we want to make sure that we could adjust the frequency of the system. So we've got this C3 capacitor here, which that and the 2 values of the potentiometer set the frequency as per the equation shown here. Here we go here. Right here, the charge time, discharge time, total period, and the frequency. Now, something that you can do, which is kind of cool with this tool, let's take a look at this also. And I like to do this as well when I'm designing things. So just like when you have, when you're writing code, you put comments everywhere. I put an enormous amount of comments. And at the beginning of functions, I'll usually put a whole description, how the functions work, my thought process at the time, because from a week to a month to a year later, I can't remember what it was I was doing or what I was thinking about. So I'll write down my frame of thought at the moment in the description of the function when I'm writing C code, assembly language, Python, whatever it may be. Same thing here. When you're designing electronics and circuit boards, what most engineers don't do is put down any notes, right? They don't like putting comments, but I do. And you should, so you can kind of tell what's going on, so you don't have to look for things. What were you thinking, right? And these modern tools have the ability to do this. So check this out. So we're here on the schematic entry here. We're on the Home tab, and remember, we can go Home, View, Project, Tools, and we're learning these things as we go. What are all these different things do? We get to them as we get to them. All right, if we go back to Home, and then we look down in each one of these little panels, this is Clipboard, Circuit Elements, Graphical Elements, Collaboration, Font, Appearance. Anyway, over here in graphical elements, these are not functional as far as a schematic, but they just help you annotate the objects on the screen. There's a couple interesting things here. There's image, so we could actually take an image and we could put it on here. There's also text string, which is how we kind of drew these strings right here, these text images. And then there's a text frame. All right, and the text frame allows you to put kind of a lot of text. So let's take a look at that. Let's put a text frame right here. All right, and we'll just, for now, let's make it kind of that big. And right click. So here's the text frame. It's a little bit hard to see. It's white. There it goes. Now let's put some text in it. So let's go back. Where are we here? Let's go back here. And let's go ahead and select some of this text here, right? We'll just put this text right in here. So we could say the charge time T1, T2. We don't really need these two, but let's take this one. And let's take this last thing here, which might be an image itself. So let's start off with this. The total period is this. And let's see if we can copy that. And then if so, we're going to put it right in here. There it is right there. Total period, so this is the period, equals T1 plus T2. We don't really need that T1 and T2 broken down. It's just this right here. That's it. That's the equation right there. We'll just put a times there, and we'll put a times here. All right, and therefore the frequency, we'll just go like this. We'll say, therefore, f, lowercase f, just simply equals 1 over t, 1 divided by t, all right, which just equals 1 divided by this. Simple as that. And then it wouldn't hurt us to put the duty cycle. This is kind of helpful. And again, it's a little bit hard to select this. Let me see what I can do here for us. All right, and then down here, we'll put duty cycle. All right, so we'll put duty cycle equals, and then what is it? RB over RA plus 2RB. So it's RB divided by RA plus 2RB. And we can, we can do it like this also. Make it a little bit more mathematically kind of like you would see in a math book. Kind of do it like this if we want. And a couple here. Just kind of pretty printing this a little bit. Okay, so now what's nice about this is we'll go like that, and then let's grab these handles here a little bit, bring them in, maybe bring it in a little bit more. Okay, and that's it. And we can just put that right there. And now we've got these little notes here, so we don't have to go back and look at the data sheet. Okay, so that's kind of a nice little thing to do. So you can put notes here. And then we can also take this, we can copy it and paste it. We'll put it right here, right above here. And we might say something like what? Modeling equations. Modeling equations, all right. And maybe we'll put it a little bit smaller. Let's maybe make it 12 point. And remember, it's cloud connected, so a lot of times you click on something you haven't clicked on before, the software is gonna go and do something and load things in and cache them. So you gotta bear with it. So we'll just let this thing here sit here and spin. Not much else we can do while we're waiting for that. There we go. And maybe we'll just make this 12 point, so it's not so big. Okay. And there we go, modeling equations. And maybe we'll modify that and say 555 modeling equations. Okay. So that's it. So now we kind of have that circuit, so we're totally done with that. Control S and save it. All right, so now what we want is we want that counter. So we look at the design here. So here's the original design off of our forked copy. And the next element we want to put in here is we've got the output of the timer. And all it's going to do is clock a counter. It's going to make the counter count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to something. If it's a 4-bit counter, it'll count to 15, up to 15 and recycle. That's all I wanted to do. I just want something changing a binary code. That's all I want. You could do something other than a counter. You could have put a few flip-flops and some feedback and just made it go in a random way, or an account it could count, but let's just use a counter. All right, now, so what counter should we use? Well, there's many of them. And one of the counters that we can find that's cheap is a 74393. So there's lots of different counters. Now the reason I picked this one is because it has a clear, it has a clock, and there's 2 counters in each package, and it's very cheap. So 74HC393, let me get that text string. All right, now again, there's a lot of companies that make the same IC. So all we really care about is the footprint of it and the symbol. So we want to find the footprint that we like, which is going to be a DIP package, dual inline package, because we're doing through hole, right? And then we don't really care if Circuit Maker has the exact version we want, meaning from the vendor we want, from TI or Philips or NXP or whomever. We don't really care. All we really care about is it's got the right footprint, and the symbol here is is correct, all right? And remember, people make these things, so we got to kind of check these, all right? And then when I actually populate this, maybe I'll end up putting a Philips chip in here, or maybe a different company. It doesn't need to be Texas Instruments because it's generic, right? And remember that, keep that in mind. But anyway, I love Texas Instruments parts. I use them all the time. They sample things. You can go on and sample them from free, and they make really, really, really good chips. And they're a big dominant IC company as far as TTL logic goes. Anyway, let's go find this chip on DigiKey. Let's go back to DigiKey here. All right, let's put this in. And there we go right there. And again, I'm picking HC. Why am I using CMOS logic instead of straight TTL logic? I want that voltage variance. I want it to be able to run from like 2 volts up to 10 volts or 15 volts rather than TTL voltages, which are, you know, more around that 5 volt range, right? If it's standard TTL. If it's low voltage TTL, then of course it could be down at 2 volts to, you know, 3.6 volts, that kind of thing. But we're kind of using old school chips. So we're going to use the HC version of it. But again, the HC version and the TTL version will have the exact same pinout. It's just a different technology. So again, we don't need to have the exact correct chip in Circuit Maker. We just need to make sure it has a footprint and a symbol, and we're going to maybe change the chip later down the line with a different variant of it, as long as it has the same footprint and the same functionality, but maybe it runs faster or it's a different process, CMOS versus TTL versus LVTTL or whatever. All right. So when I put the chip in here, the search comes up with all these various versions. Typically, those are different kinds of packaging, meaning how they come in singles and reels and this and that and whatever. So basically, we've got this chip. It goes 36 megahertz. All right. It's here's the dip version of it, right? So these are the SOIC, SOIC, SOIC. So we want this dip version right here. It's through hole. It's exactly what we want. I'm going to go click on it. What's its price? At 1,000, it's 18 cents. This is a super cheap chip, all right? And at 100, it's 30 cents. So it's very cheap. You can make a version yourself. Now, let's go and look at a couple things real quick. It works from 2 to 6 volts. So that means is our power supply, which is 3 batteries, which is 4.5 volts. As it dips down and dips down, this is going to keep operating for us, and that's what we want. Just like we had to get the 5555, that was CMOS, that'll work down to 2 volts also. We want this thing to keep working until the batteries are just dead. So that's why we use this technology. But could we go to a different technology? Sure, I could put a different chip in there. We could go ahead, we'll get rid of that SN, and we'll just put LS here, and let's see what that comes up with. And sure enough, there's the LS, the low power Schottky version of it. All right, again, this one's a little bit slower, 35 megahertz, whatever. This is a dip version of it. Now let's take a look. Look at the pricing. It's 3 times as much, because probably used 3 times less than the HC version. Look at the voltage range. Basically, this thing is running at 5 volts, and that's it. Anything else, it does not like that. Okay, so that's why we're using the HC version. Okay, all right. Now that we know we're using the HC version, the reason why we're using the HC version, let's get to the data sheet of this real quick. All right, so I'm in the data sheet here. Another thing you can do is the link. See, here's the data sheet link. I can go inside of the schematic here when we're in our schematic, and in that little text box, I could put a link. So when we put the counter here, I could put the link to it. So I could go in there, and as a matter of fact, just for fun, for kicks, where's that 555? There it is right there. There's the data sheet off of TI's server, right? So let's go into our page here. Let's zoom in. All right, I'm going to open this up, and there we go. All right, and I want to edit this. So matter of fact, why don't we put it right up here at top? There it is, and we can say data sheet right there. There's the data sheet right there. And then why don't we open this up a little bit? All right, there we go. Okay, how cool is that? So we got the data sheet there, and there's the data sheet, there's the total period, there's the frequency, right? Very cool. So now we don't have to go hunting around. Okay, let's get back to our counter. So read through this, but in a nutshell here, you can see the pinout here. Clock 1, clear 1, QA, QB, QC, QD, 1111, ground, V sub CC, and then clock 2, clear 2, etc. So there's 2 separate counters inside of here. All right, then we can look down here a little bit, and we can see if there's an abstract. Here we go. So here's kind of a functional diagram of what's going on. So you've got clear and clock. We've got a bubble on clock, which means it's probably going to be when there's a negative going edge is when things are going to happen, right? So that bubble means inversion. All right, and then that's what the counter looks like. Okay, and then let's see. Each one of these outputs is already going to the next toggle of the next IC. So QB is going here, QC is going here. So that's what we want. That's good. And then the first one, the first toggle is getting clocked by our clock input. So basically this thing's going to count QA to QD, low bit to high bit. And that's it. And then it's just going to cycle around. If we want to clear it, then we assert this clear right here. All right, and that's all there is to it. You can read through this if you want, but it's pretty straightforward. So let's go back to the design. Go back to the design. All right, so we want to pop down this chip. So let's go here and let's just say right click, place. Oh, as a matter of fact, let's get our little keystroke and mouse thing going here with QI press. Okay, so we want to place a component. There's a lot of ways to do it. We can click up here, component. We can right click and say place, and we can say component, or we can just press C, whatever you want to do. All right, there it is, and we want to choose. And let's go search on Octopart. We're going to put not the link in. We don't want that. What do we want? We want that part number, which is right here. Let me see if I can just select this. And SN74HC393. All right, let's put that right in there. And that never works out well. Select copying things from PDFs that are inside of the browser. So let's grab it here. Let's give that a try. All right, now we're more successful. Let's hit search. All right, and there's only one of them, and it's exactly what we want. All right, so we're going to select that. Now, take a look here. So it says U $A, and then so U1, U2, we're going to set that. But the A means there's an A and there's a B and maybe a C and a D and an E and an F. In this case, there's going to be an A and a B because there's two counters in this one package. So watch what happens when we place the counter. And then here's the model here. Remember, if you want to look at the model, you can kind of click in this little window here. And then I'm pressing the right button. I can drag it around. If I want to zoom, we hold, I believe, let's try it again. No. All right, in this case, you can hold down Control, and then I'm moving the mouse up and down. The scrub wheel does not work for zooming. And then if I want to go in 3D, I hold down Shift, and then I hold down the right button, and I'm kind of moving it around, and then I'm zooming it here again. So again, you just got to kind of get a feel for what goes on here. So this has both the footprint and the 3D model, which is nice. Okay, so we're going to pick that, hit OK, hit OK. Now watch this. I place this down, and now I place another one, and look, it says UA and UB, right? We don't need UB, so we're not even going to place it. We're just going to leave it. We're not even going to place it. We'll just delete it, and we're not even going to place it, okay? It's already there, all right? But we don't need to place it because we're not using it, all right? But you could, and you could just leave it. Now, one little note. As a matter of fact, let's talk about that for a second. Let's delete this. Let's go ahead and let's go back here. And this is important. So we're not going to place this, but what that means is that this counter, right, doesn't have anything connected to it. And since they're completely independent, now let me show you this. This is important. So this is actually something that I should have done in the original design. Now that I think about it. These clocks are completely separate, and so are the clears. Look at clear and clock, and the outputs are totally separate. The V sub CC and ground is in common, which means if we don't hook this thing up, one of these counters, it could just do anything. It's not going to affect the first counter, but it could do anything. So let's kind of do something to it so it doesn't do anything, all right? Okay, so first let's just worry about this first counter here, and we'll deal with this a little bit later. All right, so first thing, let's pull this down a little bit. And remember, I'm not trying to copy what the other one looked like, right? So I'm just trying to do this one, roughly based on this. And you can see in this case, I've got the counter here, and then I got the driver there. So in this one, this thing is taking up a little bit more space. I could squish it over here. Maybe I'll squish it right here a little bit, like that. Maybe I'll put this up a little bit like this. Maybe I'll put this right here. Maybe I'll put that right there. And maybe I'll move this up a little bit, but I'm just going to leave this right here, all right? I'm just going to leave this right here and just put it over a little bit. That's it, all right? We don't have to copy everything exactly. All right, so here we go. Let's hook this thing up. All right, so first thing is we need some power here. So let's go ahead and let's grab a V sub CC here, or we could go up here to power port and we could grab one of these, but I'm just going to copy and paste. Learn to copy and paste everything. Control C, Control V, there we go. And I'm going to put power. I could put it over here because I got a little bit more space. Or I can put it right here. Matter of fact, I'm going to put it over here. No, let's put it here. Yeah, we'll put it there, and let's lower this a little bit. And again, you're always, you're trying to keep things clean. Okay, now we're going to press W, get into wire mode. All right, so there's V sub CC, so I'm going to hook that up right there. All right, I'm going to hook this right up here. Now notice that I don't really need to do this because pin 14 is being replicated, but let's just do it just to be consistent. Now let's go get a ground, copy, paste, and I'm going to put the ground way down here. All right, with W, get into wire mode again, and let's go ahead and draw this in here. Okay, now we got that hooked up. Okay, zoom in. Let's make sure we got everything. Okay, now check this out. So we don't care about this one. We don't even want to use this one. So clock is active low here, right? So what we can do to just make sure this thing is not doing anything is we can just tie clock high. Just tie it high. So W, and we're going to tie it high. That's it. So it's never going to get clocked. So this one's just going to sit there. We don't need to hold down clear. We can just leave that doing whatever it's doing, right? So this is clear active high, right? So if we want to be consistent and we just want to put clear to something, it's not going to hurt. We can take clear. We can go down here and we can tie it low. All right, we can tie clear low. All right. Now we go back to our reference design here. And you can see clear is tied low here also because I never clear it. It just clocks. We just want this thing to free run, right? So back on this one, we can also go back to wire mode, and here's clear. And we're just going to tie the clears together like that. So this is never going to get clocked. Both of them are always being held clear low, so they never get cleared, all right? And then the only one we want to clock is this first one here, all right? Now, over here, we're calling this U, we don't know. So let's put a reference designator. This is U, oops, let's make that U1. Make that U1. Okay, let's see if 3 times a charm. U1, all right, and then this is going to be U2. And then it'll update. Notice it should have updated in both places. Okay, this tool doesn't do that, so we got to do it twice here. All right, so U2A, U2B, that's consistent. All right, so that's good. Control S, Control S, Control S, always saving. All right, now where's our output? Here's our output right here. So we're going to take our output and we're going to put it right into this clock. So what do we got to do? We're going to have to move this a little bit. Let's move this little modeling equation thing here. All right, let's press W for wire mode. Here's our wire. And right there into clock. Okay, so it goes right there into clock. We're all good to go. Now, let's see if I can drag this part up just a little bit. Whoa, whoa, whoa. This bottom half without doing anything funky, which I'm always weary of. You've got to be very careful it didn't connect some. Okay, and then also Texas Instruments. You know what? I don't mind the TI part. Let's just call it TI. We don't need to spell out Texas Instruments here. Same thing here. TI, don't need to spell it all out. Good enough. And remember, it doesn't need to be TI. It's a TI part. TI is kind of what we're going to use anyway, so we're probably going to use this part, so we could leave it. Otherwise, we could leave the generic 74HC393 and then know we're going to use some particular manufacturer later. Okay, good. All right, so we got our clock in there. What are we missing? What are we missing? Are we missing anything? The outputs, obviously, we've got to do something with the outputs. Not with U2B, though. Don't care about that. But what are we missing? Bypass capacitor, right? This is a clock. It's going to generate some noise. It's got a bypass capacitor. The C2 right here, let's just copy this. So I'm just going to grab this and copy it, Control C, Control V, and I'm just going to put it right here. This is why I wanted to move this thing a little bit. I didn't really like its positioning. Right? So first what I'm going to do is, see this line right here? I'm going to drag all of this down just a little bit, just a little bit, just a little bit. Okay, hoping that I didn't mess something up. And I'm going to drag this down. Oh, that's not helping. Drag this down, this over here. So now that node is like connected. I can't drag this ground away from this little node right here. It's connected to it. I could break it if I want, but I'm not going to. That's fine. All right, now I've got a little bit more room here, and let's see if we do Control V again, we've got the capacitor here. So what I'm going to do is I'm going to just put it right here, press W, connect it here to V sub CC, and then I'm just going to move this just a bit up. There we go. And now this surely isn't C2, right? It's not C2 because this is C2. All right, let's look at our capacitors. C1, C2, C3, C4. So we're going to call this C5. Now, reference designator. You can name these at the end. You can name them automatically. You can name them on the fly. And you can also put some spacing in them. For example, when I'm designing something, say I'm doing the power supply. Say I'm not done with the power supply. Say I've got maybe 8 capacitors. Maybe I need a couple more in the future. So what I'll do is in my mind I'll say I've counted from C1 to C8 here. I'll probably need a few more. So in the next block of electronics, I won't use C9. I'll just call it C15 or something. Basically, I'll leave some reference designators available and open for that other block so that it's like C1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's not C1, 2, 3, 4, 5, 6, 8, 49 because I need an extra capacitor and I've already used up all the reference designators. So basically leave space in your reference designator numbers so that if you want to have additions to other blocks, you don't have to go rename everything, right? So why don't we do this? So we've got C2, 3, 4, right? This normally would be C5. We could make it C5, but since it's a whole nother block, right? Maybe later we figure out we want another capacitor here or something like that, right? We could just call it C10 if we wanted, right? That would give us some room here. Maybe we need to add something later, right? Now, since I know we don't need to add anything later because the design is done, we're going to call it C5. When you're designing something for the first time and you're kind of in that design R&D mode, leave some reference designators values available in each section. And then what I do is I round by 10. So if I use capacitors, 1, 2, 3, 4, 5 here and resistors 1, 2, 3, 4, 5, 6, maybe in the next block I'll start with C10 and R10. So I'll basically have a bunch of slots available in each block. So I'll round by 10, and that's where I'll start the reference designator numbers in the next circuit block, all right? Very good technique, and it keeps things nice and clean. Then when you add one little capacitor, you got room for it. There's a reference designator or a resistor or an inductor or whatever, okay? All right, so we're going to call this, what, C5? Because we already have it designed, we don't need to worry about it. Okay, so we've got our bypass capacitor there. We're good to go. We got our clock here, so this looks good. Let's go and copy this little text here, and let's call this 4-bit counter, because that's what it is. All right, let's take a look at our design, our original. All right, and then we've got this little note here, right? So this little note, I think I can copy that. Let's see, can I copy from page to page? Yeah. So put it right. We can put it right here. There we go. Cool. All right, let's go back here. And all I did was select it and copy it like I would. So this tool you're going to find has some little quirks that you can copy certain things page to page, and you can and can't, and you have to kind of do things. You got to kind of trick it and select it in a certain way, like any Windows tool or Linux tool or Mac tool, you name it. They've all got their little idiosyncrasies. So anyway, all right, where are we now? So we've got the outputs here, and now I decided to take these high outputs because this is going to be counting a little bit slower than these lower 3 bits, right? Which will be clocking right on the clock. And because I want this to be viewed by human eyes, so you can see it blinking, I picked these last 3 bits. You could pick any 3 bits. It doesn't matter. It's just counting. We just want some bits toggling so these LEDs ultimately do something, right? But let's just do the same thing here. So we're going to take bits 4, 5, and 6, and those are going to go into a 3 to 8 decoder. All right, so same thing. Let's go get a 3 to 8 decoder. All right, and as the value goes from 0 to 7, it's going to select each one of these outputs here, which is going to go into our LED. All right, so for a 3 to 8 decoder, there's really only one chip to choose from this technology, from this era, which is the 74LS or HC or LVT or LV or LVC 138. So, and again, we're going to use CMOS, the HC version, because we want that voltage variance, because we're going off battery power that's going to go from 4.5 volts and slowly dip down. We want this thing to keep running. Okay, so let's go get a 74 HC here. So I'm going to select this. I'm going to go over to a DigiKey. All right, let's go take a look. There it is. Okay, and they've got 1400. They're 66 cents for one. We want the DIP package again. As long as you got the correct package, we can change who the manufacturer is and all that, and even the technology, HC, LV, LS, whatever. But we are actually going to use HC, and we're probably going to use Texas Instruments. What's it at 1,000? 28 cents. Not bad. So that's cool. And again, look at the voltage, 2 to 6 volts, through-hole DIP package. This is exactly what we want. Let's pop up the data sheet just so we have it for reference. We've looked at this before. All right, so this should be familiar. It's just a 3 to 8 decoder. All right. Everyone should know everything that we're, whoa. Okay. Everyone should know everything that we're doing at this point because we've went over all this material. So basically it has a bunch of enables, and these enables are 2 enables that are active low and 1 that's active high, just to help you with decoding and so that you can enable this in a variety of ways. Then we have the 3 inputs, A0, 1, and 2. They may be called something else depending on the chip manufacturer. As this goes from 000 to 111, you will select each one of these. And then there's 2 versions of the chip, the 238, which is active high, and the 138, which is active low, which is typically the more common one. And the reason why is because most chips are enabled active low. So this, you just connect this right to a chip and it's enabled. If you want to use an active high, then you can use a 238, but these are actually harder to find. So if we, let's take a quick look here. If we go here and we search for the 238, I don't think you can even find it here. They actually do. They have 2,800 of them available, which actually surprises me. All right, anyway, we're going to use the 138. So this is the part number we're using. Okay, that's the data sheet, so we're all good. Let's go back to Circuit Maker here. Let's go to our Circuit Maker version. All right, now, let's see here. Kind of the way that we design this, we're running out of a little room here. So let's put the LEDs over here maybe, okay? And let's put the decoder right here. Why not, all right? So let's do that. So we're going to right click, we're gonna say place, we're gonna say component, and let's go choose. All right, that's a bug you just saw pop up, and I've read why that happens, but just ignore it. There's only one of them, high-speed CMOS 3 to 8 decoder, looks good. Preview not available, so I think it's because that bug that just happened. Let's double click on it. Okay, so this is not working. Let's back out here for a second. Let's cancel. All right, let's press C again. All right, let's see if this works better for us this time. All right, and let's do that. Let's get, there we go. And okay, so this happens from time to time. It can't find it. There's like bugs in this, obviously. And so sometimes you have to back out, do it again, or you got to close this whole application and try it again. So if there's a part you know that should be there, or you were just using it, it's not showing up, you got to kill the application sometimes. All right, so we've got the symbol and we've got the 3D model here. I can grab the model, move it around. You can look at the key press thing here on the left side of the screen and kind of figure out what I'm doing. Right button, and then control, and I'm zooming in and out by moving the mouse, and then shift, and then grabbing it with the right button and going into 3D. Looks good. Let's take that part. All right, we're going to place it right here. Very simple. Okay, right click to get out of that mode, hit escape. Okay, here we go. So we're looking good. All right, so this is going to be you. Another thing, when you're doing your design, so see this, the top of this line here. So I could line it up here. So I'm just going to move this down a little bit, and that way the outputs on things kind of line up a little bit better. Okay. Okay, TI, Texas Instruments. Let's get rid of that parenthetical. I know it's Texas Instruments. Good enough. Okay, and this is going to be U3. U3. All right, so we're getting really good at this. We don't even need to look at anything. Let's take this C5 here. Let's get this going, copy and paste it. Let's go ahead and we'll put it right there. It's got our V sub CC, copy and paste it. We'll put this right up here. Let's go into wire mode. Let's hook up our power. Good. Let's hook up our bypass capacitor. Good. All right, let's get our ground. Select ground, copy, paste. Now, see how this is where this gets fun. When you get the hang of this and you've got a bunch of blocks, Control S, when you've got a bunch of different things, you just go and grab this. You want a 555 timer circuit? Just grab this whole thing and take it. You know, oh, look at this little error over here. When we drag this clock line, this happened. So what I'm going to do is I'm just going to click it and drag it back. There we go. Okay, so that's good. Control S. Okay. So now we got our our decoder, our 3 to 8 decoder here. So first let's deal with these enables. So I want this thing to always be enabled. So E1, E2 are active low. You can see the circles, and E3 is active high. So we're going to ground E1 and E2. Let's do that first. W for wire mode. Let's go out. Boom. There's that one. And there's that one. And then E3 needs to go high, so I'm going to just pull this straight up to here. Let's create a little bit of room here. Now we could go to through a pull-up resistor, but it's okay just to pull it directly to power because it's CMOS and there's no current's going to flow. All right. But it doesn't hurt to use a pull-up resistor of 1 to 10K, and a lot of times I'll do that just in case it'll decrease. Uh, uh, there's you know, currents that flow no matter what. These aren't perfect gates, right? So there's currents that'll flow, you know, into these gates as a, you know, parasitic current and leakage currents. And so putting that resistor will decrease that a little bit. But in this case, I don't care. We're just going to put it straight up here. Now it's active high, so that's good. And I'm going to go out of wire mode. You can see a little X there. I press W. I'm back. Nope. Okay, let's press escape then. Or right click. There we go. And we're out of wire mode. Okay, so the chip is now completely connected up as far as power goes. So that looks good. Now we need these 3 inputs here. Okay, so let's grab this whole thing. Let's move it over just a little bit. Now, remember we talked about nets, right? So we can go over here and back here on the circuit elements, we've got wire, we've got net label, and we've got port. All right. So watch this. We can go to port, and it makes this little port symbol here, right? So this is kind of cool. So watch this. I'm going to put one here. And you can kind of draw these things. And there's one there, and there's one there, and then there's one here. And the reason why it's called a port, you know, in electronics, we kind of think of data as moving through little conduits called ports, right? So a GPIO, a signal, whatever, you just call it a port. A GPIO port, or a signal port, or a control port, whatever. And then there's a nice little symbol for it. And we can then label this. We could actually label this. We could call this A0, right? We could call this A1, and we could call this A2, all right? And then another thing, see how it says IO type unspecified, right? We could just leave it unspecified, or we could say bidirectional. Technically, here's the thing. Right here, these would be inputs, right? But if I'm going to use these as port names over here, they would be outputs. So what we're going to do is we're not going to get that detailed. We could say bidirectional, but that's technically not true. So let's just say unspecified. Okay, just unspecified. And let's call this one A2. Okay, now we've done that. Let's go into wire mode, W, and let's connect them up. That's going to go to A. This is going to go to B. All right, and this little problem here, there we go. And then this one's going to go to C. So there are these 3 ports, all right? And so we've got these kind of 3 ports. Now I can put them a little bit closer. Can we do that? Let me take A1, let me drag it up a little bit, okay? So I dragged it up, and let me take A2. So I dragged it up. So that looks real nice. See, it looks real nice right there, okay? So now we have A0, A1, A2. So these are net labels. And wherever there's A0, A1, A2, it will be connected in the schematic. Even though it's not visually connected, it's abstractly connected in the data structure. So now what we can do is check this out. We can take these 3 signals, copy, paste, and we're going to connect them right here. So now we're going to connect QB, QC, and QD to these 3 things here. So let's go into wire mode. There we go. There we go. There we go. All right. And there it is. So now what's cool is we don't have to have these wires. We can drag this wherever. And then this is abstractly connected here. So you don't have these wires all over the place. Now, if you look in this other design, I put the wires. So I dragged the wires all the way from the counter all the way around here because it just looks cool, right? But it's a little bit much because I can't really move this element around without these wires getting dragged all over the place, right? So that's why you create these either net labels or these ports, and you can do this. So see how nice that is, all right? Now, so we're going to use this philosophy here, all right? We're going to use this philosophy. Let's move this up a little bit. It's annoying me, all right? And oops, let's make sure we get V sub CC here. Okay, I'm going to move this back here, and let's line it up at least. Okay, all right, zoom back in, looks good, Control S, okay, looks good. Okay, we're doing really well here. So we've got our 3 to 8 decoder, it's got bypass, it's all enabled correctly, there's the enables, all good to go. We've got our ports here, A012, A012, it's going to basically cycle through, click, 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 it's going to do that, very cool. Now, all we want to do is then connect these to a bunch of LEDs. Now, let's be analog engineers here for a second. If we connect these directly to an LED, can it light the LED properly? I don't know. You tell me. Let's look at what the output current is for the source or sink, okay? So let's scroll through here. Let's look here. What do we got? Okay, looks here, HC type, this and that. It can standard outputs 10 LS TTL loads, so that's pretty good. So each one of these can drive 10 loads. That's pretty good. All right, and if we go down here to the outputs, maximum ratings, no, we don't want that. Okay, here we go. V output high. Do I want that? No. We already know what the voltage is. It's going to be the voltage of whatever we're running the V sub CC at, right, roughly. We want the current. We want currents, okay? So now here's the currents that we want to know about. How much current can this thing drive? And that's the question here. So let's see here. Low level, high level TTL, and if we go here, let's see, keep going here. Here we go. All right. So here we go. So see this right here, low level output voltage, low level to TTL. So we want to know this right here. What is this current? I out in milliamperes. So see this 4 milliamperes here, and then here's a high level and here's a low level. So that's what the negative is for in the positive. So basically 4 milliamperes. So what it's saying is this thing can output 4 milliamperes, all right? Not a lot of current, but it's enough to light an LED. Not enough to light 10 LEDs, but enough to light one LED. And we're only lighting one LED at a time. If we go back to the design, only one of these is going to be turned on at once. They're mutually exclusive, so we're going to have just one LED turning on at a time, all right? So it'll be enough to light the LED up, okay? Now, we also have to put the LED in the correct orientation. So since this is going to be active low, we're going to take power through a resistor through the LED to here, to each one of these, 8 of them, okay? All right, so let's go look at our original design here, so for reference, and see what's going on. Now, so see here, I've got V sub CC, and then I've got all these LEDs, and then I've got these 100 ohm resistors. Now, we just said that this thing can barely output 4 milliamps, so why do we need a resistor? You don't, but it's good practice. And you could just put a 0 ohm resistor in there, or a 10 ohm, or a 1 ohm, or just a current limiting resistor, just in case a catastrophic something happens. I don't want to blow anything out. So the 100 ohm limits the current, and nothing bad is ever going to happen. So the 100 ohm is just a placeholder. I want to put a resistor there. I want you to get in that design habit. Don't connect things directly to things without resistors, especially I/O devices like LEDs. But I want you also to realize we already looked at the current drive. It's only 4 and 4 milliamps in or out, right? It's barely going to light the LED. So keep that in mind. All right. Okay. So another thing also I thought, again, we're going to get a footprint of an LED. We can put any color LED we want. We can buy, there's 1,000 different manufacturers of LEDs. We're going to use 5 millimeter diameter LEDs. I'm going to make them all green if I ever build this, and with the last one white, but you could make them any colors you want. And I thought that it would be green, 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 and then it hit white. Green, 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 white. You do whatever you want, all right? So anyway, but we want a placeholder for the resistor, and we want these LEDs. Okay, so now we need a wire going to each one of these, okay? And we need to place a resistor and an LED. Okay, so now we've got the problem with the LED and the problem with the resistor. So first, let's go look up a 100 ohm through-hole resistor. Okay, let's go do that. 100 ohm through-hole resistor. Here we go. So I'm going to say 100 ohm. 100 ohm should do it, but it may find a bunch of other stuff. Let's give DigiKey a second here. Okay, and we look through here, through-hole resistors, 76,000 of them. Okay, it's got a couple. All right, so let's look for bulk, cut strip, cut tape, good enough, and let's say in stock, RoHS compliant, wanted active. What's the resistance I want? I want 100 ohms. And once you find one resistor, you can tweak the number on it to find other resistors. Okay, apply filters. Now, this composition thing, right? We've talked about this a little bit. Carbon composition, carbon film, ceramic, metal film, metal foil, metal oxide film. Lots of different options here. They have different properties. Typically, metal film is going to be more expensive, it's going to be more accurate. Carbon composition is kind of the cheapest, lowest price ones. Carbon film a little bit better. Ceramic is kind of unique. So if you want high precision, you go to metal film, right? If you just want it cheap and you want it decent, use carbon composition or carbon film. So what I'm going to do here is I'm just going to say carbon composition, carbon film, and I just want to put, I want to put metal film So, and you can just hold down Control to select different things, just so you can see the price variance. Now, tolerance, what do we want? Well, if we were doing timing circuits in something very advanced where I needed really accurate timing, I would go down to, maybe 0.01%, right? But the electronics vary so much, we don't really care. And in this case, 5% is fine. 1% will be a little bit more expensive, but let's just use 5%. That's a kind of a common 5% resistor. Let's hit apply filters right here. Okay, and now wattage. What do we want for wattage? We want standard quarter watt resistor right there. There's the quarter watt resistor. Okay, and then we have some of these other features: flame proof, this, that, pulse withstanding for high current pulses. Don't care too much about that, but I do care about the size and dimensions. You got to be careful when you buy resistors because they, even in quarter watt, they'll come in slightly different sizes, and you'll get them and you'll be like, why are they so big? Or why are they so tiny, right? So you got to be really careful. And you can see here, there's these different dimensions here where it's saying that it's 1.7 millimeter by 3. So this is the diameter is the first number and the length is the second number. The resistors that we want to use are the ones that are about 6 millimeters long. But see, there's a 7 millimeter also here. So we got to be really careful here. We want to make sure that we're not picking something too small. These are these kind of teeny tiny ones, these little 1.7 to 3.3. So we want these ones that are like 6, 6.37. So what I'm going to do is I'm just going to select these three here because I want this kind of range of size. Right? Then we kind of eyeball it. Now, you see these kind of cylindrical ones? These are usually a little bit bigger, all right, than these. And so again, you can kind of look over here, and these are all the things that you got to go through. See, these are 6 millimeter, then 6.3, 6.3, and see this one's 7. See the 7 millimeter long there is kind of these kind of cylindrical ones. See how it's cylindrical, and then see how these are a little bit more rounded. So I can just look at this and I can tell this is kind of what I'm looking for. Now let's sort by price here. All right, and come on, come on. All right, there we go. And look at this. 80 cents a piece? Are you kidding me? 80 cents a piece. Why are those 80 cents for a little resistor? Well, it's pulse withstanding, which means that if this is hit with a huge amount of current, it can dissipate it without blowing up, right? And this one's non-inductive, pulse withstanding. We don't really care about that. What we want is over here. So the carbon film looks good. Flame retardant coating looks good. And this is 400 parts per million per degree centigrade. This one's 350. If I was going to actually pick this, I'd want the one that's a little bit better, so I would pick this one right here. This is Stackpole, great company, and this is Yageo, great company. Either one is going to do. So what I'm going to do right here is this. I'm just going to grab this little part number, and I'm going to see. Now, what I only care about is the footprint, because I want something that's like this 6 millimeters long kind of little resistor. So I'm going to pick that footprint, pick that part number. I'm going to go over here, and I don't know what these ones are, right? We could look and copy them, surely, but we're trying to do this this time originally. So now let's go here and let's place a part here, and let's go choose. And let's put that part in there. All right, let's see what happens. And I bet you there's a model for it in a footprint. Yep. All right, so there it goes. Okay, now this I'm not sure I'm happy with. So see, in this case, he did this so that it's vertically standing. And let me try and get this for you. So I don't like this. So see, the footprint is actually very small. And there we go. And he's making it vertically standing. I don't want that. I want it to be horizontal on the PCB. So this footprint is actually incorrect for what we want. So let's just not cry over it. Let's go here and let's see if someone made a footprint for this one more like what we want. All right, there we go. Okay, no part found for that right there. Let's get rid of the ND. No part found right there. Okay, so the 100 is clearly the 100 ohm part. All right, so now let's try this one. No part found, even though it just showed it to me. Let's get rid of the 100. Okay, this is more what we want. Now see these are the values here. See the 1K, the this, the that, whatever. We do not need the 100 ohm version. We could just pick the 1K version because all we care about is the footprint. So let's just pick the 1K, or we could pick we could even pick like 220 ohm version. It'll have the same footprint. And this one doesn't show. So this one doesn't have a 3D model, a pretty 3D model. So I like the one with the pretty 3D model, even though the value's wrong. This is 1K, but I don't care. All right. So now we've got our 1K right here, and now we're going to know to change these. All right. So let's. We're just going to put that right there. Okay. And what we're going to do here is we're going to just get rid of this whole stack pull thing here, and we're just going to put 100 ohm. Done. It's 100 ohm. We're going to realize the model and everything is for the stack pull. The part numbers for the stack pull 1K, but we don't care. We just want to make sure it's the right size. Okay, so we got one of them there. Now let's get our LED. Okay, so let's go back here. Now this is a huge subject, LEDs, and you know there's tons of them, and there's a lot of parameters. There's their brightness. There's their view angle. There's the material they're made out of. Are they transparent? Are they clear? Are they diffuse? So many things. There's different sizes, countless things about LEDs, and so anyway, this is one of those things where as you learn to play with electronics, you need to buy a bunch of LEDs, you need to get them, you need to try them out, see how you like them. They've got forward voltages. What voltage does the LED turn on? It depends on the color of the LED. Is it red? Is it green? Is it blue? Is it orange? Is it purple? All those kind of things matter. How much current, how much brightness, and you got to play around. So we're going to use, if we can find this thing, this part number right, this part number right here, we're going to use this one right here, right? But let me show you something. If we just go to DigiKey and we type in LED, all right, so 1.2 million results. So if we go to discrete, all right, 22,000 results. All right, and then I wanted green and I wanted white, right? So we could just, right off the bat, we could say, hey, we want green. We want just a green LED, all right? We want it in stock. We want RoHS compliant. We can have it in bulk, or we could have it cut strip or cut tape. Okay, what kind of lens do we want here? Do we want it clear, diffused? I want it diffused because I don't like the clear lens. Let's start searching right there. All right, now let's make sure it's active, right? We don't want anything that's obsolete. Okay, looking good. Now we've got, look at all these things we've got. We've got forward voltage I was talking about, 1.8 volts, all the way up to 14 volts. Whoa. We've got current. How much current can you push through this thing? The more current, the more light it puts out, right? The more its luminance or brightness is. The viewing angle, what's this all about? The viewing angle is how the light is diffused, like a cone, right? So here would be like 25 degrees, 30 degrees, 40 degrees, etc., like that, okay? And then over here, mounting type, we want it to be through hole, so let's start with through hole. We don't want it to be right angle, so we want it through hole, and let's just start there. Let's apply filters. Okay, so now we've got all of these LEDs here. Countless LEDs, countless LEDs. Okay, now we could go to the forward voltage and mess with that a little bit and put a real low forward voltage because we want this thing to be bright as quickly as possible. So let's try something. So on the forward voltage thing here, let's go 1.8 to, let's say, 2.2. Let's just really hammer it and make it real low. Okay, now the next thing is, what wavelength do you want it to be? These are all greens. These are all greens here, from 518 nanometers to 576 nanometers. What kind of green do you want, right? So this matters also, right? So this is how crazy this is, right? So if we go here and we say wavelength chart for green. Now, of course, you're looking at this through a camera, through YouTube or this or that. It's all been digitized and regurgitated and all that, so it's going to be totally inaccurate. But let's see if we can find some little chart here for the greenest of green. Okay, so I kind of like, I don't know, maybe this chart here. All right, view image. Okay, let's make this bigger so you can see it. Okay, so depending how colorblind you are or you aren't, if you can look here as we go, so 550 nanometers is kind of the center here, greenish. And then as we go left, we get more bluish. As we go more right, we get more yellowish. And then, of course, over here is red. So if we look at those frequencies, if we look at those wavelengths, basically we can go 518, and then we can go all the way up to 576. And if you look over here, 570, this would be someplace, around in here. It's getting a little bit yellowish, right? And the 518, that's over here. So it looks like kind of in the middles of 555, right? That's 555 timer. So I mean, hey, that sounds like a good number to me. So let's go here and let's say our wavelength, dominant wavelength here, right? So, or you can pick the dominant wavelength, peak wavelength. 555 we kind of like. So let's see what happens if we go 555, 560, 562. Let's just kind of put those in there and let's see what happens. These are all the things you can play with. And then the millicandela rating. Candela is a measure of brightness. So I want these to be bright. Let's say 10, 20, and 30. Okay? All right. Now, what size is it? What's the size? Is it 3 millimeter, 5 millimeter? There's all kinds. And it's the diameter of the base of the LED. All right, so we've got the 3 millimeter, which are little small guys. So let me show you. These little ones here, that's a little 3 millimeter. And then the bigger ones, like that, those are 5 millimeter, okay? So we want 5 millimeter. I want these big. So we're going to do this. Dome top, they're called T-1 3/4. All right, let's apply filters. Let's back off a little bit. Let's put this 5 millimeter too. All right, there we go. Okay, finally, we got two companies, Everlight and Lumex, that meet all our requirements. What are their prices? We sort by prices, and here we go. All of them are 20 millicandela. They're 2.2 volts, 20 milliampere. View angle is 75 degrees, 75 through hole, and 562. And then this one's got a 555 as its dominant wavelength, a little less viewing angle. All right, and this one's 50 cents. All right. So anyway, we could pick any of these that we want, all right? Lumex, I use this company a lot. I use Everlight a lot also. But we were kind of looking for that 555 dominant wavelength. We don't really care because all we want is the footprint for it, okay? And then here's the height. Sometimes that is also something. Got to be careful. These are all a little bit tall. Okay, let's see if the tool actually has this part. So I'm going to put this in here. And remember, all we really need is a footprint. All we need is a footprint. All right? All right. So here we go. And I'm going to right click. I'm going to say place. I'm going to say component. And if we just put LED, this would come up with a bazillion LEDs too, right? Let me show you. If I just type in LED, green, through hole, it came up with all this stuff, right? Okay, so now if we put in that part that we just found, let's see what happens. No matches found. Go like this. Give it a minute. Nope, doesn't like it. All right, can you find this one for me? Let's see, can it find this one? Okay, no matches found. Uh-oh, I'm getting depressed. Can you find this one for me? And remember, I want to find something that's got a symbol and a nice 3D model also, so we can see the thing in the 3D view of the PCB layout tool. Okay, couldn't find any of these that we just painstakingly did all this for. So that doesn't mean we can't use this part. We can actually put this part in the board. We just have to find a different part for the footprint so that we can put something in our schematic. Okay, now let's go back here. Now remember, ultimately the reason why this matters to me so much is when we're in this view right here, when we're doing the layout of the PCB, right? So here's our final PCB of this thing, right? And here are LEDs. When I go to look at this in 3D view, I mean, it's nice that I can see, you know, the 3D circuit, you know, with the LEDs there. So I want the, you know, the 3D model there, okay? All right, let's go back here. So let's just cheat and use whatever I used here. So here's a green one. Here's a green one. And I use this part right here, which is this part right here. All right, so now I can go place this into the other schematic, or I can just copy the part. So let's just do that. Let's take this and copy it. Control C, it's copied. Let's go over to this schematic here. Boom. So there's a green one. Let's go here. Here's the white one, which I believe is also the green one. And let's copy that. And copy it here. Okay, good. So there's a green one, white one. Now we're going to hook these all up with the resistor, right? And then we're going to connect them all to the outputs here, okay? And then that's that. So why don't let's stop the video here. and I've probably already stopped it a couple times or edited it. So we break these lectures up. Let's stop here and we'll start back up and we'll add the LEDs in. Okay, so I'll see you in the next video. Bye. All right, welcome back, and we're continuing with our magic wand, our little kind of magic wand Harry Potter design here. So we just left off, we were working on the resistor and the LED that we're going to replicate 8 times, which is going to connect to our 3 to 8 decoder. All right, so that is what we are working on now, and let's get this QI press thing going again as usual. All right, let's get back here. And remember, if Circuit Maker starts acting funny, just close it down and then restart it. So it's starting to get a little weird with me right now, so I may have to do that. Okay, so let's see here. Now, when we left off, we were talking about these LEDs, and we went and we searched around for something that we might actually like, but we couldn't find that part number, so we did another search inside of Circuit Maker and found something that's got the correct footprint, but not the correct part. So we just need the footprint, and we wanted a 3D model so we could see it inside of PCB view when we get to that part. And then the other thing is we picked a green LED, and then we're under the assumption we can find a white or blue or red or whatever colors you want from the same manufacturer. So we're just going to change what the string here is describing it. So if I double click here, I'm just saying a 5mm lead green, and here we're just saying a 5mm lead white, right? Okay, so now what we need to do is we want to connect the output of the 3 to 8 decoder to each one of these LEDs. Now, the way that I did it here, I put the white LED on Y7, so it would be the last in the sequence. We'll just kind of do that here as well. Now remember, you can make the LEDs any color you want, you can do anything you want with them, but we're going to just kind of copy what we have in the other magic wand. All right, so let's take this here, and we'll put it like that. Let's take this resistor, we'll copy that. And remember, you just select and then Control C, Control V. All right, now also, if I take the component, grab it and drag it, and I put it on top of the LED where those nodes match, see how it made the connection for me? But don't assume that it does that, all right? Be careful. So I'll drag that down, and see, it didn't do it that time. But if I drag it, if I let go, then it's doing it. All right. So the whole point is just be careful. Don't make the assumption that it does it. You know, that's why I like going into wire mode and putting an actual wire. All right. So now what we're going to do is we are going to replicate this 8 times, and keep your eye on what I'm doing here. Control and then the wheel to zoom and all that. Right click and hold to drag or pan. All right. So we want this green LED a bunch of times. So Control C and Control V. All right, and notice the reference designator is staying the same. All right, so we're going to have to change that. And let's scroll this over a little bit more, and I think that's 8 of them. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, so we need one more, so I'm going to grab all of this and just drag it over here a little bit, and then Control V since I've still got that inside of the cut buffer. Okay, and then looking at the spacing between these, they look all pretty much the same except for the white one, which I'll just move a little bit in. There we go. All right, and now we need to change what these diodes are, what their letters are. Now, do we have a diode anyplace else? Do we have an LED anyplace else? No, so this is the only place. There's no battery power, so we could put an LED up here, but in the original design I don't have it. So we could do that to let you know that it's on, but the second it turns on, these LEDs are going to start moving, so that's why you don't need an on light and LEDs blinking. All right, but let's go label these things properly. So just to be consistent with what I did here, so this is going to be D1 down here, and that's going to go to Y0, and then all the way up to D8. Okay, the resistors I don't care so much about what their names are, but let's keep the diodes semi-consistent. All right, so this is going to be D1. So I just click on the reference designator. This is going to be D2. Now if I click on the component, I'll get the bigger dialog. So I click on the component, let it do its little cloud thing, and so you get this larger dialog where you can see all this information. You can also mess around with the 3D model here. I right click and drag it, or I can hold control and I can zoom it in, and I think shift, and then I can do this whole 3D thing here with shift down and the right button. So I can see that it has a 3D model and a footprint and all that. Okay, so going back here, D1, D2, D3, D4, and that's another thing. If you're going to use these cloud-connected applications, which I'm not a fan at all of cloud-connected stuff, and I mean, just as a philosophical aside, I think trusting all your information to someone else, to their servers, is a bad idea. When I buy a DVD, I want the DVD, I want to hold it in my hand, I want to put it someplace. I don't want to have everything with digital rights on servers everywhere, because what happens if that information is lost? Your ownership is lost. So this whole cloud thing, the way that everything's been going like this, it'll go back. It'll turn back, and everyone will want to put things locally. It kind of goes back and forth over the years. But definitely make backups of things locally on your hard drives at your home so you have it. Make sure you do that. And there's a feature in here where you can actually archive your designs. You can do an archive and download it, and then you can save it locally. So that's important to do also, so you're not completely trusting it. I'm sure they have it backed up 3 times or 30 times, but I don't trust that. All right, so D6, D7, and D8. So those actually happen to be in the correct order. So D1, D2, D3, D4, D5, D6, D7, and D8. So that's good. Now let's work on our resistors. So over here we've got 2 potentiometers. We literally do not have a single resistor in the design. I do not think we do, no. So we can actually name these R1 through R8 also. So here we go. We'll call that R1. We'll call this R2. Call this R3, R4, R5, R6, oops, R6, R7. And notice we can also play with the fonts and things like that, but we're just going to leave them in kind of this standard default. The color, you might, if you look here, you can play with the color also. All right, so we've got those. Now, what we need to do is we need to tie all these together. Now, let's be very careful here. So the output of the 3 to 8 decoder, these are active low. So these are going to be ground, zeros, right? So these are going to be ground. So there's ground, it's going to come out. It's going to go into the cathode. So the anodes all need to be tied to positive. So we're going to tie all these anodes together. So let's press W, go into wire mode. And we're just going to put a bus down here. You could think of just a long wire. I'm going to put it like that. I'm going to put it here. I'm going to stop it. Then I'm going to stay in wire mode, and I'm just going to connect each one of these. And I'm just connecting each one of them, assuming that I'm going to make like this little kind of bus structure here. Now I could have just went 1 to 1, 1 to 1, 1 to 1, but this is a little bit easier to do. All right, there we go, done. And now we need a V sub CC. Let's go out of wire mode by pressing escape there. Here's a V sub CC, control copy. We could have just went up here, right, to power port in circuit elements and grabbed that, but we're not going to do that. We just copied it here, we already got it. And control V to paste it, put it right on there. Notice you get that little red X, which means there's a connection. So if I drag it around, there's actually a connection. All right, now we've got all of these connections here. We got R1 through R8. Now, we could just run wires. So I could just go like this, and this is going to go, let's zoom out so you can see it. So this is going to go to right here. This is going to go here. All right, so we can do this. So we can just go like this. I can go up, go like that, go like that. And I can sit there and run all these wires just like we did the other thing. Or we could put net names like we did here, okay? Either way is fine. It's whatever you kind of prefer. And also, if we run wires, it makes it harder to move things around because we've got to drag all these wires. But wires look cool, and it looks like something's connected. So we're just going to use wires this time. Now already, as I'm drawing this, I'm kind of thinking to myself, uh-oh, I'm running out of room. Right, I'm running out of room here. I might not be able to put all these, so I got to kind of drop this down a little bit, right? So that's already what I'm thinking. So, so now what I'm going to do is we've got these resistors here. I'm going to literally grab all these things. I'm going to drag them down, and It's not letting me do it, and I'm not sure why. Let me see. There we go. There we go. All right, so I put it down a little bit, and now what I'm going to do is I'm going to drag this wire, and I'm going to put it down. Can I put it down two little grid snaps? Just giving myself some room here. Okay, that looks good. Now, is this still connected? Yes. Okay, so that's good. So let's go back to wire mode. There we go. And let's connect the rest of this. And when you wanna make a turn, so like, I click again there, and that kind of stops the wire. I click again there. Sometimes the wire will follow, and there's actually different routing modes, so it kind of makes turns for you, and it's kind of smart. But you can also just, like, I can turn it. It's smart enough to realize turn up. See, I didn't click. I just turned up here, and it's kind of doing it for me. But I can click right here, and then click again, and then click again. Okay. All right. Right click. I'm done. There we go. We're all connected up. So let's Control S. So very nice. So we got our output here, going to our LEDs. All right. So let's put some labels here. So I'm going to grab that. Control C, Control V. I'm going to put this right here. I'm going to put this right here, and then we'll call these LED array. All right, what did I call it over here? Don't know. Let's find out. I call it LEDs for wand. All right, LEDs for wand. So right here, why don't we call it LED wand array? Okay, and then right here, this is a 3 to 8 decoder. All right, so we're just going to put 3 to 8 decoder. And what did I put here? Did I put anything here? We said 3 to 8 decoder LED driver. That's a little bit better, right? 3 to 8 decoder. LED 3 to 8 decoder driver. Let's put that. Okay. Don't have to make everything the same. Okay. So there's our circuit. All right. So let's zoom in a little bit here and take a look here. This is all good to go. We got all these wires here. Everything's good to go. And I'm pretty happy about this at this point. So now let's go ahead and let's take a look at the original here. Zoom out. So let's do a little let's review this. So we've got the batteries, we've got ground, the little short wire and the symbol means ground. So we've got grounds all connected to ground. We've got plus to minus, so this is in series, this is good. And this is going to be our kind of battery design. We got our switch, we got our capacitor, which is a bulk storage to V sub CC. All right, we copied that exact same thing here. Over here on the next component here is the 555 timer circuit, right, which we basically copy this. The whole point of this is we want two potentiometers to control our frequency, and then we've got this capacitor here, which is C in the equation, which we don't have here. But over here, we do. We have this nice equation here, the modeling equation, so we got that. Over here, we got these two 4-bit counters. We're taking the output from the 555, and that's going into this clock here. It's clocking this one. And then there's two timers in each one of these 393 packages. So the other clock, what are we doing with that? We're just tying that high. And these things are clocked on a negative going transition. So this will just statically keep this, counter doing nothing. And then we've got V sub CC connected to both these 14s. We don't really need to do that. We could just hook it to one. It's redundant, but that's okay. And then we've got ground hooked to both 7s. And then we've got clear, which is active high. We've got clear on both of these tied together, and then tied low. We don't want to reset or clear this ever. So that's it. It's just going to start free running and counting. And then we've got these net labels here. So these are ports. Remember, we got it up here, port. There's also net label. We can do that. So for example, we could just take a wire here. We could just run a wire out here. So I ran a wire, and then I can just go to net label. And then I can just go click this on net label. And now I could call this, I could call this A, unused. Unused, if I wanted to. And that is just like these. It's just not as pretty. And that's it. But let's not do that. Okay, let's just leave it alone. Okay, save. All right, and then so those three outputs go to the three upper bits of the counter, go to this 3 to 8 decoder. The 3 to 8 decoder then decodes it, and as it counts, it is going to turn on each one of these in sequence, which are then connected to the LEDs. Do we have this hooked up right? Well, let's see. We got ground here. We've got the two enables, E1 and E2. These are active low. Those are tied low. Good to go. We've got E3 here, which is active high, which is hooked up here to V sub CC. And we've got our bypass capacitor again. Again, if you're jumping around, why are there 3 different enables? It just makes it easy when you're building. Uh, uh, these decoder chips are used a lot when you're doing selection of memory, doing memory designs, memory architecture, or I/O space architecture. And so, for example, say you've got one bank of addresses that you want to turn on these memory chips, whatever these might be connected to, another bank of addresses where you want to turn on another set. Well, one pin, one I/O line might be an address. If it's high, I want to select this. If it's low, I want to select another. So if I just put that into one of these inputs, then I can put that same line into another one of the inputs, and I can turn the chip on in both cases depending on if that GPIO or that signal is high or low. So this gives me the option. I can have 2 different things low to enable it and one thing high, one input high, right? Or any subset of that, because I can just tie these high or low myself. So this gives you really good options so you don't have to use some external TTL AND gates and OR gates and OR gates, whatever, to kind of generate these chip selects or chip enables. So it's already built in, so it's very convenient. You'll get what I mean if you ever try and design some memory stuff, you'll use these decoders. Okay, so we got the 8 lines coming out. Oh, this one's ugly. Let's scoot this over. I just selected it, real easy. And remember, whenever you move anything, kind of just check it out. I just hit Control S. It's like a habit, constantly Control S'ing. All right, so we got all these. R1, R2, R3 up to R8, and we've got our D1 up to D8 LEDs. We've got the polarity correct, right? Here's the cathode, that's going to be negative. The anode's going to be positive. Remember, this is just a note for us, 5mm lead green. We can make them any color we want. You can make them any color you want. They just have to be 5mm and standard LEDs that are going to go, that are going to plug into the PCB footprint ultimately. Okay, so now, so now we are done with this, all right, and so our circuit is done. Now there's nothing to verify here, all right. So the computer doesn't know anything about electrical engineering. It doesn't know anything about embedded design. It doesn't know anything about how these chips are supposed to be connected. So there's really nothing we can check for right now, right? So we've got a design, and that's it. We just have to hope that it works. So I want to talk about 2 things. First, I've already brought up the fact that we did not simulate this, we did not build this, we haven't done anything. We're just assuming we're so smart we can just put chips down and connect them up and we're going to be correct. All right? Chances are we're not going to be correct. We're going to make mistakes, right? So that's why when you do embedded design, electrical engineering, what you want to do is, as you design things, you can use a PCB design tool or schematic entry tool to do your designs. But as you do this, you might want to take each one of these sections and build it on your bench or run it in a simulator. Ideally, do both, right? Therefore, you verify it works, and then you actually build it and verify that it works, right? Now, another thing you'll do is you will just, take paper and pencil and draw it. A lot of engineers still use paper and pencil to scribble down circuits. I do all the time. I sit here, I've got, if you could see all the pads I have of paper here, I've literally got probably 100 or 200 pads, this right here, on the ground with all my circuits. And I scribble things as I'm going through things just to see what's going on. Then I might copy it here or I might build it on the bench. So the whole point is, this is not the way that you should do your final design. What you should do is you can enter it in here on the computer, but then you should build it or simulate it to make sure the thing works. Because what you're going to do now is we're going to commit this to a printed circuit board. That's a lot of work. Then we're going to send it out for manufacturing, right? We're going to build the circuit boards or maybe even assemble the entire thing, and we haven't even tested the circuit. So remember, test as you go. Now, these are fairly simple circuits, right? So what we're doing, we're just learning the tool. Even if it didn't work and we made a couple mistakes, I don't care that much because right now I'm just trying to teach you how to use this tool. I'm not teaching you electronic design. I already taught that to you, right? So you can find the mistakes. But if you're going to do this yourself, please make sure that you build the things and you simulate them also. And you can't simulate it with this tool. This tool doesn't have simulation. So that's where you might use Proteus or some other, LT Spice, some other free simulator. There's lots of them, but you want to use a good one. All right. Okay. So that's that. So remember, we kind of want to go through and make sure that we're correct here. And that's why we go over this a few times. And if you've got a friend, I'll do this all the time. Even if they don't know that much about electronics or electrical engineering or embedded engineering, what they can do is they can at least look at the parts, right? they can look at the parts and, hey, this is a 74HC138E. They can go on to DigiKey, get the data sheet. Do you even have the pinout correct? Is A, B, and C, do those go to pin 1, 2, and 3? Even doing that much work helps, right? So even people that don't know a lot about electronics can actually help you, because I'm looking at this a billion times and I just see it a certain way. But someone else looks at it and they're like, hey, you forgot to connect ground, or ground's on the wrong pin. I'm like, really? Oh, wow, I didn't even see that. So, let other people help also. It's just really good to have another pair of eyes. But we're assuming we're not making any mistakes, and that's why we're going over it and over and over it, and we're trying to simulate it mentally in our heads, all right, to make sure that we think that this thing's going to work, and using reference designs for the 555 and using common sense, all right? So hopefully everything's correct. All right, now, so what we're going to do here is we're going to do one next step, and then we're going to stop the video and start back up. The next step that we're going to do is this. So we've got our schematic now. So we've got our schematic design, all right? We've got all the footprints. Every single one of these components has a footprint. So we don't worry about making a bill of material yet and building the thing. We're just still in the design mode. We know that we're going to have to make a bill of material ourselves and put the actual parts, the manufacturer, where they are, order them and all that, but that comes later. Now what we want to do is we want to make a printed circuit board. We want the actual circuit board that we're going to put this thing on. And I don't have any left here. I put them all away. So now let's use the same tool to do the printed circuit board. Okay, so how do you do that? Okay, so what we do here is this. So right now, let's go back up to this working copy, right? This Magic Wand working copy, the original we've been working off of. And you notice we've got two files here, the schematic and then this one that says PCB. As I click on it, it selects it. So what we want is we're going to build something just like this with all these components, roughly looking like this, right? Remember, here's a 3D view. If I press 3, I get 3D view. So there it is there, and I can rotate it around. And then I press 2, it goes back to 2D view. That has no effect in the schematic view because there's no 2D and 3D. It's just 2D information. Okay, so we want something that looks like this. So where do we begin? So the first thing we need to do is we need to create a PCB, all right, a blank PCB. Then we need to import all the parts and all the nets and all the information so we can start placing the actual parts on the printed circuit board, but we want that net information where things are connected to be part of the data structure so that we can then lay all the traces down and all that. So it's pretty complicated. All right, so how do you do this? So this is how you do it. So let's go back to Magic Wand Final Design. All right, so let's go here, and this tool doesn't select. So, a lot of little quirks on this tool that, upset me is, okay, now it's, see how now it's highlighted it. So, and now this is highlighted. So anyway, you got to kind of work with it. So we got this right here. Now, we want to go up here in the menu here. So we don't want to do any outputs. We don't want to do tools. We project, first let's commit the whole project here. And let's keep, you always want to do that. Remember, you can go here, you can right click and you can say commit, right? And so we just committed it. So now this has been grayed out. So everything's committed. So everything's up to date. Now, so look at this. Under project, we can say add new schematic or add new PCB or add existing document. Okay. Or we can go on the project itself here, right? We've got, now if you look here, there's 3 projects. There's Crash Course Electronics, Magic Wand Work Copy, there's Magic Wand Final Design, there's something I'm working on, Cardwino Boy. So there's 3 projects. Now if I right click on this right here, all right, if we right click on this, we should, there's an add new to project. See that? Add new to project, and we can add a PCB or schematic to this particular project, right? So we could add a PCB here, or we could add a new PCB here. All right, so either way you want to do it. All right, so let's just do it here, and we'll say, oops, we'll go here to the top of the project, right? And then we're going to say add new project, add new to project, PCB, click on that. All right, now file name. Whoa, let's slow down here for a second. All right, so what do I want the file, and you can change the file name. So Magic Wand Final, so that's what I want it to be called, Magic Wand Final. Now, it has the same name, but of course the extension is different. This is called CMP PCB Doc. Okay, so I'm gonna hit OK. All right, now, okay, so now I've got a blank PCB document. Now, So be careful with this. So now what I'm going to do is I'm going to zoom out, and this is my actual PCB right now. That's my PCB. There's nothing, there's no parts, there's no nothing. It's like empty space. It's just a blank data structure. All right. Now what we need to do is uh, the tool just created a circuit board, a printed circuit board, but it doesn't know that you want the parts from the other schematic in the circuit board, because you might have 20 different circuit boards and maybe only one schematic design, and maybe these circuit boards are just circuit boards. Maybe they have no parts on them. Maybe they're just the shape of something, or there's something that you're going to design just in the PCB layout tool, not even doing schematic entry. You can do that, right? So we've got to now tell the tool to import the parts, all right? So now we got to do that, and we can do that. There's a couple different places. So again, this is a webby kind of program here. So when you press things kind of weird, so you press these tabs, this kind of acts how you would believe it would act. But if you press File, you got to be careful with File. Let's do a Save All since I'm here. So if we go home, all right, there we go. So if we go home, and what I want here is this project, all right? And again, there's more than one way to do this. I can also do it down here, and I can do it here. But if we go to project, now check this out. Hopefully it's here. Again, let's commit project. And we didn't really need to do that, but it just created a PCB, and I like to commit it. That puts it up on the cloud. All right, we go to project. Now, add new PCB. No, we don't want to do that, right? Update schematic and magic import change. Okay, this is kind of what we want to mess with. So now check this out. So update schematic in Magic Wand Final Doc, or import changes from Magic Wand Design PR PCB. All right, so what we want to do here is we want to do this import. And what this is going to do is it's going to import from the schematic into this printed circuit board. All right, so we're going to actually import changes. All right, so watch this. Watch what happens when I do this. All right. So it brings up this dialog here. And again, we could also do this, I believe if we do from here, let's see here, recompile. I just want to see if we can do it here. And again, yeah, I thought we could, but up here at project, we can definitely do it. All right, so let's go here, import changes. All right, now what's going on here? So what this is showing, engineering change order, all right, and then again, forgive the confusion, all right, there's a lot of terminology and stuff you have to learn. What this is saying is we had this circuit board. You gave me this circuit board, it's blank. Now all of a sudden you want a bunch of components on it. Where do you want the components to come from? I want them to come from the schematic we've been designing. Oh, okay. What components do you want? I want all of them in this case, but maybe I only want a couple. So that's where this engineering change order happens. The whole idea is maybe I make a couple little changes and I don't want to add them all, so I can select what I want added or not, but we want all of it. And if you notice here, here's all the reference designators from all our components, right? There they are. And then there's all the nets. Those are all the connections to everything, okay? So I want all of this. So the first thing is, okay, click here to review them before continuing. Okay, so errors occurred during compilation of the project. So review here. And let's see here. What's wrong here? Let me close this. All right, duplicate designator C5. Okay, so one thing you can do is this. Let's go back here. So I sort of lied to you. And let's make sure which one we got here. We want the Magic Wand Final. Now, I told you that there's really no error checking, right? There's really no error checking because it doesn't understand electronics. The tool does not understand electrical engineering. But what it does understand is strings. So if I call this U1 and I call this U1, I probably didn't mean that, and it's going to be hard for it to import two U1s to the printed circuit board. Now, in this tool, it's not called validating the design, it's called compiling, which is a really bad word. So what we have to do is we have to compile this design, and that just tests it, it checks it. So let's go back. Here's the schematic. Inside of our project, we're going to right click, compile document. All right, so we can compile document. All right. Okay, so it compiled the document, and now it's saying extra pin U15 inferred normal part of U1. All right, so let's see what's going on here. U1, so here's U1. It does have a pin 5, so it shouldn't be causing us any trouble. Compile document. Now All right, so let's forget what this thing says. Let's go up here. So extra pin U1 inferred in normal part of U1, U1 alternate 1 of U1, U3-4 normal part of U3, extra pin. Okay, these are all warnings. So warnings are okay. So forget the warnings. All right, and I'm sorry this thing's kind of covering this up here a little bit. Do we have any errors? Yes. Here's an error right here. Let's let this thing shut up for a second. All right, so it says duplicate component designator C5. All right, that's a problem. Don't worry about the warnings. All right, so C5, okay, so it just looks like C5 is a problem. This other stuff, it's confused and it shouldn't be. All right, so C5, apparently we've got two of them. So here's a C5 right here. Now look over here, we copied and pasted it and put it right there. So that C5, we forgot to change that. Okay, so this is good, it told us this. Now, if you've ever programmed, which I'm assuming you have, you've played with compilers, right? C compilers, C++ compilers, assemblers, whatever language it is you like, you get errors and they're cryptic, right? You're like, what are you talking about? This tool, way more cryptic, all right? So silicon tools and printed circuit board tools and schematic tools are way worse. It's like you have no idea what they're talking about because they have no idea what they're talking about. The reason why is typically these tools are very old. This tool probably started, I mean, frankly, this probably started in the 80s, maybe even the 70s. We'd have to look up when Altium created this thing in the first place. So this has got software probably 30 years old inside of it. And it's got all this error handling, and these errors get percolated up through the chain of, the stack as things happen, and then it prints out. And a lot of times you get very cryptic errors. Now that was a good error. It said duplicate part number. That's pretty straightforward. But a lot of times all those warnings generated and this and that, they don't seem to make a lot of sense. So you got to figure it out and bear with it. But errors we want to fix. So C5, let's go ahead and change this to C6. Real simple. C6, I double clicked on it. Okay. There. Now there's C6. Let me zoom back out. All right, that was the only error, so let's go ahead and let's do a save. Let's go back to the project. I'm going to right-click on this. I'm going to commit this just in case I crash this tool. Right, I'm always worried about crashing. It's not just about Windows. Linux crashes on me. OS 10, Mac crashes on me. I got a Mac right there, crashes all the time. When you start using computers with engineering tools, they crash. If you just want to use them, for browsing the web, maybe they might be a little bit more stable. All right. Okay, so here we go. We committed it. Now let's go ahead and let's try and compile it again. We'll try and compile the project, compile the PCB project, or recompile it. Okay, and that looked like it was happy and nothing happened there. All right. So let's try this. Now we're going to compile just the document here, the schematic document. So I just right-clicked on that. All right, and it seems to be happy and it's not doing anything. Okay, so now we're ready to go back to project here, and let's go to this. Notice in our printed circuit board, there are no parts. I'm going to zoom out. Remember, this represents the PCB. It's just right now an abstract rectangle of some size. We can make it bigger or smaller or reshape it. But right now it just says, I'm just going to pick this for you so you have something to work with. All right? Okay, now let's go back up here to a project, and we're going to say import changes from Magic Wand Final Design. Here we go. All right, again, here they all are. I want all of this. I want every single one of these parts inside of my design. And again, I'm eyeballing it, C1, C2, D1, R1. All right, looks good. So now what you do is you say validate changes. Notice there's no errors now, right? Validate changes. I want to say validate all of these changes. And again, it's doing this cloudy thing. This is a very fast computer, but with this, it has to do things. And then we say execute changes. Now it's copying all these nets and all these components. Now we say close. Now, all right, so now we are where we wanted to be. So I'm going to zoom out. I'm zooming out, control, and then my little mouse wheel. And there we are. So there's all the parts. There's our 3 battery holders. There's our ICs, U1, U2, U3. There's our resistors. There's our LEDs. That's it. That's the whole design. Now, we're going to go and shift gears from schematic entry and electrical design to PCB layout. Whole different subject now. So now we got to learn a whole new set of things to do and way to do things. All right, so that's what the next lectures, plural, are going to be about as we lay this thing out. And one thing I want you to keep in mind is this is as much science as it is art. Things have got to look good and fit good and be mechanical, and you know, we got to take into consideration industrial design, or maybe plastics or housings, or if we're making a product, how is it going to be used, how is it going to be manufactured. There's so many things, and again, as I do this, I'm going to be talking off the top of my head and just kind of babbling about it like I do, to let you know that information. But we're not just going to plaster these things down, because if I just took all these parts and plastered them all down, I would have a big rectangle and I wouldn't have this pretty thing that looks like, you know, this. This is what we want to kind of get, something that looks, you know, like this, right? And then imagine plastic around here, right? And then, you know, here's the switch. Maybe we could move the switch to a different place or whatever. Maybe we could rotate these chips if we want, but you know, this is kind of what we're trying to get here, all right? So let's get out of that view. Let's go back here. All right, so let's stop the video here, and then we're going to pick it back up, and we're going to start moving all these parts one by one onto the printed circuit board itself. Okay, so let's save it, Control S. I want you to go ahead and I want you to go to Project, and I want you to say Commit Project. Make sure it's committed, and then I want you to look over here, and I want every one of these little things green. And yours, you should just have, you know, you shouldn't have this Arduino boy here. You should just have green, 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 green. And everything's green, you're good to go, and we're going to stop here. So let's go ahead, stop, take a break, and then come back in the next video. We're going to start moving these parts and building the printed circuit board. All right, so I'll see you then. Bye. Now, let's go ahead and let's shrink. So right now, the board itself, we could make this a little bit smaller, but let's not do that yet. Let's grab these three components, and let's just move them up and just center them a little bit. Okay, so I just selected them all. I'm just trying to center them a little bit because we're going to change the board shape and tighten it up later. All right, now here we go. So we've got C1 and we've got the switch one. All right, so depending how we want to orient this thing. All right, now in the other one I oriented it one way. In this one we can put the switch right there, and we could put the switch so that maybe we'd do this. So maybe we put the switch like this, put it sideways. All right, and then we zoom in, and so when the switch is in this position, that will be on. All right, so when it's in this position, because I can see here's where the two nets are. This one is open, so when the switch is over in this position, it'll be on. So on is usually like up, so up towards the light. So what I'm going to do is I'm going to rotate this around. All right, and then I'm going to give myself some room for my thumb here and put it like that. So the switch is going to be on when it's in this position. Great, now here's this capacitor. And now what I'm going to do is I'm just going to put this capacitor right here. And now remember that capacitor is going to be standing up. All right, let's take a 3D look real quick. See that capacitor is standing up? Whoa. There we go. The capacitor is standing up right there. Now, so maybe what we want is we want the switch perfectly in the middle, and then maybe we can put the capacitor here, and then what we'll do is we'll bend the capacitor leads down. All right, so let's try that idea. All right, so what we're going to do is we're going to put the capacitor put the switch right here, okay, maybe right there. And now what we're going to do is we can put the capacitor here, all right, and so it would be sitting right there. And then now what we can do is let's rotate it a little bit. So we're going to rotate it like this, all right, and then what we're going to do is we could actually even put it right here. Put it right there. And now in 3D, let me show you this so you can kind of understand what I'm talking about here. So in 3D, what we're going to do here is when we place this capacitor, we'll solder it in a little bit high, and then we'll bend it over flat so it'll be nice and flat. All right, so you kind of see what I'm talking about right there? So that's what we'll do. So even though this 3D view shows this, okay? So that's what we're going to do. We're going to leave that like that, which is different than if we go here to our other guy. Here's how I did this one. All right, and if we go into 3D view here, you can see in this case, I just put it like this because it didn't really matter that much to me. All right, okay, so let's go back here. Okay, so now we've got our batteries in here, we've got our switch in here, and again, we're going to mess with final positioning as we go. We don't need to worry about it too much right now. Okay, now the next thing we need here is clearly we've got all these LEDs here, and then depending on how much space we want, so let's just grab the LEDs and just drag them down here. So if we want them that close, we have enough space, but the other board was about 14 inches long, right? 14 inches. So in this case, let's go and make this board a little bit bigger. So we're going to go to home here, and we're going to go to board shape, and we're going to say edit board shape. We're going to back to editing board shape here. All right, and oh, we touched it. Let's try it again. Edit board shape. All right, here we go. And now one thing is when let's zoom in here. When I grab this like this and I pull it, I can't go much farther than right here. All right, so it doesn't want me to do that. All right, so what I'm going to do is I'm just going to undo that, and I'm going to move it and make it bigger from over on this side. All right, so we're just going to go like that. All right, now let's see here. Okay, now let's go ahead and grab all our components here. I just grabbed them and selected them. And again, we're just kind of eyeballing things at this point. Just eyeballing them. All right, that's not too bad. Okay, and now we look like we have more space here. Okay, so this kind of is going to fit a little bit better. All right, now let's go ahead and we can roughly put our LEDs down here. So we're going to put our LEDs here. All right, and then we're going to go ahead and space these things out. All right, and now we've got all these ICs that we've got to kind of fit in this region right here. So the question is now, how do you want to space out these LEDs? How do you want to space this stuff out? Where do you want to put these resistors? Now in the other design, again, let me show you. I put all the resistors here on the sides of the LEDs. Then I put those 3 chips right there. Okay. So in this version, we're going to do something similar. All right. But let's first put these kind of LEDs where we want to put them. Now, wherever the LEDs are right now, it's going to be difficult for me. Now, there's a way to position objects inside of the tool. But for now, let's just do it manually. So right now, grid snap is on 10 mils. So let's go ahead and let's make it 25 mils. All right, so we've got this much larger grid snap now. Now what I'm going to do is, if I go ahead and grab all of these and I move them just once, all right, twice, 3, 4, so you can see I'm on this other grid here. All right, and then if I grab this one, and you know, I kind of like its position. Now the second, you got to be very careful that you don't get off a grid. All right, and now what's happened here is, as we did that, we got off this grid snap here. All right, so we got to be careful. So let's go back here and let's go back to 10. Yeah, go back to 10. All right, let me grab this. Let's move this up right there. Now let me see. And I'm just using this rubber banding, and you can see I'm still slightly off this grid snap. All right, so now we're gonna have to go even smaller. And then this happens, you get off the grid, and then it's hard. There. Okay. There we go. Now let's go back to the 25. Okay. And all I'm trying to do is just space these things out so there's a good enough space between them. All right. And again, I'm not trying to copy the previous board exactly. We're just kind of making it. The whole idea is to make this our design here. And right now I'm eyeballing this. I'm eyeballing this and I'm counting in my head here. All right. And sometimes it just gets off and you can't adjust it. So then you have to change what the grid snap is and get it back so you can properly adjust it. All right. So let's go up, up. And even on 10 we can't get it, so we're going to have to go to 5. And now some people don't look at this detail, but it's important. Okay, let's go back. Now let's go to 10. All right, and now when we look at these, we can see that we've got some different distances in here. All right, so what I'm going to do is I'm going to, this one is kind of close to the edge, so I'm going to bring this one in a little bit here. All right, now what I'm going to do is I'm going to measure all of these and adjust these so that they're all the same distance. But right now they're close enough, so I'm not going to mess with it. This is, remember, we're just trying to get rough positioning of things right now. Okay, so now it looks like we've got our batteries here. And do we have enough space for all these different components? We know the resistors. We know the resistors. Let's select those. Let's move those over here. We know the resistors are going to go by each one of these LEDs. All right, so we can hold off on that for a second. Now, what I'd like to do is I would like to build up each one of our little circuits here. So let's go back to our schematic. That's our reference. All right, so the first thing is if we look at the chain of a data flow, we have this clock here. The clock is going to generate a clock signal. It's going to go into a 4-bit counter. The output of the 4-bit counter goes into a 3-to-8 decoder, 3-to-8 decoder. The output of the 3-to-8 decoder goes into each one of these LEDs. So basically it's 555, 4-bit counter, and 3-to-8 decoder. So why don't we build the circuit in that way, all right, going towards the LED. So the first thing is let's put down the 555 timer, and what goes with it? C2, 3, 4, pot A and pot B. C2, 3, 4, pot A and pot B. Okay, easy enough. So here we go. So C2, 3, and 4, so C2, C3, C4, U1, that's the IC, and then here's our two potentiometers. All right, and then these two capacitors obviously go to these chips. All right, so here we go, and we're going to do this from right to left. All right, from right to left. All right, so let's go ahead and place this U1 down here first. We're just going to roughly place it here because we're not really sure where we're going to put everything yet. All right, and I've already decided to put things in kind of a vertical orientation, otherwise the PCB gets too long. So let's stick to that. Now let's go back here. All right, and C3 and C4, these kind of go on pin 6 and pin 5, and C2 is on the power, which is on pin 8. So let's deal with C2 first. All right, so C2, and typically what you'll see people do is you want to have this decoupling or bypass capacitor as close as possible to the power pin, right? That so it can do what it needs to do, right, and bypass that noise. So typically you'll see us put the IC, the capacitor, right next to the power pin, and you can see the. Now, let me show you this. Let's zoom in. Here's the V sub CC pin right here. All right. So I would put the capacitor right here. We could do that. Or another thing we could do is we could put it up here. You'll see this technique where it's kind of right above it, a little bit off to the right. And why we do that is if we put it right over it, we'd flip it around like that. It makes routing a little bit hard because sometimes you want to come straight into the chip, and these pins make it a little bit hard because you don't have a lot of space. So you can do whatever you want. And this time, let's just go ahead and we're going to put it right. We're just going to put it right above. Just like that. We use that kind of convention. And that'll give us a little bit more room to route in here. All right, so we're just going to do it just like that. Now, notice the reference designator. It's sticking out. I don't really care right now. I can move this around, and I also can change the size of the font. So, we'll deal with that later, and we can put this in here. This is just text printed on top, painted on top, so it's not going to affect anything electrically. It just helps the design so you can see where to put the parts later. All right. Okay. So we got that. We got that. Now let's deal with C3 and C4. All right. Again, as I grab the part, the nets are displayed and they show where things are supposed to go. And I kind of flip things around with the space bar to kind of orient things. Now here's where you got to kind of figure out where you want stuff, right? So there's C3. Now let me zoom in. All right, so see net C3, and then ground. Now, one thing, we are going to do a ground fill on this entire board. So that means that we don't need to worry about grounds. We're going to get that for free by the fill. The fill is going to fill everything up, and everywhere there's a ground, it's going to touch. I'm going to show you how to do that when we get to it. So for right now, don't worry about ground, just worry about the signals. And the signal is this net C3. So if I put this right here, then we can, it's going to route very cleanly right there. That's all it's got to do. A wire's got to go from there to there, problem solved. All right, so let's just leave it there for now. Let's grab C4 and grab C4. There we go. All right, let's zoom in. Okay, let's move this little C3 reference designator. All right, and the C4 reference designator, let's move it too. Not sure what's going on. All right, so there's net C4, so I'm going to flip this around. Now look what happened. Okay, the reference designator got flipped. That's okay. We'll just put it over there. All right. And then now we'll go to the reference designator, and if we right click, now we might even be able to, if we go like this, I'm going to grab it and select it. Once it's selected, I can hit spacebar and rotate it around. Also, if you double click into it, you can go here, and then here's the rotation. You can change the angle here if you want to 90 or something. So if I change that to 90, see how it did that? So whenever you click on an object, you can get all its properties. There's its properties right there. You can mess with it in the object inspector, or if you double click, you can get this up here, or you can right click and you can go to properties. That gives you that, or you can right click and you can go to options, and in this case, it doesn't do anything for this this element, but there's lots of ways to do things. All right, so now we have these two components here. I don't need this to be right on top of this, and also put enough space between components. So remember, a human being or a machine is going to build this ultimately. If a human being is going to build it, maybe you don't want parts so close together. If a machine is going to build it, your manufacturer can tell you what's the closest you can put through-hole components or components in general. Remember, a little gripper is going to have to go down and grab parts and place them on the board. So typically, kind of a rule of thumb is don't put parts any closer than about 10 thousandths of an inch. All right. So right now we're on a 10 thousandths of an inch snap. So there's the two parts right on top of each other. So if I grab this, right, there's 10 thousandths, there's 20 thousandths that they're apart, right? So, you know, I'm going to maybe put it at 20 or 30 thousandths. So that's as close as I'm going to want it to get, all right? And again, because of the outlines here, it's a little bit nebulous where the actual component is. And remember, the components aren't exactly the size of this. This is just a representation. But if I measure this from here to here, that right there is 20 thousandths, right? Because this little snap is 20 thousandths. So maybe I move it down there. Now we've got almost 30 thousandths between the two parts, and they should be okay. They're not going to collide with each other unless these capacitors are really large. But just kind of keep things a little bit away from each other. And like I said, 10, 20, 30 thousandths is kind of a good place to start. All right. Oh, we've got this reference designator here. I don't really like where that's sitting. We'll just put that right there. Okay, so now we got our capacitors. We still don't really know if we want them here. We might have to move them in a second, all right? Now the question is, where are we going to put those potentiometers? We got these two big fat potentiometers, pot A and pot B. So looking back at the schematic, we see that pot A is between pins 8 and 7, and then pot B is right under it, all right? So we can probably just stack them and give ourselves enough room here. Now, remember the way that these potentiometers work. The ones that we were looking at, I believe they had a screw on the top. The adjustment was on top. Now, but we got to be careful, because what if they're on the side? If we were to stack these like this, in 3D, you'd have these two cubes, and then you'd have the adjustment coming in on the side. You couldn't adjust this one. So you got to be careful. You'd have to put them like this. Then you could adjust them both. But if they're top access, then it's not an issue. So we got to be careful about thinking about things like that. Now, if we go to a 3D view, remember there's no models for these. There's just the footprint, all right? Okay, so here we go. So let's take pot A, and I'm just going to plop it right here, all right? Oops, I'm just going to plop it right here. And maybe I want to tighten this up, so I'm going to put C3 right here, and I'm going to put C4 right here. Okay, all right, so there's pot A. And you can see the net is turning on there. So that net and that net are right there. So that doesn't give us much room for the bottom one. So we know that we're in the right orientation here. Now I could rotate it around like that if I wanted. Let's zoom in a little bit. So this has got V sub CC, here's the net, and then this has nothing connected to it. So we could turn it like that if we want, but let's go back in. All right, let's leave it like this. All right, so we're going to leave it like that. There's pot A, and let's go ahead and grab pot B. All right, okay, and then let's grab them both and move them both up, just like that. Give ourselves a little room for routing, and later we'll make sure that everything's perfect on the board. So we got pot A, we got pot B, and maybe I want to do this because maybe I want to put them a little bit closer. So we just kind of do, for now, we'll just kind of do that. And then the switch one, this is a reference designator here, right? We're going to put some text later that says on and off and all that. Okay, now a couple of little annoying things. So see designator comment. this we don't need this. So this is part of this part, and but there was nothing there other than designate or comment. So we don't need to put anything there. So what I'm going to do is I'm going to select that. Now let me show you this. Whenever you have multiple objects laying on top of each other, what's going to happen is you're going to get kind of a layer menu. So I want this element, but the tool doesn't know, do you want this element? Do you want this element? Do you want this element? There's all these things stacked. So when I click on it with the left button, I get this. And so I have to kind of scroll and figure out what I want. I want designator and delete. Same with comment. I want the comment and delete. Okay, not hurting anything. Control S, we save it. We're good to go. All right, so now we're looking pretty good. So we've got our 555 timer circuit kind of squared away. And then now remember, I may grab this whole thing and just move it a little bit. Just move it a little bit, all right, away from the switch, because we got these other couple of chips. But we're in good shape space-wise here. Okay, let's zoom out. All right, so let's save that. Let's go to 3D view. We're going to press 3. All right. So we're getting someplace. Okay, so that's looking good. So let's get these other two chips down and let's get these resistors and kind of start placing things and then tighten the board up a little bit and then we'll route. All right. So anyway, let's stop here and then we'll come back and we will add those two chips in. Okay. Bye. All right, welcome back, and we're just continuing here with our PCB design for our Magic Wand. So looking at the schematic, we have placed the 555 timer. We've placed our LEDs, roughly our batteries. So now what we're going to do is we're going to place the 4-bit counter and the 3 to 8 decoder. All right, so first let's take a look at the 4-bit counter. So that's U2, and the only thing that's connected to it really is this C5 capacitor. So we want to just put C5 close to it, and then right next to it we're going to put U3 and C6. So C5, C6, U2, U3. So pretty simple. All right, so we're just going to place those guys right now. So let's go back to our PCB layout document here. So again, over here in projects, we've got our document Magic Wand Final Design, which we forked from our copy of the Magic Wand. So we didn't mess with the original, or I didn't mess with the original. And this would be like your forked copy right here, and you leave that so you have an original to work from to look at, and then you're going to go ahead and make a new document and not even fork it and just kind of create this on the fly. All right, so anyway, we're in the layout. So again, I'll zoom in here. Keep your eyes over here on the left side of the screen if you're trying to track what I'm doing with the mouse. We've got our LEDs, we've got our batteries here, everything looks good, and we've got the on-off switch, we've got our 555 timer. So now what we're going to do is we're going to place U2 and U3. And remember, the data or information or the signal you could think of is flowing from right to left. So the 555 timer is generating a clock signal, and then the signal goes into U2, which is our counter. Then the results of the counter output bits goes into U3. So we're just putting the ICs in some kind of sane order here. All right, so we're just going to take U2. And another thing, while we're here, let's see what grid snap are we on. So again, up here in these tabs, it's going to take a long time for you to figure out what all these things are. And like I said, this is not my tool. I don't use this tool. I use Proteus for my professional work, but I'm using this tool so you guys can use something that's free. And like I said, this is a really good tool actually, and there's no reason not to use it. It just does not have simulation, which is a deal breaker for me for my professional work. But anyway, so if we're over here in Home in Layout Tool view, then Grids and Units, you can see we've got 10 mil. And remember, that's not millimeter, it's mils as in thousandth of an inch. Millimeter is mm. So 10 mil is a good grid snap. If you get down to 5, it's a little too high resolution. You don't need that much precision yet. We're just roughly placing things. So we leave that in 10. And we're in imperial or English units. All right, and so let's grab U2 here. And we'll bring it down here. We'll grab C5. Okay. And now we need both of these chips here. So we'll grab U3. We'll put it right there. Grab C6, put it right there. We're just trying to get stuff close so I can zoom in. This circuit board is very, very long. So the problem is when we zoom in, we don't get this nice full screen. We just get a little piece of it. So because it's so wide, right? nothing we can do about that other than use multiple monitors, but we can't video record on that. Okay, so we got the two ICs here. Now another thing I want you to get into the habit of, just as a convention and just as a way of doing things, is all the through-hole components on your PCB should be on a 0.1 inch grid. In other words, like if I were to take this IC right here and just place it kind of where I want it, right? So, maybe I say it looks good right about there. Okay, that's great. Now, if I were to sit here and measure from this pin to this pin, the x-axis, would it be a multiple of 0.1 inch? Probably not, right? Because I've just been moving these things all over the place. Another thing, notice how this pin doesn't line up with any pin, all right? So there's no alignment. So why this helps is because, for one thing, it's a good habit to get into, because if you have headers, things like that on the board that are 0.1 inch spaced, they'll always be in a place where you would expect them to be. Another thing is it just makes the board nicer and cleaner, right? So there's that's the whole point of having a grid. So there's no reason not to put things on the exact grid marks, all right? So again here, this is just a rough positioning, but on the IC, I want these things to be properly positioned. So again, we're going to probably take this in a little bit and take this in. You notice this board edge is right here on the 10 mil spacing vertically, but up here it's not, right? So we're probably going to take that down a little bit. So right now, looking at the batteries here, we see that the batteries have plenty of room here. So, and then we see that these ICs, if we look at the ICs, they're pretty big, right? So they almost go right to the edge as it is. All right, so it looks to me that we could bring this in a little bit here if we wanted to, but I think what I'm going to do is I'm going to actually bring it up a little bit and make it a little bit wider. All right, and that's just because these chips are so big, and I kind of want to have a little more symmetry here. So I'm going to actually bring this board edge up until it meets with that top edge. So we're going to go. So again, we're in home. And you got to search for these things and figure out where everything is. Going to take time, so just be patient. All right, so in home, we go to a board shape, we click on that, and then we want to not move, not redefine, but edit. Okay, so we're going to edit the board shape, and not sure why it did. It's doing something funky here. And let me see, let me go all the way out here, let me do this. Depending on the zoom level, it does, again, the tool's got its little idiosyncrasies. So I want to be able to grab this handle right here, but I want to have enough resolution to be able to see what I'm doing. So if I grab this handle and then I pull it up, now I've got it. So let me do undo. All right, so that kind of helped. Here we go. All right, so now my goal is, and you see, you just got to play with this. Here's this grid snap that's 10 mils. So I'm just going to drag this up to line right up with it. There we go. All right. And now it's on this 10 mil grid snap, 10 mil. So now the board is a little bit more symmetrical. Okay. And now looking here, if we click out of this, here's our battery, and we've got 1, 2, 3, 4. And here we've got whatever we've got here, 1, 2, 3, and some change. So I want this to be symmetrical. So I got what I got to do is I got to move these batteries a little bit. Move the batteries a little bit. So we're going to select the batteries, okay? And then what we're going to do is I just zoomed in, and now I'm going to grab, and I should be able to grab all of them. I'm just going to kind of move these up a little bit. Okay, so now, and let's get like this. So we got 1, 2, 3 and a half. We got 1, 2, 3, 4. So let's move this down like that. So now we've got 1, 2, 3 and a half-ish, and 1, 2, 3 and a half-ish. So that's good. So that's better. All right. And now that we move that a little bit, okay. So what I want to do now is see this center line right here. That's through this pin. Right. So that's kind of a center. So what I'm going to do is I'm just going to grab this rubber band here and see if let me zoom in some more. If I go like this and I put it through the center line, notice how it's missing this component. So this is it's just all about making things fit a little better. So I'm going to move this up. All right, I just want it to be a little bit more symmetrical. There we go. So now you can see as I rubber band, through this thing, right? It goes through the pins nicely, so it's on the same vertical position, okay? Now, like I said, we like things to be on multiples of, when you're dealing with 0.1 inch components, like these ICs, we really do want these to be on some kind of grid themselves so that the position of this IC relative to this is not some random number, but it's a multiple of 0.1 inch in both X and Y directions. So if we take a look, all right, so right now we're in 10 mil snap mode, right? Okay, so the first thing that I'm going to do here is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is 5, and this is almost 5. All right, so again, we don't have to get, too perfect here, but we could move that up a little bit. That's fine. Now what I'm more concerned about is, now look at this. I want to lay this right on here, okay? So I lay that right on there, and now what I want to do is I want to make sure that when I position this, I kind of position it so that it's a multiple of 0.1 inch. So what I'm going to do is I'm going to go over here to the grid snap and go to 100 mil. That's 0.1 inch. Now when I grab this, all right, so see what's happening? It's jumping onto this grid snap, which is the 100 mil. But because this one is not already there, all right, they're getting misaligned. So my option is to just grab this and touch it, and we could move it down a little bit. All right, so again, trying to get things on the proper grid snap. We'll go to 25. All right, and we'll move this. We're just trying to get these things semi in the same place. Okay, so we're going to leave it at 25 mils. Now, we know that if we go 1, 2, 3, 4, 1, 2, 3, 4, right? That's 0.1 inch or 100 mils. Now we'll go another 4. 1, 2, 3, 4. All right, now we'll go another. 1, 2, 3, 4. Okay, so now we go here, and now we're looking good. And now let's go up, and now we can just kind of eyeball. We just want to make sure that this is on the same Y position. So, yep, that's good. So I just keep moving this up. All right, like this. Okay. Now, so now when we look at this, we see that the chip is a little bit high. So our option is to move the thing down, all the way down here, right? Or just to leave it up there. All right. So now this again is a design preference. So if the board was a little bit bigger, right? If the board was a little bit bigger, then we would be able to have some space up here. But right now the IC is pretty close up here. But what's nice about it is everything is on this 0.1 inch, kind of virtual grid. We don't have to. I can take this now, and I'm in 25 thousandths, and I can go and put it right there. All right. Or I can put it right there. But you see it's not aligned. So the whole idea is this, is if your through-hole components, your ICs and whatnot, are all in kind of a decent grid, then it may make it easier for routing because you can do kind of straight lines. It may make it easier to position some components. It may just look better. So again, I'm just thinking out loud and I'm telling you how we do this. It doesn't need to be, but it's just something that you might try, all right? So anyway, I'm going to leave it here because it's kind of symmetrical. So now it's not on the 0.1 grid, right? We just kind of started there. Now I'm going to take this one, all right? And again, when I make the IC kind of the same size here, so 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7. This one, right, is 14 pin. This one is 16 pin. So I can't really align them and keep them. If I try to align the pins, then you see what happens. This goes up to the top edge of the board here because the board size is not big enough. So our only other option is try and be symmetrical. So I'm just going to kind of space it in the middle, and then I'm just going to move it over. And again, right there, they're totally aligned. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. At least that's 0.1 inch, right? 1, 2, 3, 4, and maybe 1, 2, 3, 4. All right, so now we take a look at it and we see what we got going on here. All right, so that's not bad. And then we might decide that we want our capacitors over here to the right. That's the only place we got them. So let's move this one more time. 1, 2, 3, 4. All right, so there we go. And we've got our LEDs there. Okay, let's Control S. Let's save that. Okay, Now let's put our bypass capacitor. First, let's move this reference designator. So I just selected it, and I'm just going to put it right here. All right, and same thing here. I'm just going to grab this reference designator because it's going to, print off the IC there if we leave it there. Okay. So the whole takeaway that I'm trying to get across here is when you're placing things down, make them neat, make them symmetrical. If you're doing through hole with 0.1 inch pitch, try and put everything on a 0.1 inch pitch grid if you can. If you can't, then don't. But the more you can, the better. And especially when you have headers, if you've got a header on one side of the board and a header on the other side of the board, and these things are not aligned on a 0.1 inch grid, what's going to happen is if you try to plug something into it, typically the thing you're plugging in is going to be on a 0.1 inch grid in both directions. It won't match. All right, and it's a problem when you're trying to connect things together. Right. Okay, let's put our capacitor here. All right, and now notice the you can see those yellow lines. Right, when I grab this, there's a green line and then there's yellow lines. Those little yellow or orange lines, those are the nets showing where the thing is connected, right? So we can see, if we zoom in here, this is V sub CC, V sub CC, and we're just going to put that right there, all right? And we're just going to put it off there a little bit, all right? So that looks good, and you can see that this capacitor here is a little bit lower, right? So again, we decided we're going to put this kind of up here because we have these other capacitors here. So all I did right now is I just moved it a little bit so it's lined up with this C5. And I'm just going to put this C5, maybe, no, I don't want it that close to the edge, so maybe I'll put it here. And again, when you're deciding where to put the reference designators, you're going to move these around a lot, but it's kind of like if you've got a couple capacitors next to each other, make sure you put the reference designators in a place such that you can tell what they refer to. All right, like if I put this one over here, probably you could figure out it's that capacitor, but it's better to have it close to it. All right, and then here I've got this one to the right. Here maybe I put this one up here. That's okay, but it's pretty ugly, right? So just try and the whole point is be symmetrical, be consistent. All right, and that's what we're trying to do here. All right, so let's grab the C6, and we're going to put it here, and maybe we're going to put C5 a little bit closer, just a little bit. Okay, and this is a little bit tight. I'm going to just bring this over a couple. All right, so that looks good. And just zooming out, seeing if I have room. And what's going through my head right now is I want to be able to route this easily. I don't want to work too hard. All right, we're going to route this with the auto router, but we're going to play with it a little bit in manual routing. All right, and so routing is it's fairly complicated, and you have to get good at it. It can take many hours. And in fact, a complex board could take 100 hours or 200 hours if you do a manual route on it, because it's a complicated problem, routing things in two-dimensional space. So for beginners, I suggest trying to use the auto router if you can, and unless the board is really, really simple. All right. Anyway, so okay, so we're getting there. So looking at our design, let's go back here. We've got our C6 here, and what I'm going to do is I'm going to put this under here because I don't really have any room. And now, since I'm going to put this one here also to be consistent with those two, all right? And this one here, I'm just going to, again, I'm going to put this right under here, all right? Just trying to have some kind of level of consistency. Okay, now the last thing are the LEDs. All right, so we have to kind of figure out what orientation we should have. Now, one thing that we don't need to worry about are all the grounds. Remember, when we do the fill, we're gonna do a flood fill, and we're gonna create a ground plane on the top and on the bottom of the board. We've talked about this, I've showed you this. Anything that's grounded, like right here, we're not gonna have to route. We're gonna get that for free, all right? We're gonna route power manually, the V sub CC. Now, remember, we talked about having 2-layer, 4-layer, 6, 8, up to 30, 40, 50, 60-layer boards exist. And in those boards, you might have an entire layer that's 3.3 volts, 1.8 volts, 5 volts, whatever, 1.2 volts, 12 volts, 6 volts. And you would route down in 3D to get to the power. So actually the power you never have to route in a two-dimensional sense. There's a whole plane of power. But we're not doing that because we don't have enough planes. We only have a top plane and a bottom plane, and we need those for signals. So we're going to use the planes as signal planes, and we're going to flood fill them with ground. So everywhere else there's not a signal, we have a ground, and that'll help us out tremendously getting our ground signals. Okay, All right, so D1, D2. All right, so that is about it. Now let's deal with our resistors. If we go look at the schematic, going back to the schematic here, where are our resistors? They are right here on the cathode side, all right, of each one of these LEDs. And then the anode side just goes up to V sub CC. So we know that the anode side is just going to be continually hooked up in a bus and a chain. And then the resistors are going to be on the cathode side. So that tells us a little bit. And then each one of those is just going to go to the output Y0 through Y7 of this U3 chip, pin 15 through pin 7 here, all right? Okay, so when we're placing those, let's go back here. Oops, sorry. Okay, when we're placing these resistors, we know that each resistor goes next to each one of these LEDs. And then the other thing was, we wanted to make sure the LEDs were roughly about the same distance from each other, right? And within 5 thousandths. We don't need to be too accurate. It's not like with your eyeball you can see, 5 thousandths of an inch. You can see 10 thousandths roughly, but it's very hard once you get, 5 thousandths, very hard for you to discern. But let's take a look. Now we can rubber band. So when we rubber band here, remember down here in the coordinates, now what this thing really should do is it should show a deviance, all right, a delta, and it doesn't. Maybe there's a way to do that, but right now the only way to get a distance is to go to Tools and go to Distance, all right, and we're going to zoom in here, and I'm going to go from this middle to this middle, all right, and so one thing I notice is the Y's are not even aligned. So watch this. Let's get out of that mode, press Escape. So again, I'm rubber banding here, and then look at that. You see where it rubber bands? So they're not even aligned vertically. So let's do this. Let's say that this one first. Let's make sure this one's in the dead center of the board. Okay. So from the top of the board, I'm going to basically measure from here. All right, from here. There's my measurement, and I'm going to go down to the center of this LED. All right, roughly, because of my grid snap, I can't hit the center, but let's just see what this is. So right now, we're looking at the distance, and the distance is right down here, okay, as the thing scrolls away, because no one thought anyone would ever want to go down there. Okay, so there it is right there, and the distance is 475 mils, or 12.0 millimeters. So 475 mils. Now, from this point, so now I'm going to go from this point to the edge of the board, all right, that's 425. So we're definitely not aligned here, okay? So we're not aligned. So the first thing I want to do is get this LED vertically aligned. So the board is now perfectly symmetrical, and if we can just count squares here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to that edge. And here it's 1-ish, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we need to move this one up, all right? So let's move it up, move it up. All right, now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and now of course this won't be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so now let's move this back down. All right, let's try it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks good. And now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's vertically, as close as we're going to get it. So that looks good. So now what we want to do is we want all these other guys to be on the same height. Now luckily now we're perfectly grid snapped here, so this is dead center, right? Okay, so now what I want to do is I want to move all of these guys here. So I'm going to zoom out and hope that if I grab all of these, and then we're going to zoom in, and now I'm just going to pop this up. Okay, and now notice because of the grid snap, I can't get it where I want it. So again, we got to go back to home. We're going to go to the grid snap. We're going to put this in 10 thousandths. And again, no one said this is easy. It's painstaking, but you can fast forward if you want or skip videos. But the point is, I want you to see this process. I want you to see the detail, and I want you to see how hard this is. And here's another thing: if you end up doing this for a living, designing circuit boards, doing schematic layout, being an electrical engineer, an embedded engineer, this is the real work, and it takes a long time. And when you tell a customer, hey, I'm going to do something so-and-so time, if you haven't done this a lot, you're going to grossly underestimate the amount of time it takes. It takes a long time to do this stuff. Now, there are tools to do this also. This tool has a way to auto-align things and auto-place things, right? and you can use those tools also. But again, you need to learn how to do this. So if those tools aren't going to work in your particular situation, you can still get something done. Okay, so now we've moved everything roughly. So now I'm snapping this down, and my goal is that every one of these is on the same line here. All right, so that looks good. That looks good. So that's beautiful. So everything is on the exact same vertical position. You can see the rubber band goes right through the dead centers of all these LEDs. If I were to go through here and go through here, okay, so that's good. Now my next problem is their horizontal positioning. All right, so all I'm going to do is I'm going to measure. Let's get back to tools. Where's our distance? So I'm going to measure from here. So I've got that measurement to this. We need to go from the same point, of course. All right, so we're going to, now this is a little bit off, so that's already concerning me. All right, so this says that this is 11.43 millimeters or 450 mils. 450 mils. Okay, so 450 mils. Let's go ahead. I want this to kind of be on dead center. So what I'm going to do is I'm going to try and move this part. I'm going to move it one to the left or one to the right. All right. So I just want to move it. So I'm going to move it one to the left or one to the right. Okay. Now I'm going to go back to distance because I want this to hit dead center. All right. There we go. So now that hit dead center. So now it's exactly 440 mils. Okay. From point to point. Here we go. So 440 mils. So let's do another distance. Okay. To this one. And this one is, where are we here? 430 mils. So this needs to move. So we're going to take this, we're going to move this one, maybe two. Yep. All right. And let's measure. All right, 440. Okay. So now I'm just going to sit here and continue to do this. Okay, so I'm done positioning these so they're as close as I'm going to get them without changing the resolution in the grid again. So that looks good. Okay, so now the next thing that we're going to do is we're going to place these resistors, and keep your eyes on the netting. All right, so we know that we're going to do it the exact same way. Now, if we look, let's look at our other board. Again, we're trying not to copy too much because otherwise we're not going to learn anything just copying. All right, so you can see how I staggered them, and that just made the routing easy, and I staggered each one of these resistors. Okay, all right, so we know that that's going to work. But let's see here. So if I take this resistor here, and we can see that the connection is going to that pin right there. Let me put it here. Let me zoom in a little bit. All right, and we can see that this net D1, here it is here, and then this net here is going over to the output of this U3 here. Okay, so we probably want to point it like this. All right, so we want to point it like that. All right, and we can put it like that. Maybe we could put it just like this. All right, we could do that. Okay, so that's R1. Now the other thing is it's kind of up here. So maybe we want to put it up here. And now what I'm going to do is see the space here and see the space here. I'm going to kind of just equispace this. And see this right here, that width there, I'm going to kind of make this centered here on the center line. These are all the things that I'm always doing, always thinking about. Now see this D1 here? It's kind of in my way, so why don't we just put that right there. All right, and we're going to put that right there. Put this right here. D4 and D5, D6. And again, you know, as you're doing this, you don't have to be ultra perfect. We're gonna clean it up when we're done, but we're just trying to get things where they go right now, roughly. All right, so there's R1. And now the question is, if I take R2 here, so it connects on that bottom there, and the problem is if I try to put it up here, it's going to kind of be on top of that. If I flip it around, I could do that, but there's just not enough room. So better to stagger these things, and so that's why I'm staggering them. All right, so now we centered that right there, so we're gonna do this kind of stagger, but we're going to center. All right, so again, I'm just centering this in this vertical space right here. There's 2, so I'm going to kind of put 2-ish, and then I'm going to center it. I'm going to center this body roughly, so that if I were to draw a center line right there, it goes to the center of both of these objects. All right, that's all. And now on the other one, if you look at it, I don't think I did that. On the other one, I think I aligned it, yeah. So if we go here to this view, yeah, so you can see what I did was I actually lined the pin right there instead of centering it, okay? And then on these, notice how I put the reference designators inside, okay? We'll figure out how to make these smaller in a second, all right? Okay, so let's continue and put the other resistors here. Okay, so we have all the resistors placed now, so that looks good. All right, so now what I'm going to do is I don't like the reference designators sitting up here, so I'm just going to drag them inside of each one of these. They'll fit, so that's okay. If they didn't fit, I might change the size of the reference designators, which we can do. And we can actually do it globally or we can do it locally. So we can just change the size of one. So for example, if we click on this, and you can see the height here is 60 mil. And then the width, we could actually change. We can just click on those numbers and change them if we wanted to. All right. The other thing we can do, and let me finish this. I'll show you a trick. But one thing that's kind of cool about this tool is you can select things and then you can filter what you select and then you can apply a change to all of the filtered items. So for example, let's get this in here. Let's back out. We're constantly looking at things, constantly evaluating things. Does it look pretty? Did we mess anything up? Is something in the wrong place? All right, so now take a look at this. Again, we've got to zoom way far out to get the width here. So I'm gonna select this entire thing. So we've got all of the components selected. Now look over here at the PCB inspector, and this is a really important little tool here. If you go to view, you see you've got projects and libraries. That's what's coming up here, projects and libraries. And then we have this object inspector selected. That's what's over here. Okay, so over here in the PCB inspector, or this object inspector, here it says include all types of objects. And it looks like a hyperlink. And I'm not a big fan of this kind of interface. But anyway, if you click on this, display all objects or display only, we click that, and then it will allow us to select, and this normally would have other things in it. So we could say only components. But since there are only components, that's what it's showing us. Now, if we look here inside of this little area, we can see graphical X, Y, height. So there's these different things here. And then what we're trying to look for is this text here. And I'm not going to do this right now because this may take some time to figure it out. But I think if we go to height, 200 mil, that might be the height of the text. Let's see here. Let's click on this and let's just make this 100 and let's see what happens. And that did not zoom in here. Select all of this again. Okay, object kind, text, so that's correct. Locked XY layer. Let's see, let's try this. Display only text. All right, so now we were able to, when I did a Control A to select everything, I was able to kind of get a little bit more what I want. So here's what we want, text height. And again, you got to play with this to figure out how to get it. So when I did this rubber band and I selected everything, all right, and we'll come up here and we'll say display all objects. When this was in this mode right here, all types of objects, then when I go to display only, it's only letting component be selected. But if we deselect all this and do a Control A, that selects everything. Now when we do include all types of objects and select it, now look, there's text inside of here also. So why wasn't the text in there before? I don't know. So now we can select text. Now we have the text. So now instead of the 60 mil here, we can change this to 50 mil. And that's going to change the height of all the texts. All right. And I don't know if you just saw it happen, but it did. And if I zoom in here, you can see that the text is a little bit smaller. For all of these, the width is the same, but the height is a little bit smaller, right? So that might make things a little bit easier, all right, to do. Now, if I press Control Z, it'll undo it, and notice how they just got bigger again, all right? So that's how you do things. So you can select everything, then you go to the Object Inspector, and then you can kind of sub-select what you want, and then you can go into its parameters and its properties and modify what you want. So, so anyway, or you can just do it one by one. But if you had a million of these, you could just double-click it, select it, and then go in here and change the height or the rotation or the width of the text. Okay, so right now they're fine. We're not going to mess with them anymore. Okay, so we have the entire board here placed. There's no more components. Let's move this SW1 here. I'm going to put this right here actually. All right, and on this BT1, I'm going to put this inside here. I'm going to put this in the corner. BT2 and put this in the corner. BT3, and again, I'm trying to put them in roughly the same place. All right, and then last thing, we have this designate or comment business here. This is just extra text when whoever designed this footprint added it. So we're just going to select those and delete them. Don't need them. Okay, we'll get this. And we'll get this one. And this last one here. Okay, now let's back out. Back out a little bit more. All right, so that looks good. Control S. Okay, so where are we right now? We've got our schematic done. We've got our PCB roughly laid out where we want everything. And then now what we need to do is we need to route this thing. All right, so we're going to route the wires that make this thing up. And we're going to start into that process. So there's a few steps that we're going to do, like we have to do these flood fills to get the grounds and a couple other things. So that's what we're going to kind of start working on next. So anyway, let's stop the video here and I'll meet you back in the next one. Next series of videos, we'll start working on the routing. All right, see you then. Bye. All right, welcome back, and we're continuing our coverage of the PCB layout of our Magic Wand. So we've got it here on Circuit Maker. Looking here at the screen, we can see the printed circuit board itself. We've got all the components roughly placed, and we could go in here and really fiddle around with things and maybe move things a little bit, but this is good enough for our purposes. Now another thing that we can also do is we can put text on here, right? So we can annotate this or decorate it with text and put cool text on it here and there. But we'll do that after we do the routing, just so that we can see a little bit better and not have everything obscured. All right, now, as I was saying before, there's two ways of routing. One is manual routing, where trace by trace we sit and we route the board ourselves. And to do this, this takes skill, and it also takes an understanding of, electrical circuitry and knowing what to do and what not to do. For example, if you have signals on a data bus or some kind of bus that has similar signals that all need to be at the same place at the same time, you would run these signals all parallel to each other and try and keep their track length, or the length of each one of those wires, the same, so that as they propagate down the wires at near the speed of light, usually 0.7 the speed of light, they all arrive at the same time, so that you don't get what's called signal skew. All right. Now, so that's one thing. Now, another thing is if you don't want noise on one line induced on another line, you don't run those lines parallel, you run them perpendicular. Another thing is when you are doing a two-layer board, for example, you select direction and orientation to route your wires on the top layer. Maybe they'll all be horizontally, primarily, and then on the bottom layer, they'll all be vertical, primarily. And this gives you more routing options, because if you run them both in the same direction, then what happens is you trap yourself. So there's lots of information on this, and again, I want you to read my book on this. Let's get back here, and let's see, hardware construction techniques. I think it's in this, let's see here, hardware construction techniques, I believe in chapter 5, and let's open up the table of contents. Yeah, printed circuit board. So in chapter 5, starting roughly here on what about page 34, talks about different routing techniques and things like that. And we've been over this ad nauseum, so please read the book, chapter 5 on hardware techniques, specifically the PCB layout stuff. All right. But other than that, you're going to learn this from doing it and just from, reading white papers and reading various books. All right. So the first step that we're going to do is we need ground planes. All right. Now, there's a lot of information on why you put ground planes and white papers and whatnot. And primarily what we want here is we want a place for all the ICs to have a ground and all the components to have a ground. We're going to do that on the top, and we're going to do that on the bottom. Also, the ground planes also help with heat sinking of the board. They also help with stray capacitance of the board. They also help with the electric field and magnetic field of the board at the edges. It has some place to come back to. It also allows a current path for as charge is moving through the traces on the top layer. If there is a ground plane under it, it gives it a place to capacitively couple to, so the field lines don't spray out into space. There's all kinds of reasons why you want to have ground planes, and it creates what's called a Faraday shield also, so it traps the electric field and magnetic field. So that's why we're going to do that. All right, so you can read about that. Now, when we are in design mode here, we need to figure out how to do this. All right, so as I said, this is not my primary tool. I use Proteus, which we've used for simulation and all that. So again, you got to kind of figure out, what to do and where to do this and how to do this. And there's usually more than one way to do it. There's, no right way sometimes. There's many ways depending on what you want to do. So again, you go through the tabs here, and views, usually not what we want. Project, not what we want, but could be. Tools, possibly, right? That sounds like a tool to me. In tools here, the auto router is actually here, right? Now, over in home, we have this polygon pour over here it's just in this one little area panel called pour. So to me, that's improperly placed, but you can move these things around also. All right, so what we're going to do is, now also over here, there's a place, and but these things, a lot of these things are just objects, geometrical objects that can be placed on a layer that then can represent something or be tied to something. So fill, that kind of sounds like something we might use, right? It's a ground fill, right? And so that is something that we could use, but it actually doesn't do what we think it does. All right, so what we want is polygon pour. All right, so what we're going to do is you click on it. You can see it's got these different options here. But what we want is we're just going to click on the object itself, the top here, the top icon. It's going to pop up this dialog for us. Okay, now there's a bunch of things that you need to understand to be able to do these fills. So what's nice about this tool is it's actually showing us with little arrows kind of what these things mean. Otherwise, you have to look them up, right? And depending on the manufacturer and depending on the country that the tool is from, like over in England, Great Britain, they will refer to things in different ways. Europe will refer to things in different ways than the United States will. So sometimes they use a term or something. You're like, what does that mean? You have to look it up in their tool to see what they mean. All right, and sometimes they just make stuff up. So that said, here where I'm moving the mouse around, this is showing what a ground connection would be. So say this pin right here is going to connect to ground. So see this filled area here? This is a ground fill, and then this is how it's going to connect. Now see how it's connecting with these 4 little protrusions? We can control the thickness of those protrusions. We can also control if it's a completely solid connection also, right? And so if it's solid, that's going to make a really good connection, but then also thermally, it's going to be very hard to solder on that if we had to solder on it. So there's different ways of doing these connections. So we're gonna stick with this kind of X method or cross method. All right. Now, there's this other little thing here with this little arrow. It says remove islands less than 2,500 square mils or square thousandths of an inch. What this means is the flood fill is going to fill, or the ground fill is going to fill in these little areas. Now, ideally, we want it to be always connected to itself, so it's always connected. So what this is saying is, well, I could fill this little area with fill right here, but it's not connected to anything. It's an isolated island. So the word island just means it's an isolated piece of copper. So it's going to help you with shielding. It's going to help you with heat dissipation. It's going to help you with a lot of things, but it's not going to help you with ground, right? Because it's not grounded unless you were to punch a via through it and ground it. So what this is saying is remove islands less than this much because I just don't even want them there. It's not even worth it. So we are just literally going to leave these things the way that they are, all right? Okay, and we're not going to mess with anything. Now, the couple things that we can mess with, see this hatch tracks in solid? Now watch this. See what it does? You ever seen a printed circuit board like this that's hatched? This gives you a ground plane, but it uses less copper, right? So it uses less copper, and it has different properties you might want to do this with, and it's cheaper, but I would just always make it solid, all right? And then also you can do none, and look, it's outlined these areas, all right? And that's another option, all right? So hatched, solid, those are usually going to be your only two options that you're going to use. Hatched you might use if you're doing some capacitive switches. You might want a ground plane under them, but you might not want it completely solid, all right? Anyway, we're going to do solid. Now, down here is where we have to make some decisions. So the properties, first, it's going to create a name of this ground, of this pore. And we can connect this pore to any signal layer, signal net that we wish, all right? It doesn't have to be ground. It could be a power net, it could be a signal net, it could be anything. So it's on the top layer, so we're going to do a top layer, and the net is going to be ground, GND. So this is just an English name. Put whatever you want, all right? So top layer, ground. Now, where do you want to connect it to? Bottom layer? No. Outline? No. So I scroll through here until I find the layer, top layer. That means the top copper layer. And that's improperly named. It should be top copper layer, right? Over here, under net options, it says connect to net. What net do you want me to connect to? And then every single net in your design, there's none in here. I mean, look, there's like, I don't know, 20 of them, 50 of them, 30 of them, 30 of them maybe. There's just so few nets. Very simple design. We want the ground net, okay? All right, remove dead copper. Now what this will do is any copper, so it's going to do this fill, and then after it gets done, what it's going to do is it's going to run an algorithm that checks if there's connectivity from every region, all right, in the fill, to every other region. Every region that's not connected to ground is dead copper. It's going to remove it. We're not going to do that right now, but that's an option you can do. All right, lock primitives locked. We don't want to mess with any of this right here. Okay, now we're going to do this graphically, and we're going to hit OK. And then what we're going to do is we're going to select where we want the fill. All right. Okay, so I'm going to hit OK, and I'm going to very carefully. I'm going to zoom in here. So zooming in with control in the mouse wheel. I'll turn the little, I always forget to turn the darn little mouse keyboard indicator on because it crashes all the time. So now notice what I'm doing here. I'm putting this right up here in this corner, and now I'm going to click with the left button. And then now, say I've got this kind of very sketchy, bizarre algorithm they've got running, trying to figure out what region, what line I want to select. So just bear with it and just move to the right side. So we're going to go all the way to the right side here. We're going to scroll out, and you got to be very careful because you press something wrong, you'll exit the algorithm or the selection process. So I got the mouse over to the right, and as I do that, it scrolls. Okay, now I'm going to zoom back in. Now, see how I got to be very careful here? I got to get it right on this vertex. Okay, there. Now, and then there's a little orange line. You may not be able to see it, and this is really weird. Now, see, I'm not used to this. So what's happening is, see how it's running this diagonal line out here instead of a straight line? The reason it's doing that is because it's making everything at like 45-degree angles. So if it were to run a straight line, like many of your art programs you're used to when you do a selection or a polygonal selection, it'll have a straight line. But notice this doesn't have a straight line. It creates two lines. One is 45, and then the other lines are either vertical or horizontal. So keep that in mind. It's just doing that because it wants to keep things a certain way, which is only 45. Very carefully get that vertex click. All right. Now it's trying to finish up now. So it's got enough vertices to create a polygon. 3 vertices are the minimum you need to create a polygon, yeah, right, a triangle. So it's going to look like a triangle. I'm going to zoom out here, and I'll zoom out a little bit more. All right. So it's saying, hey, do you want this triangle? No, we don't. We're not done yet. So let's come down here and we're going to click on this corner vertex here. There we go. And now it's saying, okay, you see that line right there? It's finished and now made a quadrilateral, right? And that is what we want, all right? So I'm just going to finish up and I'm going to put it right up here in this corner, click, and then I'm going to right click. Now it's done. Okay. So now we have that flood fill, all right, or ground fill. All right, now I'm just going to click here into white space or gray space. And now when we look at this, if we zoom in, anything that required a ground is going to be grounded, right? So let's look at our IC. So for example, U3, where is the ground on U3? Well, we can go back to the schematic, but typically on most TTL chips, ground is on the bottom left or you know, like pin 7 on a 14 pin or pin 8 on a 16 pin. So anyway, pin 8 on the 16 pin and pin 7 on the 14 pin, exactly where we would expect. So let's go see if it is grounded. Aha, it's grounded. There it is. So there's a ground. So that's cool. And then there, that's grounded. There's another ground there, another ground there. Any place there was a ground, you're going to see that ground. And there it is, just like I said, in that little shape, ground, and you'll see that little shape. Okay. So now we have all those grounds. So that's cool. So let's save that. Let's look at our batteries also. Now, if we look at our battery circuit, let's go look at our battery circuit up here. So what do we have? We've got these batteries in series, B1, B2, B3, and the only one that's grounded is B3 is grounded, then B1 is going to go to our switch. So B3 better be grounded. Let's see, is it grounded? So let's scroll over, and sure enough, B3 is grounded, right? So that looks right. So then there's the plus, and then here's the minus of B2, right? Right? But it's not grounded because it goes to the plus of B3, right? Because it's all in series. Okay, let's continue working. Let's go fix this real quick here. Let's turn this little annoying thing on. Now, so we have our ground plane. We could stop there if we wanted, but we're not. Let's put another ground plane. So we're going to also make the bottom layer a ground. Also, we want that. We want to sandwich it inside of there. Now, we could make it a positive if we wanted to. We could make it a power plane. And then we could route in it also, but I prefer to make them both grounds and then route and place signals in them as well. Now, let's talk about the layers here again. So right now we're seeing multiple layers. We're seeing the ground plane, which is the top copper. We're also seeing the text layer here, right? What if we only want to see one layer at a time? So what we can do is we can go into single layer mode, which I can't remember, I believe it's S, but we can find it another place. If we go here, we go to tools, no, we go to view, yeah. We go click here, and then yeah, it's Shift S is single layer mode. So if we hit Shift S, so now it's in single layer mode. So only one layer at a time will be visible. And then what we can do is we can go up and down the layers. We could click down here. Here's the layer stack. We could click down there. Or we can go up and down with plus and minus, I believe, on the keyboard here, on the numeric keypad. So there we go. So as I do this, you'll see at the bottom, I don't know, I'm going to point my finger down there. There's the mouse. You can see down there that it's going through these layers. And if there's anything on these layers, it'll show it, all right? So that's how we can toggle very quickly and go through the layers. So let's get back to the top layer, okay? So that's single layer mode, and I'm gonna put it back into the full layer mode. Okay, now what we can do is, since we have all the components placed and we have this ground fill, let's go ahead and let's view it in 3D. What does this thing look like? Let's find out, all right? So they're very, very nice, and we've already seen that. Very, very nice, looks good. We can't really tell any difference with the ground fill, right? And the reason why is because we have this solder resist layer, this green solder resist layer on top of it, so you can't really see it, right? Go press 2 to get back into 2D mode. All right, so now I want to add another ground layer, all right, to the bottom. So let's select the bottom layer. Here it is here. There's the bottom layer. So that's what's selected, and that's what's active right now. All right, so now but we still see all these layers because it's just layering them and stacking them, okay? If we go into single layer mode, we would only see the current layer visible. So we can do that also, so let's do that. So let's go to single layer mode, click. Now notice, now you see just gray because we're in the bottom layer and there is no bottom layer. There's nothing there yet, right? So now let's go ahead and let's put a fill. So let's go back to, where was it? In home, all right? Yeah, that's exactly where I wouldn't put it. All right, there it is. Okay, so here we go. So name, so this is going to be bottom layer. It's not no net, it's ground. And again, that's just an English name. Layer is bottom layer, good. Connection, let's connect it to the net. And then here's some options here. Pour over same net polygons, don't pour over same net polygons, pour over all same net polygons. So pour over same net polygons only. In other words, anything that's a ground, pour it over it. That's fine. That's what we want. We're going to leave it at that. Again, we're going to leave all these things like this. You can play with these things later if you like. All right. You can read about them and just try experimenting. We've only got so much time to do things, so we can't try everything. All right, so again, I'm in the mode. So I've got that little crosshair, which means you're doing something. So let's start clicking. I'm going to zoom out. Whoa, I'm going to zoom out. And I'm going to drag this over here. And again, it's not the fastest thing in the world. Got to give it time. And I'm trying to get it over here, and I'm going to zoom back in here so I can accurately grab this vertex, this corner vertex here. That's better, got that. Now we'll scroll down here, pan down here, and I'm just panning by pulling it off the window. Okay, and we're going to do it over here again. It's now drawn a triangle. We've given it three vertices to find the minimum to make a two-dimensional polygon. And let me zoom out a little bit here, do it a little bit faster. Again, trying to be very careful so I stay in the mode and I don't lose the mode. And of course, when you're working with this thing that's got such asymmetry, it's really long or really tall, it makes it a little bit hard to move it around on the screen. Okay, we got that vertex, and now it's finished it up thinking we want a quadrilateral, which we do, but let's just make sure of it. So I'm just moving it up here again, and there's lots of ways to scroll also. I'm sure there's 25 different shortcuts to do it, but this is the way that I'm going to do it. And I click there, and now I'm done. So it's trying to do more, but I don't want it to do more. I right click, and then I've got my ground fill, and it's this highlighted blue, so it looks like this powder blue, baby blue, very light blue. All right, and now I'll just click into space, and now you see it. Okay, so let's analyze and see, oh, there's a ground right there, there's a ground right there, there's a ground right there, and those are our capacitors. Those are our bypass capacitors, right? So those should be good. There's a ground down there, the bottom of the IC. There should be another one there. Yep, it looks all good. Now, we are in, I believe, in single layer mode, so let's go into all layer mode. And now look, when we're in all layer mode here, we can now see the text layer on top overlaying, and then we can scroll through the layers so we can make the top layer of the primary layer on top. So we can see it, there it is, and then we just press minus and we just jump down to the bottom layer. It's smart enough to do that, plus minus, plus minus. If we keep going, then it'll go through all these other layers, all right? But since those layers have nothing in it, you're gonna see the opaque layers, which is the top and the bottom copper, okay? So, and also you can see top and bottom copper excuse me, are right here, okay? So they're just right next to each other, and that's why we can jump so quickly. Okay, Control S. Okay, let's go ahead and commit this. We're going to click on here, we're going to click commit. And again, just doing whatever this does on the cloud, who knows, and we get all greens here. Now I'm happy. I know that if my computer crashes or something happens, I've got it. Okay, so now we are ready to route. All right, so this is a big subject, and again, you could do a whole class, you could do many classes on how to route, and then once you know how to do it, then you have to become skilled at it. It takes many years. And when you're developing boards, routing is so complex, very few electrical engineers can route themselves or even try to route. Few of them even make their own printed circuit boards. So if you want to really be a full stack embedded engineer, obviously you have to be able to design the circuits, design the circuit boards, lay it out, do everything. So you really want to know how to do this. But again, it does take a lot of practice. You got to try things and figure things out. So one of the things, one of the rules, and again, there's like rules, and you can just come up with some rules of thumb, right? One of the rules of thumb is you want to make all the traces as wide as you can, right? So they can carry as much current, they have the least amount of impedance, and so forth. You want to make power traces very large compared to signal traces. So if you've got signal traces and you've got a CMOS circuit, you're talking about nanoamps, right? Microamps, right? Maybe milliamps is running through the circuit. You don't need those traces very wide, but the power rails or the power lines, you do want those very wide because that's going to send power to all of those ICs. And remember, we've seen those tables before that show the width of a printed circuit board trace and how much current it can carry, and AC and DC and all that. So the bottom line is, I'm just going to give you some rules of thumb. When you are laying out circuits, and you're going to be doing these layouts on these fairly simple printed circuit boards, you're trying to get your signal traces, 8 to 10 mils, 8 to 10 thousandths of an inch, 12 thousandths even better, right? your power lines, try to get those 12,000s, 15,000s, 20,000s, 30,000s, 40,000s if you can. Make them thick. Don't be afraid. Make them thick. But at first, don't make them too thick because you may not be able to route things, all right? So these are called design rules, and this is a huge subject, and all these tools, these CAD tools, have design rule managers where basically you can give it hundreds of design rules, and these may be design rules so that you get certain kind of characteristics from the board and you meet timing criteria, and there's so many things. The bottom line is these rules say, I want this, I don't want this, I want that, I don't want this. Hundreds of them. And all these rules then are read by the tool, and then the tool watches you. If you invalidate one of those rules or violate one of those rules, it tells you. If the auto router invalidates one of those rules, it tells you, or it won't do it, right? So where is that stuff? We're not going to get into too much of it, but we're going to take a look at it. So in Home, over here in Design Rules, now we have design rules, and again, there's lots of places to find these things in this tool, all right? So this is just one way to do it. So here's the design rule check, and here's the design rules. So now if we click on design rule check and the little drop down, this just says reset error markers, okay? So that's all that option, the only option there. What that means is after you've ran a design rule check, this resets everything so that you can run another one and flag the errors again. Otherwise, it just kind of leaves, it doesn't want to keep telling you the same errors if you don't want to know the same errors. So anyway, that's the only thing there. So you hit reset if you want a fresh run, a fresh analysis. All right, so we go to design rule check, let's click it, okay? And typically, you know, save everything often, so if you break something or delete something, you can just reload your last source code or data. So typically you can't hurt things, but sometimes you can damage something or do something that you can't visually see what you did. And then this gets embedded in your printed circuit board or your design way down the line. You don't even realize you did it. So you got to be careful with these tools because, you know, these are big complicated tools. There's a lot of buried menus and stuff, and they do really take years to get the hang of. Okay, so here is DRC. You've probably maybe you've heard this acronym or seen this acronym. It's, you know, design rule checking. Design rule checking. That's all that means. All right. Okay. Let's see. So we've got all these different rule categories: electrical, routing, manufacturing, and placement. Okay. So rules to check, report options, create a report, create violations, subnet. We're going to leave most of this stuff just the way it is. Rules to check. Now and then. Inside of each one of these categories, we can turn things on and off and so forth. So this is just saying, I want you to check all these different things: short circuit, unconnected pin, clearance. Now, for example, clearance, this is when pins are too close or traces are too close or something is too close, and your manufacturer will not be able to manufacture it if you violate that rule. Your manufacturer may say, hey, listen, we've got really old PCB stuff here, and it's like $2 to build a printed circuit board, but you have got to have a 10,000th of an inch distance between all your traces. That's the rule. So you got to put that in here. Otherwise, your auto router or yourself will violate that rule. And so that's what that clearance is about. Now, it could be clearance trace to trace. It could be trace to pin. It could be pad to pin, pad to pad. It could be pad to text. It could be anything. It could be anything. There's lots of these things. So that's where you know, you enable or disable these things. Now, this is just the design rule checker dialog, enable disable dialog. This isn't the rules. These aren't the rules. The rule, and then you just run a design check. Now go here, cancel here. Here's the rules. Much uglier. Okay, so here's the rule dialog, and there's all these different categories. So there's the design rules, all right? We're in electrical rules, we're in clearance rules, we're in this, we're, you know, all these different things, and then, you know, these blow up and there's subcategories of them, all right? So what we're going to do here is, all right, so we're not going to mess with too many things. What we're going to mess with right here is we're going to go into routing, okay? We're going to leave all this stuff the way it is, and if things violate, I don't care. It's just going to give me a warning usually unless there's an error. Errors are things like short circuits, unconnected nets. That's an error, but if something's too close, that's a violation, all right? All right, so we're going to go into the with category here, and we're going to this with category. Now, again, you got to play with this tool for a long time. I don't want to. I could spend 2 hours just on this one little dialog, so I'm not going to. But I just wanted you to know that it's here. So it says, here's the name with. So this is a name of a rule. It's the width rule. We can make many width rules. Right now, there's just one width rule, but we may want a width rule for signals, for normal signals, for power, for antenna, for there could be all kinds of things. So right now, we're going to let one rule say the width of everything, and it's going to be all encompassing. And basically, it's going to be a gross rule, not gross like ooh, but gross like it's going to encompass everything and it's going to apply to everything. So we know that everything will kind of follow this rule. Then later we can go in and tweak things, all right? So now typically when I do a circuit board, I'll have signal layer rules. I might have bus rules for things that are buses. Maybe they need to be smaller. And I'll have power rules, V sub CC, V sub DD, 1.5 volts, 1.8 volts, 2.5, 3.3, 5 volts, 6 volts, 12 volts. And every one of those rails, I might want to have a different thickness because maybe more or less current is going through it. So I'll have a different rule for each one of those. So when the auto router routes it, it'll route them trying to adhere to the rules. Now that you've got all that in your brain, here is a image, a representation of a trace. Now, so what it's showing you is, here's the trace. So I'm trying to connect one pin to another pin, right? Right there. And so it's saying, the minimum width is 10 mils, 10 thousandths. That's what I want is the minimum. Preferred is, in this case, 10. It's just showing it bigger because it's an iconic representation. And it's saying the max is 10 mil. So it's just showing this iconically. So this is not graphically accurate, right? If there were 10, 10, and 10, it'd all be the same. But it's saying that the min is 10, the preferred is 10, and the max is 10. Now, let's change that a little bit. So let's say that the minimum width is 10. Let's say that the preferred width is 12, right? And we'll say that the max width is also 12, all right? And we might even change that to make the min width 8. All right, so, but let's start from 10, 12, 12, all right? So that's what we're kind of shooting for here, all right? And so this says layers and layer stack only, characteristic impedance driven with. So this is something different. Remember, we know what the word impedance means, and this means the characteristic impedance or the impedance that a trace seems like if you were to measure the impedance. Remember we talked about all this. These lines are inductors and capacitors really, so they act like an impedance. They have a characteristic impedance. So, but that's only when you're doing kind of RF things or high speed signals where you have to start worrying about that. So don't worry about that. Just keep this the way it is and keep this checked right here. All right, and then we're done with that, so we hit apply. Okay, and that's the only one we're going to mess with. Now, also what we're going to mess with here, some other things. Routing topology, we'll just leave that alone. All right, routing priority, we'll leave that alone. Again, we can drop this down, and then it comes in here, and then routing layers, what layers, top layer and bottom layer, and I go through all these things. Routing corners, what do you want me to do on a corner here? And then here's some terminology, right? Setback is 100 mil to 100 mil. So it's talking about when there's a corner, right? You're going to make a 90-degree corner here, but it makes a 45-degree corner. So how far do you want me to make this little length right here? Okay, so that's what this is talking about. And you might have different properties that you want. If you start studying really high-speed signals, so there's a book called The Black Art of High-Speed Circuit Design. It's like a classic, very complicated, graduate level, and so there's a big argument going on. Does it matter to make things 45 or 90 degrees? And in some cases, it matters if they're 90 degrees because of certain things mechanically and this and that, and then waves can reflect and all that. But then tests have been done, and it shows that this doesn't really come into play until you start getting in very, very high gigahertz signals and all that. Bottom line, I make corners at 45 degrees. Unless it's a big, thick track, then I'll make it at 90. So leave your things at 45 when you make a corner. And this is just saying how much space do you want me to waste here when you're doing this. So what's the minimum, maximum, and all that. Or we can say, hey, give me a 90 degree, just like that. But we're going to leave it at 45. Or you could say round it. No one really rounds it. Rounded corners used to happen when people would manually tape, T-A-P-E, they'd sit on tape in a transparent piece of plastic, and they'd sit and draw their circuits with tape. I've done this, right? A long time ago, back in probably high school, I would tape out circuits, and we'd make our own printed circuit boards. But we would round them because when you have a little, a piece of pinstripe tape, you round it, right? Okay, but we're going to go 45. All right, so that's that. That's all that is. Now, routing vias. All right, so we've got routing vias, so all vias, and now it's saying a via diameter 50, 50, 50, via hole, blah, blah, blah. Let's talk about vias. This is important, all right? So We want to make, so if you've got really large vias, it's going to make it really hard, especially if these vias are so big, they're just like going to punch these giant holes through the board. So typically you want vias as small as you can make them, and so that the via is at least as large as a trace that it's being used to via from one layer to another layer. Okay, let me show you that real quick. Let's draw that. All right, let's draw that on the drawing program, which is not cooperating. There we go. So real quick here, let's get in here, and let's say that our board is green here, right? And it's been a while since I've drawn on here, so this is going to probably look horrible again. It is surprisingly difficult to draw on one of these pads if you don't do it a lot. Okay, so this is a cross-sectional view. So here's the red layer. So here's the red layer, and I'm just going to show a piece of copper. So there's a red layer right there, right? And that's just showing a piece of copper, you know, coming across that way. And then I want to via down through here and then connect to this blue layer, which is another piece of copper going someplace else, don't know where. So here's what the via looks like. Let's represent it here, like this. So there's the via. Let's make this red, go all the way through here. All right, and so there's the via right there, and this is a cross section of the via. Okay, and then let me draw this inside section. This would be the hole. So there's nothing there. There's nothing there. So that's a hole in there, right? So that's like all black or all gray. It's all open space. So now the distance, now let's take a look at some distances here. So this is the, from here to here, the outside to the outside. This is the via size. This is the total outer diameter, right? The OD, the outer diameter. Then inside here, this is the via hole size or drill size itself, right? So this is kind of the via size or the inside diameter. All right, so these two things, a manufacturer will tell you what the smallest is. Now, I'm going to tell you right now, typically the hole on the inside is about 10 mils. 10 mils is the, and we've talked about this, is the minimum in many cases. And then now we're going to turn this on its side so you can see it. All right, we'll use the same colors roughly here. Let me try this. So I'm going to enlarge it a little bit though. So here's the via here, and then here's the hole in the middle. Okay, so there's the hole in the middle. All right, so pointing here, this is the diameter of that. Okay, that's 10 mils. Now, from here to here, this little guy, this width here is called the annular ring. And this annular ring, typically, depending on who you go to, has to be a minimum of 5 mils. So if it's 5 mils over here, it's 5 mils over here, right? 5 plus 5 is 10, 10 plus 10 is 20 mils. So the total diameter of the via, typically you can get away with a 20 mil via with a 10 mil hole. But you have to verify this at your manufacturer, okay? But this is like 90s tech, so most of them will do this. And if it's a modern company, they can go way smaller, right? So that's kind of what we're shooting for. So 20 mils and 10 mils, and that's going to allow us to route much better because our vias won't get in the way of things. All right. Okay. So let's switch back here. Okay, so what did we just say? So here's the inside. Okay, so via hole size, and we don't want any of this minimum maximum stuff. Let's just stick to one thing here. So minimum and maximum and preferred, just one size, and that makes it easier for your manufacturer. He's not going to be crazy. Now, one thing, since the via is only 20 mils wide, we're going to make it 20 mils in 1 second. We don't want to punch a via through a trace that's 30 mils. We have to make a 30 mil via. So we have to manually change that via or have another rule. So keep that in mind. So we'll just say we won't make any of our power rails bigger than 20 mils. 20 mils will be fine. All right, so minimum here for the via diameter, what do we say, 20? So we're going to make that 20. And we're going to make this 20. And we're going to make this 20. And these will be tiny little vias. Okay, and we're going to hit apply. Not okay, because I still want to mess around here. Okay, is there anything else? Fan out control. This is talking about when the router's routing, you know, how many things can be fanned out from a signal, and then mask plane manufacturing. These are things I don't even want to mess with. Okay, we'll hit apply here. We're done. Okay. Okay, so those are the design rules, and we're going to get violations if we violate those rules. Pretty simple. Okay, so now let's go ahead and let's route some of the board. let's route a little bit of the board here. So we've got our top layer, we've got our bottom layer. Let's start on the top layer. So I'm going to press plus or minus to get me to my top layer. Now you ask, well, wait a minute, I don't know what to route. So what's supposed to be connected to what here? Okay, well, how you do this is you go to your schematic and you look and you say, I know that BT1, BT2, BT3 are all connected. So I can just connect those two. What else can I do? Well, remember the thing called the nets? The nets that shows the nets, the network of connections? Where was that? I don't know. Project, it was in view, it was in home. I believe it was in home. Let's see here. I will find it and tell it to you in a moment. Here it is. It's in the perfect place. Let's write this down somehow. It's in routing. So in routing, show all, show net, hide all, hide net. So we're going to say show all because we want to see all the nets. And notice when I did that, all these little wires started showing up. All right, so that's where that is. Another horrible place. This should be in view. Home, connections, and we say show all or hide all, or we can say show a specific net or hide a specific net. Maybe we only want to see power. Okay, so here's the nets. All right, so now let's go over here to our batteries. All right, let's work on the top layer. All right, so now where do we find this tool? So home, and we go to place here, and then we've got pad, we've got line, we've got via, we've got arc. Okay, we've got those things. All right, we don't want to place any of those. All right, we don't want to place it via. At some point we're going to place, but we want to go to route here. All right, and we're going to go to interactive routing. That means I want to interact and play with it. Okay, so we're going to go to interactive routing. There's other routing modes here, but interactive is the one we want for manual routing. Now we're in it. So now what we're going to do here is I'm just zooming in, and let's do this. Let's get into it. So I select on this, and what's our snap grid? 10 mil. So we're going to stick on 10 mil. Now I just click on this, and now you can see it's routing. Now there's different modes, different kind of algorithms and following that this thing will do. So now watch this. So if I have it here, if I press space, I believe it's space, it'll go through different kind of routing obstacle modes. All right. So you can see track 45 down at the bottom here. Let me get out of that. Well, it just erased it. Down at the bottom, it shows the kind of mode, and there's different modes of routing that kind of will run the trace in a different way that you may like, being able to push things and all that. Right now, we can't see too much because we don't have anything really to route yet. But once we get some wires in here, you can see that behavior. Okay, so you can see, here's the net. This is net B2, BT2_2, and we're going to route it. So I click there, and it dims down everything so you can see what you're doing. And of course, you can play with these colors. And we're going to go right there, and we're going to right click. All right, one polygon, but would you like to? Okay, so now what's happened now is because I did this route, I've modified things, and it wants to re-pour the ground fill. So yes, re-pour now, go ahead. And now notice what's happened. It's not going to fill all this in because there's a trace going through here, so it stops the ground fill, which it better because otherwise it would short the signal to ground. All right, so now we got that. Now this is a power trace, right? Later I'm going to make this thicker, right? I'm going to make this thicker. So what I can do is I press escape here. Now when I hover over this, you can see a white line. I can right click or I can double click to get its properties. And we'll just let the wonderful, and again, half the time I can't tell what's going on because the cloud stuff. And this says include, over here in the PCB inspector, remember this has a filter. Got to be careful of this, so we need to put this display all objects. All right, now, because it was just showing text. Let me, and okay, here's another thing I want you to be careful of. When you click into this ground, it'll select this, and if you're not careful, you'll delete the thing. All right, so be careful. All right, so we select that. Here it is over here. Now look, it says the width is 10. So now, since this is power, I'm going to make that a 20 mil. And because I did that, I have to re-pour. There we go. All right, and now notice it's got a bunch of X's on it. Give this thing a second here to respond. Give this thing there we go. Notice it has a bunch of little X's. You know why? Because I made a violation. Remember we said that all traces should be, what did we say, 12 at most, right? 12 mils at most. Well, this is 20 mils. It doesn't like that. But it's okay. I'm telling you it's okay. And by me, I mean I'm telling the tool because I want it like this. So I can live with that violation. All right, so that's okay. And now I'm going to do it again over here. So again, we're going to get over here and we're going to get back into our interactive routing. And I'm sure there's a key press to do that. All right, we got that. I'm going to hit escape. I'm going to re-pour now. All right, then I'm going to press escape. I'm going to double click on this and see now what it did is because I double clicked, it gave me this little dialog instead of this one, and we can go change it here also, right? More than one way to skin a cat. Re-pour now. Okay. All right, so now we got those two nice traces. Good enough. All right, and now this one goes to the switch. Right, so this one goes to the switch. So now what I'm going to do here is I'm going to again get into this routing, and here it is here, and I'm going to click it. Now as I do, okay, see where it's going here? So I could do it just like that, but that is really ugly. Obviously that's not a wise thing to do. Now if I press the space bar, watch what happens. Not much. Okay, there it goes. It's kind of changing. There it goes. Kind of changing what it's doing, right? It's not doing this hugging thing as much or whatever. So again, this is just, this kind of flips and tries to do the route in a different way rather than you having to work on it. But let's do it ourselves, right? Let's not let this computer do it. I do not want the computer doing all this. I want to do this. All right, so what I want to do is I'm going to kind of push it up here interactively. That's good. I'm going to come down here, and then I'm going to kind of do this. I'm going to do this, and then right click, I'm done. Now report now. Okay, see that's a nice little track. Now I look at it and you see this distance right here. Over here, maybe I want to back this out a little bit, so I select that piece. Just click on it. It's smart enough to select it. If not, you got to fiddle with it, right? And I'll drag it out. See that? And as I drag it out, it kind of creates that straight piece there. Report now. Okay, good. And let's go ahead and make this whole thing thick. Uh-oh, look, when I click that, it's only clicking this, it's not getting this, it's not getting this, right? So my options are to get this whole thing is I have to hold down Control or Shift. Let's see if we do Shift. I believe that's it. Yeah, we do Shift, Shift. We get all the little pieces. Okay, now I got it all selected. And now we go over here, because this is a power line, and let's make that 20. Okay, make that 20, report now. Okay, and click here. All right, looks good. So you see the process? That's routing. All right, and you just got to sit here and do this. Okay, and it's painstaking. Okay, and it takes a long time. So let's go ahead and let's do a component here. Let's do a component. So on U1, we know that C2 is this bypass capacitor. All right, so let's go ahead and let's go back into interactive routing mode here. We'll go there. We're going to get that one done. Okay, we'll say report now. Just for now, I'm going to leave it that width right there. Even though it's a power line, I'm just going to leave it. All right, I'm going to come over here, get back into interactive routing, and this one goes, if we zoom in, right here, okay? And then V sub CC goes to these 2 pins, so great, let's put it to those 2 pins, great. And then of course at some point we're going to have to connect V sub CC, all the V sub CCs together, right? And then let's do this C6 over here. Let me get out of here, and let's go do C6. All right, and when people start trying to do routing, they have a lot of questions, and the questions are why or how, or there is no why, there is no how. You just have to do it. You have to get experience at it. You have to figure out why you do things and why you don't do things. You have to get these rules of thumb and just get the hang of this. All right, piece by piece, inch by inch, you do the routing. All right, let's get these capacitors right here. And again, I don't need to look at the design. I could look at the design, right, to see what's connected to what, but this is helping me and showing me what's connected, right? But I also may want to look at the design because this is just showing a very narrow scope view. The design itself, I see the whole thing at once, and I can cognate, well, I probably don't want to connect that to that. Maybe I want to connect this to this, then this to this, you know, different ways of doing things, all right? Because we're going to run out of space here real quick. And you're going to wonder, how do they route a motherboard, right? Very carefully, that's how. All right, so let's go back in interactive mode. C3 here. So let's get this guy, and it's just going right here. So I'm just going to now, again, if I just let this thing go automatically, it kind of, let me show you this. See how the track is coming in not centered? I want it to come in centered. It's coming out centered, but it's not going in centered. So just using this router, I can hit spacebar, right? And see, that's not helping me, right? I'm still getting this off-center hit. So I'm going to manually go down like this. See that? And then I'm going to bring this in centered. I'm going to try to. All right. And what's happening now is because the grid snap that I'm on, it's not allowing me to get any more, and it didn't. Here's another thing. When you're, sometimes you got to double click. There we go. You got to double click to make sure you get contact. Now, I'm not happy with that because I messed with that track and it didn't quite do. Okay, so it is connected. You got to be careful. Make sure you can see that. Make sure you can see that it's connected in there. All right. And because sometimes it's not, so you got to be careful. But it didn't hit. And again, we're getting in a weird, funky mode here. Okay, it didn't hit. It didn't hit exactly in the center. So again, but that's okay. We could pull it if we changed what our grid snap is to 5 mils. All right, but we'll just live with that right now. Okay, Now let's go ahead and let's save this. All right, let's recommit this. Give it a second to save, and then the commit should come up. Yep. All right. And now what's happened, something's got selected here, and I'm not sure, I've seen this happen before, and it just gets kind of funky. All right. And I'm not happy when it does this. It's not, let me try and, yeah. And I'm sure I don't know what I'm doing, and that's why it's doing this. If I select, and now I can't select this. You see this? I can't select this ground plane anymore. It's not allowing me to select the ground plane. So this is selected here. I'm trying to deselect it. And let's see here. Okay, so let's try and get out of interactive routing. So I don't know if this is a bug or just some kind of weird behavior, but the whole thing is I can't. Okay, I seem to be able to get it that time. All right, now let me see. Can I click? No. It's keeping this unhighlighted, which I do not like. So I can't tell if this is a bug or not. So what I'm going to do is everything is saved right now. So I'm going to just restart this and then just get right back here. So I'll see you in 1 second. All right, we rebooted the machine and, well, not rebooted the machine, rebooted the application. It seems to be working again. So again, I don't know if that's a problem, but it seems to get locked up in a state. If that happens, just better to restart the application rather than keep in a funny state where it could damage your files. All right, so we were just routing right here, manually routing on the top layer. And so we just did C3, so let's go ahead and do C4. So we're going to go back to route, interactive routing, and we're going to grab. And again, if you zoom in enough, the net names will come up, net C4.1, net C4.1. And we're just going to go in here and go ahead and grab it, double click. You got to double click at the node. And again, we're not hitting, I like to hit these things on center, dead center, so it's coming in perfectly perpendicular to the circle here, to the circumference. But we can't do that with this snap grid. We'd have to go down to 5 mils. So we're not going to do that. We're just going to stay at 10 mils. Okay, so we've got those two traces there on U1, and we can continue. We can see that pin 2 goes to pin 6. Let's do that one. That's an easy one. All right, pin 2 to pin 6. Again, let's get pin 2 here, and we'll come in, and we could come in like this and go tight, or we come through the middle. You know, there's lots of ways to do this. All right, double click, repour, and then when we're done, what we're going to do is we're going to go grab things. And again, whenever you select an object where there's multiple layers, you have to select the one you want. There we go. And I'm just dragging it a little bit. And when we're done with routing, we're going to go back and clean everything up. All right, we're going to clean everything up. So this is the process. All right, so now I could sit here and route this entire thing for you. But what I'd prefer that you do is you just use the auto router for now. And then what I'd like you to do is augment the auto router with yourself. So after it auto routes, you kind of take a look at it and you go, oh boy, that's ugly, that part's ugly. And you can rip the traces up. It's called ripping. The traces up and then redo them yourself manually and clean them up, change the size of things and so forth. Okay, so we're going to try and use the auto router. And remember, the auto router is going to be able to route on two different sides, on the top copper and on the bottom copper. Okay, all right. So we'll just put it here on the top. And what we're going to do is we'll zoom out. We're not going to be able to see much here. It's not going to do it visually. It's just going to do it and then pop it all up. Now let's do a Control S here to save. All right, and then now what we're going to do is first we're going to run a design rule check here. All right, so we're going to go here, we'll say reset markers, we'll click design rule check. All right, and then we want to run design rules. All right. Okay, and you can see here we've got all these violations. All right, so 38 of them are unrouted nets. We know about those, okay, because we haven't routed them. 44 are silk to solder screen mask clearance. Don't care about that, right? That's the solder, the silk screen, that's the text. Don't care about that. That's not anything functional. And then these are silk to silk screen. Again, and what is it talking about silk screen? And the reason why it uses the word silk screen is silk screen comes from a printing process, right? Which may not necessarily be the way they do it. It's called silk screening still. And it's a way of printing material or printing on surfaces. It's called silk screening, and it's a layer process with ink and so forth. It's a printing process, so it's called silk screen, and that's where that word comes from. And it's completely confusing and really doesn't have anything to do with anything anymore. But that's just talking about the text. The text. We don't care about that. So we're doing pretty good. So basically, all we have to do is get these nets routed, these unconnected nets. So here's this design rule report. Now, what you can do is you can drag this off to another monitor. I have another monitor over here, another monitor over here, which you can't see. I could drag that off, but I'm just going to close it. So I'm going to right click on it, close design rule verification report. I don't need to see it. I already know. All I really need to do is get these nets routed. So let's use the auto router. So let's find this thing. Where is the auto router? So in home, clipboard, routing. So here's routing. So it should be in routing, right? No, not in routing. So interactive differential, not there. It's not in unroute. It's not in connections. It's not here in place, not in collaboration, not in any of these things. Where is it? It's over here in tools. Total horrible placement. Drives me crazy. Here's the auto router right here under auto route. And it's not route. It is route. It's auto route. It's routing. So we're going to click here. And so if you click the icon itself, in this case, many of these things will go to a dialog, but this one doesn't. It only will drop this down. So again, this tool has weird behaviors. So we can go to setup, we can go to all, we can do all this. So let's just go to a setup. Now, in setup, this is where we start to play with the parameters of the auto router, right? So routing width, routing via styles, all these different things here. Let's take a look at these. And there's strategies for routing. How do you want me to route it? A router is a very complex piece of software. Routing is an NP complete problem in computer science, and so these routers use heuristic algorithms. Some use artificial intelligence, some use all kinds of different methods to route your board. And routers can cost from $200 to $50,000, or very expensive pieces of software, especially if you want to route high pin BGA ball grid arrays, 1,000, 2,000 pin FPGAs. On 60 layer boards, crazy stuff. So these routers get really expensive. Many routers do a horrible job, and most electrical engineers just will not use them, including me. I typically won't use them, but they're getting better all the time. And this router is not bad. The router inside of this, and I'm not sure which router it is. I'd have to look it up. But it's not a bad router. But it can have different strategies where it optimizes different things. So it has a priority of, I want to make your buses this, or I want to do your power like that. Again, a gajillion different settings to make that happen. But let's start off simple. Routing widths. So remember this, we set this ourselves. So rule width, the rule, its name is width. Okay, it's not rule width, it's the name is width. So if we were to click on this thing, we could say edit rules, and I believe we can just click on this one. Yeah, and it brings up the rule specifically. And we already set this rule. So on the top and bottom layer, we said minimum is 10, preferred is 12, maximum is 12. We'll just hit cancel. All right, routing via styles. Remember we did this, right? So we could click here. Remember we said we want it to be 10, 10, 10 for the whole size and 20 for the total width, all right? So that's good. And that's the only thing we did. And then there's all these different things here we can play with, but we're not going to play with them. And that's where you do all this right here. Yeah, it's the Citus router, S-I-T-U-S Citus router. Says it right there. And that's a very popular router that's used and licensed by a lot of companies, the Citus router. Okay. So we'll hit cancel on that. Let's go back to auto route. And so we're going to say all. And we go back here, and all we're going to do is just say route all. Now, rip up violations after routing. So what this does is if you click this, anything that's a violation, it'll rip that trace up and just get rid of it so that you can go at it. We don't want to do that. We want to leave everything because I don't care about violations, because I know the only violations I'm probably going to get are clearance violations to text and things like that, which I don't care, are not functional. All right, so let's leave that unchecked. Okay, and then like I said, there's these different strategies here. There's this strategy, default two-layer with edge connectors, default multi-board, general orthogonal, via miser. So the via miser, let's look at that. For routing multi-layer boards with aggressive via minimization is what it says. So maybe I don't want to punch a bunch of holes in the board because that's going to cause some kind of a problem with RF or EMI or the integrity or the thermal characteristics of the board, right? So that's just one strategy. Okay, so let's go back to default two-layer board, looks good. And we can create, these are just built-in strategies which are based on a parameterization. So there's a bunch of different parameters that you can change, and then you can say, I want to call this the default two-layer board. See, we can add here and create other strategies. And then when you do that, a big dialogue is going to pop up and you're going to fill out a bunch of things which are really complicated. So we're not going to mess with it. Okay, here we go. Ready? We're going to say route all. Cross your fingers. Now this process used to take minutes to hours in the past, but this is an i7 something, i7, I forget the name of the particular version of the processor, but it's a fast one. I think it's running at 3 or maybe 3.5 gigahertz. All right, so during the routing, it's done. Now it wants to repour the fill polygons, the ground fill. So let's say, sure, repour, go ahead. All right, okay, now not sure if it's done. We'll scroll around in a second. I see the cursor flickering, but here in this window, the output messages, look here. It said up here, routing started, creating topology map, starting fan to plane. It's just telling you all these different states that it's going into here. 27 of 48 connections were 56% done in 2 seconds. Really, really fast. 46 of 48 were 95% done. And then a lot of times it'll get 99% done and get stuck for a little while. It'll have to keep trying different things to, a couple traces it'll get stuck on, and then it'll finish. All right. And what you might have to do is you might have to move around a couple ICs or just manually route those last signals. So anyway, it was able to finish itself and do everything. And 48 of 48, 105 seconds. So it took it 5 seconds. Crazy, huh? This might have taken like minutes before in the 90s, but now it's very, very quick. Okay, so here is the board. And there it is. I just clicked in there, and once it hit that message box, it popped up. So I'm just going to zoom in and look at this. All right, and now what's interesting is a lot of the routing is on the blue plane, which is kind of interesting. So on the back plane, it did a lot of the routing instead of the top plane. It made that decision as it was working. All right, and routed there on the bottom plane. Let's put this into single plane mode so we can see a little bit better. So we'll go to Home, View, Single Layer Mode. There we go. All right, and now we can switch between the top layer and the bottom layer with a plus and minus here. Oops. There we go. And now what we're going to do is we're going to go through this manually, and we're going to clean this up for things that I don't like. All right, and I'll tell you why I don't like them, and then we're just going to clean this board up. So let's start with the top layer. So I'm going to zoom out. All right, so what we're going to do now is the thing has been routed. Okay, so there's the top layer and there's the bottom layer. All right, so it's been routed. So good. Let's go ahead and let's run our design rule verification again. Let's make sure we're okay. So let's go to Tools, which it's not in. Let's go back to Home. There it is. Design rule check. Let's go ahead and reset error markers. Great. Let's click on design rules. I want to do the whole thing. Run design rule check. Okay, there's our report. So let's look. Rule violation 63. Okay, errors 0. Okay, violation, don't care about. Errors, I do. So we look here. What do we got? We got width constraint. So a couple traces, we violated the width constraint. We click on that. It'll show us where they are. Don't care right now. Solder, silk to solder, mass clearance. A couple times, many times, it's violating that, but I'm sure it's okay, because we set it's set for 10 mil, which is huge. So this can probably go down to 6 mils or even 5 mils. It would be okay. I'm sure it's okay. Silk to silk clearance, again, it's been set for 10, which is huge, and probably got some 9s or 8s in there, and that's why those violations occurred. But the big thing we care about